No, no. I mean, I think at the end of your talk, there will be some question coming in the will be coming in the chat box.
Okay.
The chair will read it out for you, or you can see it yourself
Okay. Okay.
to answer those questions. Yeah.
And I should talk for 45 minutes, right?
Yeah.
Yes.
Yes.
So, welcome everyone. Good morning. Welcome to the sixth day of VMF 2020. For today's symposium on algebra and number theory, Professor Moushumi Mondol from IIT Kharagpur will be chairing the whole session. Ma'am, it's up to you.
Yeah. Thank you, Saurabh. Good morning, everybody. So let me welcome you to the sixth day of the conference. First, I would like to thank the organizers for arranging such a wonderful conference. We are almost at the end of the conference, and it has been really successful and full of mathematics. So I hope many people have got many ideas and they have been benefited from this conference. So today's morning session, I would like to start with our first speaker of the day, Professor Santosh Nadinpalli from Indian Institute of Technology, Kanpur. And he will talk to us on the theory of types and interior support of smooth representations of p-adic group. So please welcome Professor Santosh Nadinpalli for his talk.
Thank you very much for the introduction. And okay, I hope you can listen to me, right?
Yeah.
Okay, so this talk is about detecting invariance of smooth representations of p-adic groups, where by the way of looking at the restriction to the compact open subgroups. Okay, and the first part of the talk will mostly be recall of the general theory, and second I will explain some results and open problems and possible techniques involved in such problems. So okay, let's start. So, okay. So let P be any prime number and let QP be the field of p-adic numbers and ZP is the set of p-adic integers. So one thing is that, so whatever I say in this talk is mostly valid for any finite extension of QP, not necessarily QP, but for simplicity, I'm just considering the case of QP. Okay, so I'll just consider the case of QP in this talk, and P is any prime number, and QP is a field of p-adic numbers, and let ZP be the set of p-adic integers, the usual things. The field QP is locally compact field, and the sequence of open subgroups given by p power n ZP, they form a basis of topology around the origin of QP. So this is a very weird thing, like the basis of topology is given by open compact subgroups. So this is very weird compared to what we see in real numbers. So G be any reductive group or QP. I'm not going to define what that is, but you can all your favorite examples like GLN, SLN, SO, exceptional groups are all examples of a reductive group. You can, if for most of the talk, we'll be concerned with this list: GLN, SLN, classical groups, and so on. So, and once you have a reductive group, you can talk about the group of QP points of the reductive group. This guy is naturally a locally compact group such that the identity has a basis of open compact subgroups which are induced from this filtration of QP. Okay. For simplicity, we'll call G to be a p-adic group. Okay. And for instance, when G is GLN of QP, the sequence of groups identity plus p power n times the matrices over ZP, n cross n matrices in entries in ZP, forms a basis of topology around identity. Okay, so this guy is decreasing sequence of compact open subgroups, and they form a basis of topology around identity. Okay, so in this talk, we are interested in the category of smooth representations of G. That means those representation rho comma V is a vector space and rho is the action of the group on the vector space for which the following property is satisfied. Every vector basically has an open stabilizer. So this is what the condition says. For any V inside V, there exists an open subgroup K of G such that rho K times V is V for all K inside K. Okay. In this definition, we haven't used any topology on V, neither the characteristic of V. V can be a vector space over a field of any characteristic. It does not matter for this definition. Okay. And irreducibility of smooth representations is the usual algebraic definition. That is, there is no non-trivial G invariant subspace of V. Okay. In this talk, we are mostly interested in complex representations, and the category of representations is denoted by this mathcal G. Okay. So let's look at some examples. When G is GL1 of QP, which is the non-zero numbers in QP, any reducible smooth representation is a character such that the subgroup 1 plus p power n ZP is contained in the kernel for some n bigger than or equal to 1. Okay. These are the examples for GL1 case. And now we can see in the case of QP star that this guy has an isomorphic copy of Z, which is spanned by, which is the group generated by this by the element prime number P times the compact group ZP star. So this already shows that the category of representations of a p-adic group cannot be semi-simple. After all, if you look at those representation on which those representations for which ZP star acts trivially, then you just have one linear operator and there is no reason for that to be diagonalizable, right? So therefore, the category of p-adic groups are in general not semi-simple, but mostly the semi-simplicity is caused by this phenomenon itself. And that's we will see how this manifests into understanding the category of representation itself. Like many parts of representation theory, we also have good induction functors, which sort of builds representations of a bigger group from starting with a smaller group. Okay, so let H be a closed subgroup of G. The induction functor basically gives a map from the smooth representations of H to smooth representations of G. What does it do? It takes a representation sigma comma W of H to the G representation on the space of locally constant compactly supported functions sections of the bundle G cross H comma W of the product space to the usual coset space. Uh, are people able to listen to me? Can you listen to me?
Yeah, it's fine.
Okay.
You can carry on.
Yeah. So this is the usual induction definition for finite groups and all other groups. Depending on your smoothness or your topology, there would be some topological structure on this guy. But in our case, we do not put any topological structure. This is almost like a set, and this guy is a p-adic manifold, and one can talk about locally constant functions and so on. We look at for every representation sigma comma w of h, we associate a G representation, which is the locally constant compactly supported sections of this bundle. That's the induction functor. So in the case of GLN of QP, typically we are interested in the groups H of the form QP star times K, where K is a compact open subgroup, or H is a parabolic subgroup of the group G. So we'll see some examples of parabolic subgroups and so on. Parabolic, yeah, incoming. So unless G is compact modulo its center, all finite dimensional representations in the category of smooth representations are just characters. Typically, this means that all representations that you encounter in this theory are infinite dimensional representations. Okay, so what is a parabolic subgroup? Parabolic subgroup in a general reductive group is an algebraic subgroup P of G such that G mod P is proper. Okay, this is a definition, but we will see many examples in GLN which are much more concrete in nature. So let's start with the basic example of GL2 of QP. So in the case of GL2 of QP, the upper triangular matrices form is the first example of a parabolic subgroup. You can see that the quotient GL2 of QP modulo B is the set of all lines, which is the projective space over QP, and hence it is a compact set. So therefore, this is the group of invertible upper triangular matrices is one of the basic examples of a parabolic subgroup. Okay, now this the group B has two important subgroups, which is the set of invertible diagonal matrices and the unipotent matrices sitting inside B. One knows naturally that B is the semi-direct product of the unipotent group times the torus, or the invertible diagonal matrices. Suppose if chi is a character of T, then we can consider this as a character of the group B itself via inflation from the projection map from B to T. When you go modulo n, you naturally obtain a map from B to T. So by this way, you can consider this character chi as a representation of B, and then you induce this representation. So this representation induced from B to G of chi is usually called as a parabolically induced representation, or it's also called as a principal series representation. So it turns out that this representation is generically irreducible. So this means that there are only finitely many characters chi for which this representation is reducible, right? And that is there. In fact, there are just two values of this character chi for which this induction is reducible. One of them is identity, of course, and the other one is a modulus character, which I will not define in this talk, but they are more or less equivalent. Okay, so if chi is equals to identity, then you have the induction. You can look at the induced representation, induce B to G identity. These are all functions on the space G mod B. So when you have functions on G mod B, you can look at the you can look at the constant functions, which forms the identity representation inside the space of all functions. So the quotient of, so therefore the identity representation occurs as a sub-representation of this guy, and the quotient is called the Steinberg representation and is an irreducible representation of G. So this induced representation in general has length 2. So it can have two subquotients usually. So this is the example for GL2 case, and in general also this is the parabolic induction is not very different from this case. The structure exactly looks like this, but let us look at what are parabolic subgroups of GLN case. So parabolic subgroups of GLN QP are associated to flags. So a flag is basically a sequence of subspaces inside QPN such that it's a decreasing I consider it as a decreasing sequence of linear subspaces of QP. The parabolic subgroup P associated to this flag is basically set of all elements inside the general linear group which fix F. This means that G of Wi is equals to W is contained inside. Yeah, so it's basically it fixes this flag. So let N be the group consisting of all invertible matrices which fix these quotients. So Wi modulo Wi plus 1 is equals to Wi modulo Wi plus 1. Okay. So now we got P and N. N is a normal subgroup of P, and we want to get a subgroup M such that P is N times M. So this is like defining a Levy subgroup. So when we want to define a Levy subgroup, we need to have a choice of a splitting. So this means that you choose subspaces Vi such that Wi is Wi plus 1 direct sum Vi. Then M is defined as the matrices which fix these VIs. Okay. Now, if sigma comma W is any irreducible smooth representation of M, then we consider sigma as a representation of P via the inflation map from P to the projection P mod N is equal to M. Now, in this way, we get a general parabolic induced representation, induced P to G of sigma. So this is the in general parabolic induction construction. So we talk about a parabolic subgroup which has a unipotent subgroup inside it, and this unipotent subgroup will have this unipotent subgroup has a complement to it, which is a Levy subgroup, and P is the semi-direct product of the unipotent group times the Levy subgroup, and then you form the parabolic induction using this procedure. This holds for all reductive groups whenever you have a parabolic subgroup contained inside that. Can you listen to me?
Yeah, we can.
Yeah. So a parabolic induction functor is a very nice functor. So in sense that if you take arbitrary closed subgroup, the induced representation may not have finiteness property. That is, suppose you start with an reducible representation and you take a induction, and the first question is that does this induction have a finite length, or is it finitely generated in first place? So in general, it turns out that if you take an arbitrary closed subgroup of the p-adic group and you perform induction, you lose many finiteness properties, you lose finite length, etc. But this does not happen for parabolic subgroups. So in general, the parabolic induction functor preserves finite length. So it takes finite length representations to a finite length representation. So that is advantage in working with this particular induced parabolic induction. Okay. So now naturally the question is that can every irreducible smooth representation of G can be obtained as a subquotient of a parabolic induction? So is it possible? Does all the parabolic induction and their subquotients exhaust the entire irreducible smooth representations of G? And it turns out that it is not the case. but somehow it is surprising in p-adic groups, but because when you do representation theory of real reductive groups, then you do have such a theorem which is due to Harishchandra, but in p-adic groups such things do not happen. So there are many representations which do not occur as subquotients of parabolically induced representations. So these are called the supercuspidal representations. Okay, now it is, of course, one has to somehow show examples of such representations, and I will indicate some easy method to see it for GL2, and for other reductive, for other supercuspidal representations exist for all p-adic reductive groups. So that is known, and then for GL2 it's almost easy counting exercise. So supercuspidal representations, in other words, can also be characterized by some other means without using the parabolic induction. They are basically the matrix, those representations for which the non-zero matrix coefficients are always supported on a compact set modulo its center. So you can, of course, like as a finite representation theory of a finite group on a finite vector space can be realized as matrices, and the entries of the matrices are called the matrix coefficients. So even in this theory, one can define analogs of the matrix coefficients using the dual space. So basically, you can use the dual of the smooth representation to define the matrix coefficients in the usual manner, and they must be supported. They must have a compact support modulo its center. I will not go into this definition. This is not very relevant at this point, but they have an independent characterization apart from parabolic induction functors. So remember, so far we have constructed parabolic induction, and we have constructed the parabolic induction, and we said that there are representations which need not exist, which need not occur as subquotients of these parabolic induction, called the supercuspidal representations. Okay, this is so far. And let's give some examples of supercuspidal representations. Let K be the group GLN of ZP, the compact subgroup of GLN of QP, and let sigma be an irreducible representation of GLN of FP such that it does not have any fixed points for all P silo subgroups of GLN of FP. So such a representation is called a cuspidal representation of GLN of FP. This must be of GLN of FP. Okay. So for n equals to 2, it is just a simple counting exercise on conjugacy classes. So you have basically induced representations are just induced from characters of the torus, and then you can just count the number of conjugacy classes which are given by the rational canonical form and so on. So it is very easy to count the conjugacy classes of GL2 of FP and count the number of parabolic induction, number of representations obtained as parabolic induction. We have already seen that it has at most 2 factors, and using this counting exercise one can simply realize that there are representations of GLN FP such that sigma has no fixed point by P silo subgroup of GL2 of FP. So n equals to 2, it's very easy counting exercise, and that will show the existence of cuspidal representation for the finite group. So when you have so what you can now do is that suppose sigma is such a cuspidal representation of K, then via natural inflation map you consider the sigma as a representation of the maximal compact subgroup K. And now you extend sigma as a representation of QP star times K by setting P to act trivially on sigma. Okay. So you set P to act trivially on sigma, and then that becomes, so now sigma can be considered as a representation of QP star times K. Now you can form the induction from QP star K times GL2 of QP of sigma, and this is an irreducible representation. So the way to prove that this is an irreducible representation is just use the usual Mackey criteria. Look at the double coset representatives GL2 QP modulo this guy, and one can show that there is no intertwining. And one easy the fact that there is no intertwining exactly follows from this condition, that there is no fixed points by the p-silo subgroup, and that gives you the result that this is irreducible. And since this is induction from a compact open subgroup, using matrix coefficients argument, one can show that this is an irreducible representation. Okay, irreducible supercuspidal representation. So supercuspidal representations does exist for all p-adic reductive groups, and this is not easy result. However, it is slightly subtle or counting argument of this form. One can now show that every irreducible smooth representation occur as subquotient of a parabolic induction where sigma is now so I keep using the word cuspidal and supercuspidal in interchange, but of course that is true for complex numbers. There is something to prove in positive characteristic, but this talk is all about complex numbers. So I'll just keep using supercuspidal and cuspidal in an interchange way. So so basically now any irreducible smooth representation occurs as a as a subquotient, or rather a quotient of the parabolic induction, where sigma is now a cuspidal representation of a Levy subgroup of P, where remember Levy subgroup is this M that we define such that P is n times M. Now, the question of classification of irreducible smooth representations of a p-adic group can be reduced to understanding subquotients of parabolic inductions and cuspidal representation. But both these things are equally hard, and the methods that are usually used in proving such results are totally different in nature. So the way to analyze subquotients of parabolic inductions and way to construct cuspidal representation are sort of orthogonal in nature. Usually they are very different techniques are used in both these things. However, if you want to understand the category of smooth representations, it is just of course it is reduced to first understanding cuspidals and then trying to understand what are the subquotients of parabolic induced representations. However, in practice what happens is that you assume that cuspidal representations exist, and the techniques of understanding the parabolic inductions, what are subquotients of them, one does not require many serious properties of the cuspidal representation. Okay. So now the question comes, if suppose you have two parabolic inductions. So if you have two different parabolic induced representations, now it might happen that a smooth representation can occur in both these parabolic induced representations. So you want to reduce redundancies in building the the set of irreducible representations. So the first question comes is, when does two parabolic induced representation have the same or a common Jordan holder factor, at least one? So let's take two parabolic subgroups. P is equals to m1 times n1 and q is m2 times n2, where n1 is the unipotents and m's are the Levy factors. And let sigma 1 and sigma 2 are two cuspidal representations of m1 and m2 respectively. So the Levy subgroup are always reductive groups, so cuspidal representations again make sense. And it is natural to ask, when does two parabolic induced representations have a common Jordan holder factors? Okay, so the answer for this is rather simple. So if suppose the parabolic induced representations have a common Jordan holder factor, then there exists a element G inside G such that M1 and M2 are conjugate by G, and sigma 1 so sigma 1 now becomes a representation of M2 by this conjugation by twisting with this conjugation, and that sigma 1 twisted by G must be isomorphic to sigma 2. So yeah. So basically what is sigma 1 G? So you have G M1, G inverse is M2. So you just take an element of M2, which is G M1 G inverse, and then you apply conjugation by G inverse. So that is what is sigma 1 G as a representation of M2. It just twisted by this automorphism. Okay. And now one can see that this condition that we have here, the conjugation by the element of G, is basically an equivalence relation on the set of pairs M comma sigma, where M is a Levy subgroup of a parabolic subgroup of G and sigma is a cuspidal representation of M. So this defines sort of an equivalence relation of what are the possible M's. They are basically conjugates to each other, and sigmas are basically transported via this conjugation. Okay, and if suppose a smooth representation pi occurs as a subquotient of the induced representation, where sigma is a supercuspidal representation of a Levy factor of p, then the equivalence class containing M comma sigma is called the cuspidal support of pi. Okay, so now given the category of given category of any representations of an abstract group, we want to get some sort of functorial decomposition of this category into irreducible subcategories which are indecomposable. So for example, if you're working over a finite group, then the subcategories are those representations which have all simple factors given by one single irreducible factor, right? So in order to do this, we must consider the fact that already there are some extensions provided by this factor of P. So one needs to somehow refine the notion of cuspidal support. So this is very hard equivalence relation. We need to make it slightly coarser. And this coarse definition is called the inertial support. So what is an inertial support? Inertial support is basically just extending this relation on these pairs by not just the isomorphism of this twisted representation, but you also have a character chi, which is the unramified character of M2. So what is an unramified character? So I'll explain it in the case of GLN. After all, in GLN, all these M's are product of several general linear groups. So therefore, it is enough to understand what it means for one general linear group. So any character of general linear group is given by the following character. So first you take the determinant and then you take a character of QP star here, this QP star, sorry for this. So an unramified character of GLN of QP is exactly for those characters such that chi of P is equals to identity. Okay. So basically you are looking at all those guys for which I'm sorry, here it should be chi ZP star. It should be identity on the ring of integers inside QP. I am extremely sorry for this. It's not P, it is the ZP star. So with that correction, let pi be an irreducible smooth representation contained inside an induced representation where sigma is a cuspidal representation of a Levy subgroup. Then the inertial class containing the pair M comma sigma is denoted by M comma sigma. So this is the inertial class, which is relaxed criterion of the equivalence relation. This is called the inertial support of pi. Okay. So Bernstein sort of proved an equivalence relation. Okay, let S be an inertial equivalence class and let MSG be the full subcategory of smooth representation whose irreducible subquotients have inertial support S. Remember, we have defined what is inertial support of a representation. Look at when pi occurs inside this induction and look at the inertial class containing this pair M comma sigma. Okay. Now the category of smooth representations admits the following decomposition into subcategories of the form MSG defined in the above point. So this is sort of an analog of isotypic decomposition for a group G. So it gives you a functorial decomposition of any irreducible representation pi into pi s, where this pi s belongs to this category ms of G. And there are no extension between pi s prime and pi s. Okay. So now let I be the inverse image of the upper triangular matrices in the map. So you look at upper triangular matrices here and take the inverse image under this obvious reduction map. And if suppose S is T comma identity, where in the case of G is GLN, T is just the diagonal matrices. So that is also a Levy subgroup, right? For the Borel subgroup, which is upper invertible upper triangular matrices. You look at this inertial class, and then Borel proved that pi has fixed points by this open compact subgroup if and only if this pi is inside this component. So in some sort, this theorem of Borel suggests that the cuspidal support of an irreducible smooth representation can be read from understanding its restriction to the compact open subgroup, which is in this particular case, it is the group, it is called the Ivahori subgroup, which is the inverse image of upper triangular matrices. So this began the study of understanding inertial support from the restriction to the compact open subgroups. Okay. So the following theorem, the above theorem of Borel is now known for many inertial classes of many p-adic reductive groups, although it's not yet complete, but large classes of groups are already considered. Large classes of reductive groups are already considered, and if you assume that P does not divide the order of the Weil group, etc., that is, so this analog of Borel's theorem is now known for all reductive groups. Now, what does this mean? So basically, there exists explicit construction of pairs Js and lambda s consisting of a compact open subgroup Js and a reducible smooth representation lambda s, such that for any irreducible smooth representation pi of G, this lambda s occurs inside pi if and only if pi is inside this category, this block. So such pairs Js and lambda s are called the types, and these types are explicitly constructed for GLN and for many other groups using techniques of Bushnell and Kutzko, and also a lot of variants of these constructions are now known. And often these constructions are rather explicit in nature, like there is some scheme of construction in one paper, there is another scheme of construction in some others, and if one wants to go between one construction to another construction, it is extremely complicated and it's very difficult to use such that means that there is no characterization of these pairs Js and lambdas. These are the pairs which satisfy some nice property. So for this reason, and then applications in number theory, it was required to construct types by fixing the subgroup Js to be the maximal compact subgroups. Okay, so this led to the theory of typical representations. So for example, let us take, since we want to build types for maximal compact subgroups, that immediately runs into problems. For example, if you take the identity T comma identity, an inertial equivalence class of GL2 of QP, the representations identity and the Steinberg representation both occur here. And if suppose K comma tau is a type for this block, then tau is necessarily identity because it must occur inside the identity representation. And using Iwasawa decomposition, which is this usual famous decomposition, we can see that the Steinberg representation has no trivial representation. There is no fixed points by the compact open maximal compact subgroup K. K here is the GL2 of ZP. Okay. In general, the example shows that there may not be any type of the form K comma tau in the above strict definition, that if pi contains lambda s if and only if pi is inside the block. So therefore, the following relaxation in the definition of type was suggested by Enya. So you look at an S in be an inertial class, an irreducible smooth representation tau of K is called an S-typical representation if only one way is true, that if suppose it occurs inside pi, then pi is inside MSG, not the other way around. So if pi is inside this, this inequality need not happen. So you are basically interested now in the S-typical representations of a compact open subgroup K. So given any type of an inertial class S of GLN, the GLN has a nice property that it has up to conjugation, it has a unique maximal compact subgroup. So therefore you can conjugate this JS inside K and you look at the induced representation. Now Frobenius reciprocity implies immediately that all these guys are S-typical representations of K. But now we can ask, are there any other examples of K-typical representations? So it is natural to ask for the classification of S-typical representation of K other than those constructed in this example. So then we are going to speak about some known results and some still problems which are open in this direction. So in the case of GLN of QP, we conjecture that any S-typical representation is a sub-representation of the induced representation. So this sort of gives some kind of legitimacy of what this lambda s, this construction of the pairs JS and lambda s are. So like there are many constructions, but yet when you induce to K, it satisfies a very simple property that it is an S-typical representation, which does not involve any explicit construction. So it's some kind of characterization of types. So a lot of substantial progress is already made, but the question still remains open. So what are known results in the case of GLN? So if F is a finite extension of QP, so are you people able to hear me? Can you guys?
Yes. Yes.
So let F be a finite extension of QP. Now I want to state my general result. So I will assume that F is a general local field, which just means that is a finite extension of QP or it's isomorphic to FP of T, where T is a variable. And let OF be the ring of integers of F. These are like the p-adic integers, and it has a unique maximal ideal PF. And I denote by var P of F the generator of PF. It's a principal ideal, and let you fix a generator. Let K be the group GLN of OF. Okay. So the classification of typical representation for all inertial classes of GL2 is due to Enya. So he proved even for the case P is 2, there are some discrepancy from the above conjecture. So this conjecture, so I should note that this conjecture holds true for all P not equals to 2. One can make a refinement of this conjecture for P is equal to 2 as well, but I'm not going to go into such technicalities. So Enya proved even for P is equals to 2. So I proved, assuming that the residue field, which is the quotient of the ring of integers modulo maximal ideal, if it has more than 3 elements, then I proved that any inertial class S of GL3 of F, an S-typical representation of K occurs as a sub-representation of this. So in my thesis, I also proved this statement for n equals to 4. And in most of the cases, there is one small case still remaining. So otherwise, this results are already also known for n equals to 3 and n equals to 4. But later, if suppose for inertial classes of the form S is GLN, F, so basically where you assume that the Levy subgroup is the whole group and sigma is the cuspidal representation, the typical representation, so this representation remains irreducible representation, and Pascunas showed that any S-typical representation is isomorphic to this induced representation, somehow showing that typical representations for cuspidal representations are unique. Okay, so let K1 be the group 1 plus var P times the n cross n matrices. Let S be any inertial class of GLN. Here M is allowed to be any Levy subgroup which can be product of smaller GLNs, not just the GLN of F. So you look at some inertial class S of the form sigma K1 intersection M is non-zero. This means that this sigma is sort of has fixed points by the intersection of this guy with the Levy subgroup. These are called the depth zero representations. Remember that if you put higher n's here, higher warp power k here, these forms a decreasing sequence of compact open subgroups, and then smooth representations are supposed to have fixed points. So we are looking basically at the topmost layer of smooth representations. So I proved that S-typical representations are sub-representations of this induction, and the structure of these representations is rather simple. It is somewhat like inflation of a parabolic induction of GLN of FP, and those representations are very highly studied by Howlett-Lehrer theory or by Lustig and so on. And in fact, in this case, it's just results of Ho. So in the classical groups, so I also proved some results beyond GLN. In the case of classical groups, the main problem comes with the conjugacy classes of maximal compact subgroup. In general, the conjugacy classes are not unique. So suppose in the case of SL2 of QP, SL2 QP, SL2 ZP, and this just a second. So these two are conjugate in these two compact subgroups as SL2ZP and T times the conjugation. They are conjugate obviously in GL2, but they are not conjugate inside SL2 of QP. So there are many classes of compact open subgroups. So you want to talk about S-typical representations of that compact open subgroup. Hello? Can you listen to me?
Yeah, you continue.
Yes.
So therefore, the non-uniqueness of maximal compact subgroup is a problem. So in general, S-typical representation for a general compact subgroup may not exist, unlike the case of GLN. But somehow, for G equals to SLN of F, when P does not divide N, it was showed, Peter Latham showed the analog of Pascunas' result. So in some cases, S-typical representations exist, and in some other maximal compact subgroups, it does not exist. So he proved completely that case. And Monica Nevins and Peter Latham extended to other classes of groups. And I proved that when G is a split classical group and K is a hyperspecial maximal compact subgroup, and S is a depth zero inertial class, which again says the same property, then I along with Amiya Mandal, we proved that all S-typical representations are sub-representations of this. And I make the following conjecture. So now let's come to some questions. So for general reductive group, so inertial class S, can one show the finiteness of S-typical representations? So even that is not known for a general case. That is quite interesting. So for any general split reductive group, take a hyperspecial maximal compact subgroup, assume the condition that it is of depth zero. Is the statement true? So this is one problem. And the question basically still pertains to exceptional groups. So that case is not known. All classical groups, GLN, I have proved it. So can we remove the hyperspecial condition, like this point is non-zero, and assume that depth zero case? So this is quite an interesting question. Snyder and Zink sort of say that given an irreducible smooth representation of GLN of F, which is tempered, then they show which representations of this compact induction occur in that tempered representation. And such analysis is not known for any class of groups. Even for SLN, one does not know the analog of this Snyder-Zink result. That means You take a tampered representation of the bigger group, you tell me which irreducible representations of this maximal compact subgroup occur in that guy. Okay, so these are some interesting questions, and especially the Schneider-Zink question is rather very interesting, and it has many interesting number theoretic applications. So I prepared some more slides for sketch of proofs, but then I don't seem to have time. But anyway, so the key proposition in all this argument is the following thing. So this, I'll give a problem and then stop it. So this is the most important problem if we want to prove any of these results. So this problem must be solved for exceptional groups. So let G be a finite reductive group and let P be a maximal parabolic subgroup which is not equals to G, and let sigma be a cuspidal representation of a Levy factor M. You look at a non-trivial unipotent element in the unipotent radical of P, and look at the stabilizer. M acts naturally on N is the normal subgroup. So look at MU, the M stabilizer of U. For any irreducible sub-representation Xi in the restriction of sigma to MU, you must construct an irreducible representation of M which is not equal to sigma, and such that this Xi occurs. So in other words, what you are saying is that the stabilizers of unipotent subgroups inside N cannot distinguish cuspidal representations together. So in fact, the problem should be true if you replace sigma prime, not any irreducible, but in fact a cuspidal representation. Two cuspidal representations cannot be distinguished by the restriction to the stabilizer of the an unipotent element. So this is a key proposition. So it's sort of a concrete problem. Even if you do not understand many things, this can be the concrete problem one can take away. So I'll stop here.
Thank you very much, Professor Santosh, for such a nice and well-organized talk. Now it's time for questions. So if anybody has any question, then he can unmute and ask the question directly. So anybody has any question, please ask. I think there are a few questions in the chat box. Okay. So if you can see.
Yeah, so these are probably clarification.
Yeah.
So Mihir asked me that an irreducible smooth representation occurs as a sub of a parabolic induction, sub-representation of a parabolic induction, not a quotient. So these two are equivalent things. So if something occurs as a quotient or a subquotient, you can change the parabolic subgroup by conjugation such that it occurs as a sub-representation. So these are equivalent. These are results of Castleman or even Bernstein, for example. So this is one question. What is T? T is the diagonal matrix. Okay, so yeah, there is no more questions.
If there is no other questions, then let us thank the speaker once again. So thank you, Professor Santosh, for such a nice talk. Thanks.
So I'm leaving now, or?
Yeah, you can now
unshare.
Yeah, unshare your. So our next speaker will be Mihir Sheth. So Mihir, are you there?
Yes.
So still we have some time. Maybe you can just share your slides and be ready. So we will meet at, we will start at 11. Okay.
Yeah.
Okay, so welcome back to the next session, which is contributory talks. So each talk is of 15 minutes. So in that session, our first speaker is Mihir Sheth. So Mihir, you are ready?
Yeah, I am ready.
Oh, still we have 2 minutes. So maybe we just wait for 2 minutes and then we will start. Okay, I guess we can start now. So let me welcome our next speaker, Mihir Sheth. He will talk to us on locally analytic representations and p-adic Langland's problem. Mihir,
Okay.
start.
Yeah, thank you very much. And thanks to organizers for giving me the opportunity to talk about my work in this symposium. So this is going to be an overview talk on the theory of locally analytic representations in the context of p-adic Langland's program. And in the end, I will mention my result from my PhD work, but most of the talk is an overview talk. Okay, so let's begin. So let K be a finite extension of QP, GK be the absolute Galois group of K, and WK be the Weil group of K. So the story begins with the local class field theory. So the local class field theory is a statement about um, connection between the local field K and its abelian extensions of K. So local class field theory gives a map from K cross to the abelianized Galois group, which induces isomorphism onto the abelianized Weil group. That means the Weil group modulo its uh, commutator subgroup. So this is a sort of um, uh, this is kind of a link between the abelian extensions of K and the data which is intrinsic to the field K itself. And so local Langland's correspondence is a generalization of this fact to higher dimensions. So from this isomorphism, we see that one-dimensional representations of the Weil group are in one-to-one correspondence with the smooth irreducible representations of K cross, right? That is GL1K. And this can be generalized to the higher dimensions. And then we have a so-called classical local Langland's correspondence. It's a one-to-one correspondence between certain n-dimensional representations of the Weil group K and smooth irreducible representations of GLN K. Now it's not just any correspondence, but it satisfies certain properties. In particular, this one-to-one correspondence is compatible with the local class field theory in the sense that on the right-hand side, if I look at the central character, it matches with the determinant character of these finite dimensional representations of the Weil group via this isomorphism. So this extends the local class field theory to higher dimensions. And also note that on both sides of this correspondence, I do not mention the underlying base field of the representations, because on both sides we consider smooth representations. Here I say certain n-dimensional representations, but they are basically smooth representations of the Weyl group. And here are also smooth representations of the general linear group. So the base field does not matter. But when we speak of Galois representations, which is a natural source for the Weyl group representations, the base field plays an important role. So over complex vector spaces, this classical local Lagrange correspondence restricts to continuous n-dimensional irreducible representations of the absolute Galois group, restricts to the correspondence between continuous n-dimensional irreducible representations of the absolute Galois group and smooth irreducible supercuspidal representations of the GLNK. We saw the definition of supercuspidal in the previous talk, so maybe audience might be familiar with this. Okay, so over complex vector spaces, we do have a sort of bijection between Galois representations and the representations of the general linear group. But if you look at the structure of this Galois group, which is the absolute Galois group of a local field, it has a closed subgroup, which is a pro-p group. The wild inertia group is a pro-p group, and therefore the complex representations of this GK do not give much information of this Galois group. So if we look at the continuous representations of this Galois group on p-adic vector spaces, so that means on vector spaces which have the same local topology as the absolute Galois group, then we will get more information of the Galois group itself. Okay, so do we have such a correspondence then over p-adic vector spaces? Unfortunately, over p-adic vector spaces, however, there are too many continuous Galois representations. That is understandable because, as I said, the topologies of this Galois group, topology of the Galois group GK and GLN of p-adic field are compatible. So there are too many continuous Galois representations. That means on the left-hand side, we need to have some sort of control on the left-hand side, as there are too many representations on the left-hand side. Or in other words, we need to enlarge the category on the right-hand side. So it is naive to consider any sort of p-adic correspondence with the right-hand side consisting of only smooth representations. We have to sort of look for other type of representations of the general linear group. Okay. Nevertheless, there is a p-adic analog or extension of the classical local Lagrange correspondence when n is equal to 2 and k equal to qp. And let's see what is this. So let rho be a absolutely irreducible crystalline representation of Hall state weights 0, k minus 1 over a p-adic field L. Okay, so here I am considering the representations of the absolute Galois group of QP over a two-dimensional representations over a p-adic field, that is some finite extension of QP. And as I mentioned, these representations have rich structure. So that is sort of described by these data that it is crystalline and Hall state weights 0, k minus 1. But you don't need to worry if you don't know these notions, but it is just some additional data associated with this p-adic Galois representation. And using this additional data, we now construct a GL2QP representation that is just the tensor product of the symmetric k minus 2 for representation of L2 and a smooth representation that comes from the classical local Lagrange correspondence. Now, since rho is a nice p-adic Galois representation, one can associate to rho a classical Weyl-Dirichlet representation. And by classical local Lagrange correspondence, it corresponds to some smooth representation of GL2QP. So this pi smooth is that Weyl group representation. And then we consider, not Weyl group representation, but it corresponds to Weyl group representation, pi smooth, under classical local Laurentz correspondence. And then we consider the tensor product of this pi smooth and symmetric power representation, and let's call this pi rho alg. And it's a fact that this GL2QP representation admits a unique Banach completion. So there is a GL2QP invariant norm on this pi rho alg, and the completion of this with respect to this GL2QP invariant norm is a Banach representation, which is also topologically irreducible, admissible, and unitary. And this gives a correspondence between, this is, so generalizing these two more general types of irreducible two-dimensional representations of GQP gives a correspondence which is over p-adic fields. So this is a p-adic local Laurentz correspondence, which is again a bijection between two types of representations. On left hand side, I have continuous irreducible two-dimensional representations of GQP over a p-adic field L, and on the right hand side, I have certain Banach space representations of GL2QP over p-adic field L. So this is an extension of the classical local Laurentz correspondence to p-adic fields, because you see the information coming from classical local Laurentz correspondence is already there in this p-adic Laurentz correspondence. So this sort of extends the classical local Laurentz correspondence. And the representation that we construct here from the data of the p-adic Galois representation is an instance of a locally analytic representations. So now I come to the definition of a locally analytic representation. So as the name suggests, it's a continuous representation of a p-adic Lie group G. So like GL2QP, for example, in this case, on a topological L vector space V is locally analytic if some open subgroup of G acts analytically on V. So that means if you look at the orbit map for each vector in V, if you look at the orbit map from G to V, which sends small g to small g acting on V, that orbit map is given by is analytic. I mean, you can make sense of analytic maps because it's a Lie group over p-adic fields. Okay. So what are examples of smooth locally analytic representations? So classical smooth representations of p-adic Lie groups are locally analytic because the orbit map is locally constant. Locally algebraic representations, here the orbit map, here G acts sort of algebraically. So of course it also acts as analytically. And this pi rho alg on the previous slide here, it's an example of a locally algebraic representation. It's a tensor product of algebraic representation with the smooth representation. So if my p-adic Lie group is a very nice group like the additive group ZP, so a compact and abelian group, then any continuous character, L-valued character, is in fact locally analytic. This is a theorem due to Amis. So this says that if my group is nice, then the locally analytic characters are sort of familiar objects. They are just continuous characters. Then there is a analog of principal series, parabolic induction of locally analytic representation, and then you can talk of principal series representation, and then you also have a locally analytic Steinberg representation, that is just the L-valued functions on the projective line modulo the constant functions, locally analytic functions. Yeah, I take. Now, it was observed by Morita that this locally analytic Steinberg representation is in fact isomorphic to something coming from geometry. And this is the representation realized on the topological dual vector space of the space of differential one forms on Drinfeld's upper half plane. Recall that Drinfeld's upper half space, so upper half plane is one-dimensional Drinfeld's upper half space. So in general, n-1 Drinfeld's upper half space is nothing but the projective space n-1 dimensional you consider the complement of all k rational hyperplanes in this n-1 dimension of projective space. Now, GLNK, of course, stabilizes this set of k rational hyperplanes, and therefore there is natural action on this Drinfeld superhalf space. The GLNK acts on this Drinfeld superhalf space, and therefore it acts on any equivariant vector bundles on this Y0, that is the Drinfeld superhalf space. And if you consider the global sections of such equivariant vector bundles, they gave sort of first geometric examples of locally analytic representation. So here we consider omega 1, capital omega 1. So it's the sheaf of 1 forms, and the global sections are basically the space of 1 forms on the Drinfeld superhalf space. All right. So this Drinfeld superhalf space Y0, there is a formal model of this. That's a formal scheme, and that formal scheme parameterizes deformations of certain p-divisible groups. So it's a deformation space, and then there is a space X0 which parameterizes deformations of the dual data to this data, which is parameterized by Y0. And this X0 is called the Lubin-Tate moduli space, and so it's sort of dual space to the Drinfeld superhalf space. And if you look geometrically, it is nothing but the open unit disk over a p-adic field of some dimension. So the poly disk even. Say. So let me explain the duality between Lubin-Tate space X0 and Drinfeld superhalf space Y0. So here I have considered some Galois covers of these spaces. So as I said, X0 and Y0, they are both deformation spaces of certain p-divisible groups, right? And if you consider torsion points of these fixed p-divisible group that these spaces deform, you get the covers, étal covers of these spaces. So these XM and YM are étal Galois covers of these X0 and Y0. X0 is the Lubin-Tate and Y0 is the Drinfeld superhalf space. And on X0, I have the action of the automorphism group of the p-divisible group that is being deformed, and that is isomorphic to the group of maximal order of the division algebra over K. And also on Y0, there is the automorphism group of the p-divisible group that is being deformed by Y0. And in this case, that automorphism group is isomorphic to the maximal compact subgroup of GLNK, the standard maximal compact. And the duality is reflected in this picture in the sense that if you look at these Galois covers, the Galois group here is in fact isomorphic to G0 mod GM, where GM is the mth principal congruent subgroup of this G0. And the Galois group on the Drinfeld superhalf space side is isomorphic to the J0 mod JM. Again, JM is the congruent subgroup in the maximal order of the division algebra. So, as I said, the equivariant vector bundles on the Drinfeld superhalf space and its étal covers gave rise to locally analytic geometric examples of locally analytic representations. So in my PhD thesis, I considered the problem whether equivariant vector bundles on Lubin-Tate space also gives rise to local analytic representations or not. And it is indeed true that it's a theorem due to my advisor and myself that the dual spaces of the, let's say, the structure sheaf of XM are local analytic representations of the J0, the automorphism group of the p-divisible group. And the local analytic representations coming from the Drinfeld superhalf space show up in the geometric realization of the p-adic local elements correspondence. So here their connection with the p-adic local elements program. But the
Excuse me, Mihir, hello. Yeah, just a request to finish it in 2 minutes because we are running out of time.
Yes, this is my last sentence.
Okay, sorry.
Yeah. So the locally analytic representations from these Drinfeld superhalf space do show up in the geometric realization of the p-adic local elements correspondence. And the relevance of those coming from the Lubin-Tate space to the p-adic local analysis program is yet to be discovered. And, so here are some references for the interested people. And thank you. Yeah.
Okay, let us thank Mihir for such a nice talk. If now it's time for some quick questions. If people have some questions, they can just unmute and ask the questions.
Hi, Mihir.
Hello. Hi.
So you have said that the Lubin-Tate tower, the representation of J0 is locally analytic, right?
Yeah, right.
So can we do slightly more by saying that is in fact rigid analytic or something like that?
Yeah, as in, yeah, one can think whether the action extends to the rigid analytic group and
Yeah,
group underlying the J0. That's what your question is, right?
right.
Yeah, so there is a student of Matthias Strauch who considered the rigid analytic action on this Lubin-Tate space, and he shows that. So as I said, this X0 is a like open disk of radius 1, right? He
Right.
says that on certain disk of radius strictly less than 1, the action of J0 in fact extends to the rigid analytic group, but not to the whole disk.
I see.
Yeah, that's what I know about this. But so
Yeah, thank you.
yeah.
Okay, so if there is no other questions, let us thank the speaker once again. Thank you, Mihir, for such a nice talk. So you can now close your slides. Yeah, stop sharing. Now our next speaker is Ravi Teja Vangala. So Ravi Teja, are you there?
Yes, ma'am, I'm there.
Yeah, so can you share your slides?
Yeah.
Okay. So Ravi Teja, are you ready?
Yeah, 1 minute. Just I will
sure.
turn on my video.
Yeah, please.
Yeah, I'm ready.
Okay, so our next speaker. Yeah.
Ravi Teja, can you go to the full screen mode?
Full screen.
Yeah.
Already. Yeah, it's already in full screen.
Okay.
Okay.
Okay, this will do. Yeah.
Okay, so let me introduce our next speaker is Ravi Teja Vangala. Can you go to the first slide?
Yeah, this is
The introduction slide. Title slide.
Yeah, this is the.
No, where the title of your slides is written. The title slide. This is page 1. Can you go to the page 0?
No, this is a static page. It's the title is in the.
So what is the title of your talk?
The
So
monomial.
where is the title written in your slide? So can you please go to that page?
Yeah, it's the monomial lattice and the reductions of Galois.
But yeah, I can understand. But please, can you go to that page? You just click the left arrow of your laptop.
Yeah. Yeah, I clicked the.
Okay. So he will talk to us on the monomial lattice and reductions of Galva representation.
Yeah.
So, Ravi Teja, you can start now.
Yeah. Thank you for the organizers for giving me opportunity to speak in this conference. Today, this talk is based on the joint work with Professor Eknath Ghate. So this talk will have some of the intersection with the already talk delivered by Ghate in this seminar. So let us begin. So let K be a field, P be a prime number, gamma be GL2K, which is invertible 2 by 2 matrices with entries in K, and gamma acts on K2, the usual action of matrices on the two-dimensional vector spaces K2. If you let VR denote the RH symmetric power representation of K2 comma gamma. So this will denote VR, and the field will change in our talk. So I'll make the field explicit whenever the field we are talking comes into picture. And VR has a model consisting of homogeneous polynomials of degree R in variables X and Y. And so with this explicit model, we can actually define the action of gamma on VR. So it's, you take any matrix A, B, C, D, act on the polynomial f of x, y. So the action just means that you need to substitute ax plus cy for x and bx plus dy for y. So this will denote the action, and we will work in this framework with the homogeneous polynomials of degree R and this action. This VR is very interesting, and it has a lot of interesting submodules and quotients. So one of the particular class which we are interested are the gamma modules generated by the monomials. So x r minus x subscript r minus I will denote the gamma module generated by the monomial x to the power r minus I y to the power I. So you take the k-linear combination of gamma dot x to the power r minus I y to the power I. So this will be the space x r minus I. And by monomial lattice, we mean the lattice of these gamma submodules x r minus I, where I varies from 0 to R. So monomial lattice in general consists of like what are the inclusion relations and what is the structure of individual modules and so on. So one example is when K is C, the complex numbers, it is known that the representation VR is irreducible. So all the monomial modules are equal to VR, and the structure is just VR. So there is nothing interesting in this case. So next interesting case which comes is when K is the algebraic closure of Fp, that is Fp bar. So in this case, Roti gave an elegant description of the monomial lattice. So this has already come up in the Professor Ghate's talk. So let me just say what it is. The sequence of zeros and ones one must carry while adding the base 3 expansion of r minus I and I is called the carry pattern of the monomial x to the power r minus I y to the power I.
I think slides are not moving. So can you, you are still in the
First,
second page of the slide, the preliminaries.
okay.
Yeah, maybe you can unshare and then again share it.
Yeah, okay.
It happened with other speakers also. Please try.
Yeah, okay. Share. Okay. So now it has come to third slide, right? It's fine now?
Yeah, it's case K equal to Fp bar.
Yeah. So
Okay.
yeah. So let me recall the definition. So the carry pattern of the monomial is just you add the base p extension of r minus I and I. So you'll get sequence of carries 0s and 1, that is called the carry pattern, and you just equip the set of all carry patterns with lexicographic ordering or the dictionary order. It's the same. So in this case, the Roti's result is following. So VR be the RH symmetric power representation of K2, and K is Fp bar in this case, and the monomial module xr minus j is contained in xr minus I if and only if the carry pattern of the monomial x to the power r minus j is less than or equal to carry pattern of x to the power r minus I y to the power I. So this is his first result, and the second result is that any gamma module of gamma submodule of VR is generated by monomial. So it will look of the form xr minus I plus xr minus j, so on. So it will be just sum of these monomial modules. So, and it is also stated in his result that this result is true even if you replace Fp bar by Fp, any finite field Fp per t, as long as R is strictly less than P2 per t. So these are the two cases. So next comes the case which we are interested. So that is K is equal to Fp. So in this case, actually Glover already studied the submodule, highest monomial module xr, which is generated by the monomial x to the power r. And the next second highest monomial module, which is xr minus 1, it is studied by Bhattacharya and Gate. So we actually try to study further monomial modules. So before that, we just set up some notations. For any positive number, sigma pr denote the sum of the digits in the base K extension of r. So you just take the base K extension of r and just add all the digits. And r naught denote the constant term in the base K extension of r. So r naught here is just the congruence class of r modulo p, and r naught lies between 0 and p minus 1. So this is just a fancy term saying this constant term. Basically, it's the congruence class of r modulo p. So first result we proved, this joint work with Professor Ghate. So it says that p be any prime greater than or equal to 2 and j comma I be any two integers between 0 and p minus 1 with j strictly less than r. And we assume that r is greater than or equal to p, then this monomial module xr minus j is always contained in xr minus I. But for the other inclusion to hold, that is these two monomial modules are equal, we need to have these two monomials should have the same carry pattern, and additional two conditions: summation of p-adic degrees of r minus j is less than or equal to p minus 1, and summation of p-adic degrees of r minus r naught is less than or equal to j. So this is some kind of generalization to Doty's work in K is called Fp bar, but it is in slight lesser in less generality, because I am restricting j and I between 0 and p minus 1. So just let me go back. So here the Doty's result, you have the first result, those two are equal if and only if the carry patterns are equal. But here we are saying that the carry pattern should be equal, and further two more conditions, this combinatorial data, these also should hold. So in some sense, this is some generalization of Doty's work to the case K is equal to Fp. So next, we actually determine the structure of these individual modules. As said earlier, this highest monomial module xr and xr minus 1 already studied earlier, but we did from 0 to p, and this actually agrees with the earlier results. Let D denote the determinant character of gamma, and so here actually we obtained the structure of xr minus I in all cases, but for the simplicity I'm just stating one result which is generic. Let p be any prime greater than or equal to 3 and I be between 0 and p minus 1. R is at least this number, and A prime denote the congruence class of R minus I modulo p minus 1, and A prime lies between 1 and p minus 1. If summation of p-adic degrees of R minus R naught is greater than or equal to p, then we have following exact sequence of gamma modules. So here you have the tensor product of these VRs. Actually, there's a formula of Klefsch-Gordon given by Glover. You can decompose this tensor product into direct sum of indecomposable modules. So this actually, you can explicitly write all the Jordan-Holder factors of xr minus I from this sequence. So the next result, so here I is between 1 and 0 and p minus 1. But next result is about when I is equal to p. So in this case, we had interesting observation. So let p be prime greater than or equal to 3 and r is greater than or equal to 2p plus 1. So for every positive number r, there exists another integer greater than or equal to 0, such that the monomial module xr minus p by to the power p, this monomial module generated by this monomial is same as the monomial module generated by x to the power s minus 1 times y. So this is somehow relating a module. This is actually contained in VR, RH symmetric power representation, and this is contained in SH symmetric power representation. So this is some kind of giving this. And one more point. So here S, you can actually specify in terms of R by comparing the summation of p-adic degrees of R minus P and summation of p-adic degrees of R minus 1. So this is the combinatorial data which determines S. So next we want to consider some interesting subquotients of VR. So let me define this. What are these quotients in VR? So for any n greater than or equal to 0, let VRn denote the set of all polynomials in VR which are divisible by x to the power p minus y, x y to the power p whole to the power n. So actually one can show that this is actually a gamma module, because one can check any matrix acting on this just without this power of n. You can show that it acts by the factor of determinant. So this is uses we are working in with FP. So let me denote the quotient Qi. So Qi is the quotient VR modulo xr minus I plus VR I plus 1. So this is a gamma module, and using some algebra one can show that this is same as the quotient VR mod VR I plus 1, quotient with xr minus I, quotient with xr minus I plus 1. So here xr minus I plus 1 is nothing but xr minus I intersected with VR I plus 1. And in Professor Ghate's talk, it was said that each of these individual quotients, they are periodic with respect to R with period p times p minus 1. So basically this quotient Qi is periodic with period p times p minus 1. So the structure of Q0 and Q1 was determined by Buzzard-G and Bhattacharya-Ghate. And we determine the structure of Qi when I is between 0 and p minus 1. Small notation, let m be any integer, then the square bracket of m is number between 1 to p minus 1 such that m is congruent to square bracket m modulo p minus 1. And A will denote the congruence class of R modulo p minus 1 with this notation. So we prove the following structure theorem regarding Qi. When I is neither A or nor p minus 1, and we have these numbers, so p is greater than 1 and I is between, and R is at least this number. As said, I is not A and p minus 1. J is minimum of I and A minus I. Then we have exact sequence of gamma modules. So 0, W, Qi, Qj minus 1, 0. And you can explicitly write down W, and this is actually a quotient, subquotient of Vrj modulo Vri plus 1. And you can write down this expression for W depending upon vanishing or non-vanishing of certain binomial coefficients which depend only on A, I and R. So these binomial coefficients you can write in terms of A, I and R. And in some cases, you additional to this vanishing of binomial coefficients or non-vanishing, you need to compare the two numbers A minus R naught and R naught. So let me tell you one thing which you can do. So assume that you know the structure of Q0, QA and QP minus 1. So I want to say how you can use this exact sequence to somehow like determine rough structure of Qi. So you take Qi, if I is A or p minus 1, you already know, or it is 0, you are no. But then from Qi, you go to Qj minus 1. So again for Qj minus 1, you can apply this theorem whenever j minus 1 is not A or p minus 1 or 0. And you can further up. So when j minus 1 is equal to 0, you already know the structure of Q0, and Qa, we assume that we know the structure. So using this exact sequence, you can determine Qi in all the cases. So here is some explicit description of W when in some cases. So when I is strictly less than A minus I, so here the minimum, J is actually the minimum. So it will be I here. And here it has two possibilities, and this occurs when this binomial coefficient is non-zero, and this occurs when this binomial coefficient is zero. And when I is equal to a minus I, then the minimum is same equal to I and a minus I, because these two numbers are equal, and W has four possibilities here. So here there is a non-vanishing of the binomial coefficient, and this is zero. And here it has four possibilities. So this is Vp minus 1 tensor determinative per I when R naught is I, and R naught is I minus 1. You have V0 tensor determinative per I, and it is VRI mod VRI plus 1 otherwise. When I is greater than a minus I, you have actually 5 possibilities, but here I am omitting 3 cases. Here the minimum is a minus I because we assume that I is strictly bigger than a minus I, and W is 0 if this binomial coefficient is non-zero, and it is equal to VR a minus I mod VRI plus 1 if this binomial coefficient is 0. Actually, if you go to the theorem, I wrote here the comparison between a minus R naught and R naught is needed. So that K comes up in the 3 omitted cases, which I have not mentioned here. So similar theorems can be proved when I is equal to A or I is equal to P minus 1. As I said, sketch little argument like how you can use from QI to QJ minus 1, how you can go and how you can find the structure of QI. So we use those ideas to list the complete Jordan-Holder factors of QI. But here I want to mention only particular consequence where I determine the cases when QI is irreducible. So we have following result. So all the assumptions are as in the previous theorem. P is at least 3. I is with any number between 1 and P minus 1. And A denotes the congruence class of R modulo P minus 1. And QI is irreducible in the following 3 cases. When I is a minus 1 and R is congruent to these numbers modulo P. And in this case, QI is actually isomorphic to Vp minus 1 minus a tensor determinative per A. And when I is A and R is congruent to A plus 1 till P minus 1 mod P, in this case QI is isomorphic to VA. And if I is P minus 1, then and A is 1 and P divides R. In the case we have QI is isomorphic to Vp minus 2 tensor determinative. So this result has a immediate number theoretic application. So this also has come up in previous talk. So it uses some local Lagrange correspondence and everything. So this is where the second title. So reductions of Galois representations come to the picture. So let me mention that result. So let VKAP be irreducible two-dimensional crystalline representation of absolute Galois group over QP, and it is defined over E, and it has Halstead weights 0 and K minus 1, and we assume the slope of which is the valuation of AP to be strictly positive. Let V bar KP denote the semi-simplification of the reaction of VKP modulo maximal radius M. So actually it's an open problem to determine the shape of V bar KP. So in various cases the shape of V bar KP is known. So we prove V bar KP is irreducible in following cases, and this is a new result. So V bar KP is irreducible if K minus 2 is congruent to A modulo P minus 1 and K minus 2 is congruent to these numbers modulo P, and slope, which is valuation of AP, lies in this interval. So in these cases, we prove that it is irreducible, and there is one more case, same assumptions, but here we assume that valuation of AP belongs to A and A plus 1, inter A and A plus 1, and A is between 1 and P minus 1, and A is not equal to P minus 2. So these are the two cases, and using mod P local Lagrange correspondence, p-adic local Lagrange correspondence, and result of buzzard G, we can actually determine the shape of V bar KP V bar Kp is isomorphic to induction omega 2 to the power a plus 1. Here omega 2 is the shared fundamental character of level 2. So these are the results we have proved, and these are the sum of the references. And I thank you for your attention.
Okay. Thank you, Ravi Teja, for such a nice talk. We don't have much time for question answers. So if you have any questions, maybe you can write to him, because we are already running out of time. But if you have some quick questions, then we can take. Anybody has any quick questions? Okay, if not, let us thank the speaker once again. Thank you, Ravi Teja. So you can unshare your screen. Now, our next speaker is Sujit Kumar Singh. So Sujit, are you there?
Yes, ma'am, I'm here.
So can you share your slides?
Yeah. Is it visible?
Yeah, it is fine.
Yeah.
Okay, so you have 15 minutes time, Sujit. So let me invite Sujit Kumar Singh from National Institute of Science, Education and Research. So he is going to talk to us on congruences in Hermitian Jacobi forms over Qi. Please, Sujit.
Thank you, ma'am. First of all, I would like to thank the organizer for giving me the opportunity to speak here.
Can you switch on your video? We can't see you.
Yeah, wait. Yeah, I've done it. Am I visible?
Yeah, it's fine.
Okay.
Yeah, you can now full screen your slides and start.
Yeah. So this is my joint work with Dr. Javan Meher, and in this presentation, I am going to discuss about UP congruences in Hermitian Jacobi form over Qi. This congruences has been already studied in modular form and Jacobi form, so I will start from modular form. So by H, we will be denoting the complex upper half plane. A modular form is a function from H to C, which satisfy the following two properties. The first is a modularity condition, and second is that it has a Fourier expansion of this form. So it's form a vector space over C, and we denote by currently following these notations that by Mk we denote modular form of weight K, and Mk are when collection of all the modular form which has a Fourier coefficient in R, where R is any ring R subset of C. Okay, so Ramanujan delta function, which is defined by this. So it's a modular form of weight 12, and it has Fourier coefficients in Z. Next, I define what is called UP congruence. So we will be taking P to be a prime and ZP to be the localization of Z at the prime ideal PZ. So if we have a modular form which has Fourier coefficient in ZP, we define the UP operator as by this way, means we take out those coefficients such that P divides N, and we say that F has a UP congruence if F/UP is congruent to 0 mod P. So this congruence means all these coefficients will be congruent to 0 mod PZP. PZP is the maximal ideal in this ZP ring. Okay. So I give some example of UP congruence. So we have delta/UP is congruent to 0 mod phi for this primes. So this was proved by Ramanujan in 1960, and for P equals to 2411 by Newman in 1972, and for this big prime by this Lygros and Rogier in 2010. And these are the only primes which are for P less than 10 to the power 10. such that delta slash UP is congruent to 0 mod P. Even this is a conjecture that there are infinitely many primes such that delta slash UP is congruent to 0 mod P. I will not be going for the conjecture, but I will discuss about some equivalent condition for the existence of UP congruence in modular form, and then in my case in Hermitian-Jacobi form. So next, so to give the equivalent condition, we uses the mod P theory. So this was proved by Swinnerton-Dyer. Suppose that we have two modular form, and they are congruence mod P, then their weight must be divisible by weight difference must be divisible by P minus 1. So the two modular form of different weight can be congruent mod P. So it's interesting to define the smallest weight modular form which has a congruent to a given. So we define for some bigger class. Suppose if f is any function which has a Fourier expansion of this form with the Fourier coefficients in Zp, and if f is congruent to some modular form of weight k, then we define the filtration to be the infimum of weights of all the modular form which are congruent to this f mod P. Okay. Next is a theta operator. Suppose we have a theta operator. Theta operator is defined like this, and if f is any modular form, then if we apply theta on this f, then it simply give the Fourier expansion of this form. Theta f is not a modular form, but Swinnerton-Dyer proved that this, if f is any modular form, then there exists a modular form of weight k plus p plus 1 such that theta f is congruent to g mod p. Now, since this theta f is congruent to g mod p, and the way we have defined this filtration, we can calculate the filtration of theta f. So, Swinnerton proved that that filtration of theta f is always less than equals to w of f plus p plus 1, and it has equality if p does not divide w of f. Ono used these two results, this result and this result, and give an equivalent condition for the existence of UP congruence. So the result says that if f is any modular form and f is not congruent to 0 mod p, if you take p to be greater than k, then f has UP congruence. This f has UP congruence. If we calculate the filtration of this thing, this theta p minus k plus 1, if it's equals p minus k plus 3, then f has a UP congruence. So it gave an equivalent condition for the existence of UP congruence in modular form. So next, similar results hold in the Jacobi form. So first I will give the definition of Jacobi form. A Jacobi form is a holomorphic function with matrix index m, from H cross Cl to C of weight k index m for the Jacobi group SL2G semi-direct product ZL cross ZL. If it satisfies the this is transformation with respect to the group SL2G, and second is that it has a lattice transformation with respect to ZL cross ZL, and third is that it has a Fourier expansion of this form. Okay. So I will be following this notation that by JKM gamma L, Jacobi form of weight k index m, and R when we put the collection of all the Jacobi form and the Fourier coefficients in R. Similar result in the case of Jacobi form with matrix index for UP congruence also have been proved, and for Ziegel modular form also this was proved by Martin Raum and Olive Caricta in 2015. And the main result which was needed to prove their result is a structure property. It says that suppose if phi is any Hermitian-Jacobi form, and if determinant of 2m is t, then there exist phi I Jacobi forms, phi I and modular forms such that phi can be written like this. And if psi is any another Jacobi form written in this form, and if they are congruent, so this results break down to fi is congruent to gi mod p. So any two congruence of Jacobi form, if they are congruent, then their corresponding fi must be fi congruent to gi mod p. So using these results, they have proved the result for similar result for Jacobi form with matrix index. Okay. We have proved UP congruence for Hermitian-Jacobi form over Qi. So I will first give definition of Hermitian-Jacobi form over Qi. So these are notations we will be following. We take gamma 0 to be to gamma O semi-direct O square, and this is the Jacobi group in the case of Hermitian Jacobi form. So it's a function from H cross C square to C, and it satisfies the, with respect to this group, it satisfies the modularity transformation, and it has a lattice transformation, and it has a Fourier expansion of this form. So we will be following this notation that by Sjkm delta, the space of Hermitian Jacobi form of weight k, index m, and parity delta, and by R, the collection of all the Hermitian Jacobi forms of weight k with all the Fourier coefficients in R. So similar to the case of modular form, we proved that if two Hermitian Jacobi form, if they are congruent, then their indices must be equal, and their weight will be divisible by weight difference must be divisible by p minus 1. Moreover, we have proved that if there is a collection of finite sum of Hermitian Jacobi form, and if they are congruent to 0 mod p, then for each conjugacy class, this class summation will be congruent to 0 mod p. So to prove this, we followed the similar method as we have in the case of Jacobi form. So this was not a big problem for us. Next, we defined the filtration as we have in the modular form. So suppose phi is any function from H cross C square to C, and it has a Fourier expansion of this form. And if phi is congruent to some Hermitian Jacobi form, then we define its filtration to be infimum of all the weights of modular form which are congruent to this phi. And similar to modular form, we have a heat operator in this case, and if we apply this heat operator on any Hermitian Jacobi form, then it all again give a Fourier expansion of this form. So next, as we have in the seen in the case of modular form, we needed to prove a similar result here for Hermitian Jacobi form, and this was the big problem for us to prove. And the proof of this theorem requires a structure property, as we have discussed in the case of Jacobi form. So this that structure property is not known in the case of Hermitian Jacobi form. And to overcome that problem, we consider a bigger class of Jacobi form. We consider the Jacobi group to be gamma 1 O, and Jacobi form for this space, this group satisfies all the condition of Hermitian Jacobi form with epsilon equals to 1. So there it was epsilon to be 1, minus 1, I, and minus I. So here we take only epsilon to be 1, and it satisfies all the condition of Hermitian Jacobi form. And moreover, the Hermitian Jacobi form, now it's become a subset of this bigger Jacobi group. And then we prove that this Jacobi space is isomorphic to Jacobi form with matrix index with M equals to this group as a vector space over C. And then we extract the structure property from here to this our vector space. And we prove the required result for this. And next, if you define the filtration for this space by suppose if phi is any function which has a Fourier expansion, and if phi is congruent to psi for some Jacobi form in this space, then if you define filtration for this space by W phi, then we prove that if phi is any Hermitian Jacobi form which is a subset of this, then we prove that these two filtration, this was filtration with respect to this space, and this is a filtration with respect to this space. So we have proved that these two are equal. And using this result, we have proved the required result in the case for which we were required. And then using these two results, we have proved the so first I will define what is UP congruence in this Hermitian Jacobi form. So if phi is any suppose Hermitian Jacobi form which has a Fourier expansion of this form, so Atkins UP operator on phi in this case we define by this way, that it takes out those coefficients such that p divides 4nm minus norm of r. So we say that phi is UP congruence if phi slash UP is congruent to 0 mod p. So we proved a similar result as we proved by Ono, that phi is any Hermitian Jacobi form, and if p is greater than k and p does not divide n, k greater than equals to 4, then phi has UP congruence if the filtration of this element is p plus 5 minus k. Okay, so Hermitian Jacobi form actually occurs as the Fourier Jacobi coefficients of Hermitian modular form. Hermitian modular form is has a Fourier expansion over Qi has a Fourier expansion given by this, and it has a Fourier Jacobi expansion. Any Hermitian modular form has a Fourier Jacobi expansion of this form. So this phi km is equals to this much, this Fourier expansion. And these phi kms are Hermitian Jacobi forms of weight k, index m, and for some parity delta belonging to plus and minus. So using this property of Hermitian modular form, we have proved a similar result of UP congruence in the case of Hermitian modular form of degree 2 over Qi also.
Sujit, okay. Okay, thank you, Sujit, for such a nice talk. Yeah. So if anybody has any question, please ask. If there is no questions, then we will thank the speaker. Thank you, Sujit. Okay, so I think our next session will start from 12:10. So we will have 10 minutes break. So I think we can meet again at 12:07. And our next speaker is Lalit Baishya. Are you there, Lalit?
Yes, ma'am. I can listen.
Okay.
Hello.
So maybe we can meet at 12:07, Lalit. And
yes,
then you can share your slides and we will start from 12:10.
Yes.
Okay?
Okay.
Okay. So see you at 12:07.
Hello.
Yes, is it Lalit?
Yes, yes.
Okay. Okay. We have you. Okay, that's great. But we'll meet at 12:07. Okay.
Yeah.
What happens 10? Professor Mundul will tell you to share your screen. Okay. Yeah. Just wait.
Okay, so welcome back. So Lalit, you are ready?
Lalit, first unmute yourself in order to speak. And now you can also turn on your video.
Yeah, Lalit, are you there?
Yes, ma'am. Can you hear me?
Yes,
Yeah,
yes.
we can hear you. Yeah, we can see your slides as well.
Okay.
So we have just 1 more minute. So let's wait for 1 minute. Be ready. I will tell you.
So my video just started. Yeah.
Okay.
Can you see me?
Yes, yes.
Okay, now it's time for our next talk. So let me invite Lalit Vaishya from Harishchandra Research Institute. He will be speaking on sign change of Fourier coefficients of normalized Hecke eigenforms at primitive binary quadratic forms of fixed discriminant. Okay, Lalit, we can start
Okay.
now.
Thank you, ma'am. And first of all, I would like to thank the organizers for giving me opportunity to speak here. So my title of the talk is sign change of the Fourier coefficients of Hecke eigenform at the primitive binary quadratic forms of the fixed discriminant. So here is my outlines of the presentation. So some history and basic things about the modular forms and the main results, and then a brief proof. So the sign change problem is one of the interesting problem in number theory, which has been studied by many authors. And there are the many results which deal with the quantitative results, such as the number of signs for the sequence of the Fourier coefficients. So when you consider the subsequence of the Fourier coefficients, then the problem becomes more difficult. So uh, we assume let f be an Hecke eigenform. So normalized means that the first Fourier coefficients lambda f1 is 1, and this normalized means we have removed this n to the power k minus 1 by 2 from the Fourier coefficients. So in 1985, this Ramurthy have studied the sign change property for the subsequence at the prime numbers. Precisely, he considered that lambda fp where p runs over all the primes. And in 2013, Knopp, Conan, and Wilkinson shows that if the Fourier coefficients of the cusp forms are reals, then there are they changes the sign infinitely often. And in 2013, Jaban Meher, Kashi Vishwanath, and Karamdev Shankar studied the problem for subsequence lambda f n to the power j, where he considered j equal to 2, 3, and 4. And in 2014, Conan and Martin shows that if you consider the subsequence lambda fp to the power jn, then there are infinitely many sign changes for almost all the primes p and natural number j. So recently, Somaru Banerjee and Manish Kumar Pandey considered the similar problem for the sign changes for the subsequences, which are the sum of two squares. And precisely, he proved that there are infinitely many sign changes. So if k is an even integer and f is a normalized Hecke eigenform for the full modular group of weight k, then the sequence lambda f c square plus t square have infinitely many sign changes. And he proved that in the interval x to 2x, the subsequence lambda f c square plus d square have at least x to the 1 over 8 minus 2 epsilon many sign changes. So we have considered, we'll show that the theorem can be improved And this method, whatever this Somirup Banerjee and Manish Kumar Pandey have used, can be extended to prove more general results for the positive definite binary quadratic forms. So let Qx denotes a primitive integral binary quadratic form defined as a ax square plus bx1 x2 plus c square, where this a, b, c are the integers with co-primality condition and with the fixed discriminant d, which is defined as a b square minus 4ac, and which is negative because q is a positive definite. We have considered q to be the positive definite quadratic forms. And we know that the generating function theta q defined by uh, summation of all the tuples in z square q to the power qx, uh, which is, if you write the Fourier expansion, it becomes rqn q to the power n, where rqn denotes the number of representations of n by the quadratic forms qx. So we know that this theta qx is a modular form of weight 1 for the level gamma 0 mod d and the character chi d. This character is defined by the Jacobi symbol, which is the extension of Legendre symbol, and precisely the formula for RQN given explicitly in terms of the character, which is given by WD times the summation over the divisors chi d over d, and WD is a constant according to as d. And we will see from the formula that this RQN does not depend on the choice of A, B, C, but it depends only on the discriminant. So now we'll start some little bit about the modular form. So let SKL chi denote the space of cusp form of weight k for the congruent subgroup gamma 0L with Dirichlet's character psi, and F is an AK eigenform, a normalized AK eigenform in the space SKL chi with this Fourier expansion. So this normalized means this lambda f1 is 1, and this lambda fn, we call it the nth normalized Fourier coefficients of f. And precisely this lambda f satisfies this recursive relation due to Hecke, which says that lambda fm into lambda fn is equal to summation over d dividing d divisors over the GCD of m and n psi d lambda f m square mn divided over d square. So whenever m and n are co-primes, the coefficients are multiplicative. So precisely this lambda fn satisfies this Stieling's bound, and we'll assume that the Fourier coefficients of reals, because uh, uh, it is not necessary that the Fourier coefficients lambda fn's are always real. So with this assumption that the lambda fn coefficients are real, we'll prove our results, which state that if f is an Hecke eigenform and the Fourier coefficients of real, then the sequence lambda f qx, this is a binary quadratic forms defined earlier, then this subsequence has infinitely many sign changes. And precisely we prove that in this interval, at least x to the power 1 by 5 minus 2 epsilon, many sign changes. So to study the behavior of sign changes, we need to consider the following two sums, two partial sums S1 and S2, defined over lambda f q by qx, where x represents all the tuples and up to x. So this sum, we can write it as a lambda f rqn. So if you write n equal to this one, then this lambda n repeats rqn times. So similarly S2. And this rqn is the number of representations of n by qx. So it is enough to consider the upper bound for S1 and the approximate behavior of S2. So precisely we'll prove the following proposition, which state that S1 has the upper bound of order big O of x to the power 3 by 4 plus epsilon, and S2 have the approximate behavior, which is c times x plus big O of x to the power 3 by 4 plus epsilon. And this c constant is positive and depends on the cusp form f, epsilon, and d. So to prove this proposition, we'll use the truncated parents formula, which uses the which relates with this partial sum with the L function. So we'll define the following Dirichlet series RF theta q, which is defined as a lambda fn rqn over n to the power s, and this appears in the Rankine-Selberg convolution. And this is we define another Dirichlet series, and we'll decompose these Dirichlet series into the known L functions. So precisely we'll prove the following lemma, which relates this Dirichlet series RF theta and RS with these known L functions. And PS is given by the PS, and this US is given by the Euler product, which converges for real part of S bigger than half. So to prove this proposition, to prove this proposition, we'll use the following key ingredients. The first one is truncated Perron's formula, and then the convexity bounds for L functions, and the integral moments of the Rankine-Selberg L functions. So this is the truncated Perron's formula, which relates the Dirichlet series and the partial sum. State that under certain conditions, this partial sum is equal to 1 over 2 pi I, the integral from b minus it to b plus it ds over x to the s plus over s ds, and the big O things. So whenever this an satisfies the Ramanujan-Petersen conjecture, that is the big O of n to the power n, then this factor dominates over this one. So precisely we'll have this truncated Perron's formula. And we'll use these two key lemmas, which is the convexity bound and the mean square estimates for the Rankine-Selberg L functions, to prove our results. So this convexity bound says that if you have any L functions of degree d, and then s minus 1 over s plus 1 to the power r lf sigma plus it is of order 3 plus sigma plus it to the power d times 1 minus sigma by 2 plus epsilon. And this R denotes the order of pole at s equal to 1. So if L is the entire function, then R will be 0. So, and this lemma due to Matsumoto, which state that if f is an Hecke eigenform, sorry, this will be Hecke eigenform, then the mean square estimates is given by the following estimates. So now we'll state prove this proposition. We know that this the D-Links bound for lambda fn is which says that this lambda fn is a big O of n to the power epsilon by 6, and this Rqn is the Fourier coefficients of modular form, so it satisfied the Weyl bond. So together this we can have the order of an. So this says that this an is a big has the order big O of n to the power epsilon. So we can take b to be 1 plus epsilon and apply the truncated Perron's formula. So after applying the truncated Perron's formula, we will shift the line of integration from 1 plus epsilon to 1 by 2 plus epsilon, and then apply the Cauchy's theorem, and then the estimates for the L functions, and convexity bound for this convexity bound for the L functions to get the estimates for this S1 and S2. So to prove the results on the sign changes, precisely we'll use this key lemma, which is due to Ramamurthy and Jaban Meher, which says that if an is the sequence of real number which satisfied following three conditions, that an is a big O of n to the alpha, and the partial sum n up to x an is big O of x to the power beta, and the square of the partial sum is c times x plus big O of x to the gamma. Then if you choose delta bigger than alpha plus beta and gamma, then the sequence an has at least one sign change in this interval, and precisely in the interval x to 2x we have x to the power 1 minus delta sign changes. So since we have the estimates we have the estimates for S1 and S2, which is big O of 3 by 4 plus epsilon, and C the estimates for S2 is a C times x plus big O of x to the 3 by 4 plus epsilon, So we can choose the maximum of this epsilon plus 3 by 4 plus epsilon, the number bigger than this epsilon plus this one. So precisely we'll choose delta to be 4 by 5 plus 2 epsilon, and we'll use this lemma, and so that in this interval we have at least one sign changes, and precisely in the interval x to 2x we can have at least x to the power 1 over 5, that is 1 minus this 4 by 5 plus 2 epsilon, which is 1 over 5 minus 2 epsilon sign changes. These are the references that I have used to prove the results. Thank you. Hello.
Yeah. Thank you, Lalit, for such a nice talk. Any questions? Okay, if there is no questions, then thanks the speaker once again. Thank you, Lalit.
Thank you, ma'am. Should I stop this hearing? Can I stop this
Yeah,
video?
you can unshare your screen now. Yeah, so our next speaker is Pasupulati Sunil Kumar. Are you there? Sunil Kumar?
Yeah, I'm there. Can you hear me?
Yeah, your voice is very low. Can you increase the volume a little bit?
Yeah, sure. Now?
It's better.
Okay, maybe I will increase it a little more. Can you share my screen?
Yeah, please share your slides.
Can you see my slides?
Yeah, you can see. You can make it full screen.
Sure.
Yeah, it's fine. Still, we have 4 minutes. So we will wait for 4 minutes and then we will start.
Yeah, sure.
Hello, Sunil.
Yes, ma'am.
From the audience, it says still your voice is low. Can you little bit increase it?
Is there any change? Is it better now? Volume button.
still it is low. If you can increase little bit more, it will be good. If you have some earphone or something, then you can use that. That might help.
Is it better now?
Yeah, I think it's better now.
Okay, thank you. Yes, now.
Okay, can you switch on your video if it's okay with you? Yeah.
Okay.
Okay, now it's time. So let me invite our last speaker of the morning session, Mr. Sunil Kumar Pasupulati. So he is from ISAR Trivandrum, and he will talk to us on the p-divisibility of class numbers of an infinite family of imaginary quadratic fields q root d and q root d plus 1. Please, Sunil, you can start now.
Thank you, ma'am. First, I would like to thank organizers for the opportunity. And this is a joint work with Lakshmi Krishnamurthy.
We can't hear you properly.
So this is joint work with Lakshmi Krishnamurthy. Is it okay, sir?
No.
No. Okay. Maybe. How about this?
So can't you talk without the headphone?
Yeah, I think maybe I'll try that. How about this, sir?
Is it okay, Professor? I don't.
Oh, I can't hear you. How about this?
I think this is better. No?
Let's try. Yeah.
Okay, so let's get started. So this. Okay. Can you see my screen?
Yes.
Yeah, fine. Okay, this is my plan. Actually, my talk has two parts. One part I'll be constructing infinite family of quadratic fields whose class number is divisibility. The other
it has again become very low.
I think maybe then. Okay, I'll maybe speak a little louder, and that would be okay.
Yeah.
The second part I'll be constructing a pair of quadratic fields whose class number is the q root d and q root d plus 1 whose class number is divisible by 3. So first I'll introduce some notations and definitions. The K is number field, the finite extension of Q. OK is a numbering of K, integral closure of Z in K. And CLK is a class group of K. Actually, if you consider set of all fractional ideals of K, that is finitely generated modules of OK contained in K, with a binary operation as ideal multiplication, it forms a group, and set of all principal fraction ideals forms a subgroup of it. And you consider the quotient. This quotient is a class group of number field K.
and actually it is well celebrated. Result is that the class group is finite abelian group, and the order of this class group is defined to be class number of K. Okay. So the number the n I defined to be norm on number field K, which is actually is a product of all Galois conjugates of an element. So it's very immediate from the definition is that if class number is 1, if and only if OK is p-adic. And the ideal class group is actually the most basic and mysterious object in the algebraic number theory. The ideal class group is one of the most the complete list of imaginary quadratic fields with the class number 1 is given by q root k, where k is one of them. And whereas for a real quadratic field there is no such list exists, but Gauss has conjectured that there exists infinitely many quadratic fields whose class number is 1, but it's still a conjecture. So understanding the class numbers, people have started looking at the divisibility of class numbers so that they'll understand the structure of a class group in the number fields. So even covalence heuristic predicts that the positive portion of imaginary quadratic fields, quadratic number fields, have a class number divisible by n. So it has been supported by several mathematicians, proving that there exists infinitely many quadratic fields whose class number is divisible by n for any n. So for example, there is a Nagel, Ankni, Chawla, and Grass and such people. So many people have shown interest in the families like q root of 1 minus mu x power n, where mu is equal to 1, 2, 3, 4. So we look at some of this kind of families first, and so Gross and Rolovich has proved that n greater than or equal to 3, where n is a prime. They have proved the class number of q adjoint 1 minus 4 u power n is divisible by n. Even Stephen Lobotin has extended this result for any odd n. He is proving that q adjoint 1 minus 4, class number of q adjoint 1 minus 4 u power n, where u greater than 2 is divisible by n for any odd n. Okay, this theorem will come handy in one of the outros. And for n mu is equal to 1 case, Ramurthy has proved that whenever u power n minus 1 is a square root integer, he has proved that q adjoint 1 minus u power n is the class number of q adjoint 1 minus u power n is divisible by n for n. So now we will be looking at case mu is equal to 2. Recently, Azihul and Kalyan Chakraborty has proved that the class number of q adjoint 1 minus 2 m power 3 is divisible by 3 for any odd integer n greater than 3. So we generalize this result and prove that whenever m is an odd prime power and p is any prime number, p is any odd prime, we'll prove that, and also the q adjoint root of 1 minus 2 m power p is not equal to qi. Then the class number of q adjoint 1 minus 2 m power p is divisible by p. The condition that I have here is that q adjoint 1 minus 2 m power p is not equal to qi. Is just that I am making sure that 2 m power p minus 1 is not a square. Okay. So once the similar problem, one of other interesting problem was looking at pair of quadratic forms whose class number is divisible by a particular number. So in the same spread, the Izuka has proved that in 2018 there exists infinite family of pairs of quadratic imaginary fields q root t and q root t plus 1 whose class number is divisible by 3. So he also conjectured, based on this theorem, he has also conjectured that for any prime p and a positive integer n, there exists infinitely many n plus 1 successive real or imaginary quadratic fields q root t plus 1, q root t plus n, where t belongs to n, which the class numbers are divisible by p. So here I'll be actually proving Izuka's conjecture for n is equal to 1. So this is what like for any odd prime p greater than or equal to 3, there exists a infinite family of pairs of quadratic fields q root t and q root t plus 1, where t belongs to Z, whose class number is divisible. This is what I'll be proving it first, and then later on I'll put my main theorem one. So before getting into the proof of this theorem, we'll just check the infiniteness of of the family that I gave in the main theorem 1. So what I want to if I consider set of all m such that p divides the class number of 1 minus root of 1 minus 2 m power p. So if m to be in this yes, this should not be root of this should not satisfy this equation for any y. But we know that by Siegel theorem, this particular equation has only finitely many solutions. So S contains all odd powers but finitely many. All but finitely many odd powers. So this implies that the family that we have proved in the theorem 1 is actually infinite family, and now we'll get to construct. Now we'll construct a consecutive integers t and d plus 1 such that p divides the class q root d and q root d plus 1. Okay. So by main theorem 1, we know that p divides the class number of this. But this thing can be also written as this. It's just I'm sending 4 inside and taking power p. It is just the same as this. And okay, let's keep this aside and then look at. Now let's take u is equal to 2n power p minus 1, and now apply Stephen Lobotian result that I have stated in the starting. It gives me that p divides the class number of q adjoint root of 1 minus 4 u power p. So now we look at, but let's look at what is this q adjoint 1 minus 4 u power p. If you look at this is actually comes out to be something like this. And now choosing d is equal to 4 into 1 minus 2 m power p whole power p, we actually have that the prime p divides the class number of q root d and q root d plus 1. Okay. This proves the main theorem 2, and now here I'm just left with proving the main theorem 1, which is constructing an infinite family whose class number is divisible. Okay. Let's look at that. The proof of main theorem 1. So let's say d is a coefficient part of 1 minus 2 n power p with a signature. Then k is equal to q root. With a set k is equal to q root. So idea of this proof is actually we construct an ideal I such that I power p is going to be a principal ideal, and then we'll show that I can't be the principal ideal. So p divides the order of a class group, which means p divides the class number. That's what the idea is. So let me consider alpha to be 1 plus root of 1 minus 2 m power p. Then the norm of alpha is equal to 2 m power p. And also consider so since norm of alpha is 2 m power p, then the only primes that divide alpha that appear in the factorization of alpha will be the prime that lie above 2 and the primes that lie above p. Sorry, m. That is actually, since m is a prime power, like if you consider it is a prime power of q, then the only prime that appear in the factorization of alpha will be the primes that lie over 2 and the prime that lie over 3. Okay. Since d is congruent to 3 mod 4, the ideal 2 is ramified, so there exists an ideal p in OK such that ideal generated by 2 is actually equal to p square. Okay. So now, as I said, we'll write the since I said the only primes that lie over that appear in the factorization of alpha will be p and q. So like if factorization of alpha will be if it is like p into q power t, then look at norm of alpha, that norm of ideal alpha it comes out to be 2 into q power t. But see, observe that see, now we have it is actually 2 q power t is equal to 2 m power p. I can write r. So p divides t. So now set an ideal I is equal to p into q power t by p. Okay. So now look at the power of this ideal I that comes out to be a principal ideal. Okay. So now my aim is to prove that this ideal, I will prove that this ideal I is not a principal ideal. Okay, if suppose this ideal is supposed to be in principal ideal, then what happens? If I is a principal ideal, then beta power p is equal to ideal generated by 2 power p minus 1 by 2 into alpha. Okay. So since I was already assumed this k is not equal to q of I, and also since d is congruent to 3 mod 4, so this also can't be equal to q adjoint minus 3. So the only roots of k are 1 comma minus 1. So this implies I is not a principal ideal if this is not a power of a p. Because if this happens to be principal ideal, then what happens? Then I'll have that p minus 1 by 2 of alpha is equal to plus or minus beta power 2. So if I had to prove that p is not a principal ideal, it is enough to prove that plus or minus 2 p minus 1 by 2 alpha is not a pth power of any algebraic integer in OK. It's enough. Okay. So the next lemma will show you that this is not a pth power. So this will now I'm just left with proving this 2 into plus or minus 2 power p minus 1 by 2 alpha is not a pth power in OK. Okay. Let's proceed next. So the proposition, this proposition, the same conditions as the main theorem. Now I will prove that plus or minus 2 power p minus 1 by 2 alpha is not a pth power. Okay. So observe that minus 2 power p minus 1 by 2 alpha is a pth power if and only plus means 2 power p minus 1 by 2 alpha is a pth power. So now with this I'll say it's enough to prove that 2 power p minus 1 by 2 alpha is not a pth power. Okay. Suppose it's a pth power of some algebraic integer beta. Okay. Then we apply binomial theorem on one side, and one side we'll just see what we'll substitute what alpha is, and then combining the constant terms, we'll have 2 power p minus 1 by 2 is equal to this. So, but observe that a appears in every term in this summation. So we take a out, and this will imply that 2 power p a divides 2 power p minus 1 by 2. Okay. So there are two cases we'll consider. One is a is even. Later I'll deal with a is an odd case. Okay. So if a is even, then substituting this, looking at equation 1 that was, and then applying norms on both sides, I'll have 2 m power p is equal to a square minus b square d whole power. So since I know that a is even, 2 divides a and 2 divides 2m, so 2 divides b square d as well. So this implies, since d happens to be the square part of 1 minus 2 m power p, which is odd number, so d is also odd. So 2 divides b. Okay. So now 2 divides b and 2 divides a, so 4 divides a square and b square, which implies 4 divides 2m, which means 4 divides 2m, which means 2 divides m, but m we have taken is odd power, which is not a which contradicts the assumption that a is even. Suppose now let's consider the case a is odd. If a is odd and a also divides 2 power, which means a actually plus or minus 1. Now putting this into equation 3, which is something which looks like this, and then again applying the norm on both sides, we'll have 2 m power p is equal to 1 minus b square d whole power p. Okay. We just rewrite this equation like considering taking capital D is equal to minus d and m as a like power of prime q, will have 1 plus db square is equal to 2m to 2 q power r. And as I said in the starting, since 1 minus 2 m power p is equal to 1, this d we have taken to be square root part of 1 minus 2 m power p, which means I can write 1 minus 2 m power p is equal to some beta dash b dash square into d. Okay, just again taking minus d is equal to capital D and replacing this, I'll have 1 plus b dash square d is equal to 2m 2 q r square. Okay, these two equations imply that b comma r and b dash comma rp are solutions of 1 plus x square d. Okay, maybe I'll just change the slide. That would be more better. Okay. these two equations will give me it shows that they are actually there is two solutions for dx square plus 1 is equal to 2q power y. But actually this lemma is simple consequence of results of Sore and Bugard, where it says that for any odd prime q, an integer d greater than 3, the equation dx square plus 1 is equal to 2q power y has at most one solution. But so whatever the cases, then when a is r, we could get two solutions for this equation, which is a contradiction. So this plus or minus 2p power p minus 1 by 2 alpha is not a p covering, okay, which proves our main theorem. I will not be giving the proof of this lemma, but that is simple consequence. These are my references. This is a paper where the results of the dependent equation I took it. And thank you.
Thank you, Sunil. So if you have any questions from the audience, please ask.
Yes, I have a question.
Yeah, please.
Yeah, Sunil, can you please go back to the slide where you have referred to the result of Lobotin?
Yeah, sure. Yeah. Chekra, can you just...
Yeah. No, yeah, this one.
Yeah.
So actually Lobotin has proved that for k any odd number. So I hope you are aware of the result of Ankeny and Chawla that gives us that for any given integer k, there are infinitely many imaginary quadratic fields with class number divisible by k.
Yeah.
Yeah, so you can just take those elements as u.
Yeah.
And consider q square root minus 4u to the power k.
Yeah,
Then that would be basically q square root minus u.
Exactly, yeah.
So my point is that you have made use of Lobotin's result to prove the particular case of Izuka's conjecture. So that actually gets followed from Lobotin's result in just one shot, I guess, if I am not wrong.
Yes, it does. Like it's kind of I can say, yeah, it does. Similar.
Yeah, I could follow that you have used Azizul Haq and Kalyan Chakraborty's result to get a new family of fields whose class number is divisible by k, and then you manipulated with that.
Yeah.
That gives you a different family altogether. But
Exactly.
This particular case of Izuka's result is being followed from Lobotin's.
Exactly, yeah.
Okay. Yeah, that's all I had to say.
Yeah, thank you.
Yeah, thanks.
Any other questions from the audience? If there is no other questions, then...
I posted on chat.
Okay, posted on chat.
The class numbers have applications to the problem of equiangular lines. And the work by Appleby, Bengtson, etc. And there is an expository article, very elementary level, 1804.08100. It is mine with Shiva Kumar and Chatterjee.
I'll look at it. Thank you.
Thank you. Does the speaker have any applications to tell us?
Application, I haven't looked at any of these applications.
Okay, fine. Thank you.
Okay. Are there any other questions? Okay. If not, then we can thank the speaker once again. Thank you, Sunil.
Yeah.
Okay, so with this, I will conclude the morning session. And I would like to thank all the speakers and especially once again, thank all the organizers for this nice arrangement of the conference. And I hope that every year you can continue this type of initiative.
Yeah, Professor Moshmi Mondal, we want to thank you for being chair of this session and organizing this session quite well.
Thank you.
So I have given a feedback form link in this chat. So I request everyone to fill this up, as this is the last day of the symposium. We need to hear the feedback from all the participants. It's available in the chat. Okay.
Okay. Thank you. Bye.
Bye.
Okay.
Yeah, Dr. Suparna, you can share your screen, maybe.
Okay.
Let's check.
Yeah, okay.
Is it visible? Is it visible
Yes,
properly?
I can
Yeah.
see. Yes.
And audio is also fine, right? I hope there's no disturbance.
No, audio is fine. So welcome everyone to the post-lunch session of this BMF 2020, and we have Professor Gupta.
Hello, I'm not able to hear you, sir.
We can't hear you, Shan.
Yeah, there's some problem with your audio.
Shan, can you repeat?
Hello, I'm not able to hear you.
We can't hear you, Shan.
Yeah.
So, Shayanda, can you please introduce the chair once?
Can you hear me?
Yes, now I can hear you, but you have to talk a bit louder.
Okay.
Okay.
We have Professor Beth Prakash Gupta from JNU as the chair. So over to you, Beth.
Yeah, thank you, Sayan, and welcome to this afternoon session of the conference. And today it's the last session on the symposium on analysis and PDs. And today we have one invited speaker, namely Dr. Suparna Sen from University of Kolkata. Her research area is basically harmonic analysis, and she focuses mainly on Lie groups. And today she is going to talk on around theorems of Ingham, Paley, Wiener, Levinson, and Borel regarding decay of Fourier transforms. So, Professor Sen, over to you.
Okay, thank you very much for your kind introduction. And firstly, I would like to thank the organizers for inviting me to give this survey talk. And also kudos to them that they have organized such a nice conference at such a big scale. So thanks a lot for this too.
So I would like to state in the beginning that my talk is going to be very much at the basic level. So if there are any experts, my apologies to them. So since this is going to be a survey talk, I would like to pitch it at very basic, starting from very basic. I will not talk too much about technicalities. I'll just mention which result has been done. So yeah, as you've seen in the title, it's going to be on these classical theorems of Ingham, Pelli-Wiener, Levinson, and Boiling regarding decay of Fourier transform. So let me first start with the definition of Fourier transform. Okay, so for a L1 function, as all of you know, that the Fourier transform is defined in this way. And also, if f hat is also in L1, then we can also get back the function from the Fourier transform in a similar way by the inversion formula. So we all know this, and this sort of gives a duality between the function and the Fourier transform especially on Rn. This may not happen for all groups, etc. On Rn, we have this property. Now, this will be used very much in our versions of uncertainty principle. Now, what is an uncertainty principle? An uncertainty principle is, in general, can be described as a result which tells you that a function and a Fourier transform cannot both simultaneously be small. Now, what is small? You can define several notions of smallness. So one wants to optimize that to get a result of uncertainty principle. Okay. So, for example, one notion of smallness can be some decay at infinity. You can impose some decay on either the function or the Fourier transform at infinity. How rapidly is the question? That is what we want to know. And for example, on the other, you can impose some vanishing condition. Okay. So on how large a set, again, that is subjective. Okay. So let me start with a very elementary uncertainty principle. Okay. So let's start with the function f in L1R. And let us assume that its Fourier transform has a decay of this form, that its modulus is bounded by some constant times e to the power minus a mod psi for some positive number a. Now, notice that this already imposes a L1 condition on f hat. Okay, so we know the inversion holds. Now, in the inversion formula, instead of x, if you put x plus iy, we can see that this formula is actually, this quantity is actually finite when you have if the Fourier transform satisfies this estimate, if you have mod y to be less than a. Okay, and for all x, of course. And and using Morera's theorem, you can get that this f actually extends as a holomorphic function to this strip. So where this strip of mod y less than a, which contains a real line. Okay. Now, since f is a holomorphic function, so of course it cannot vanish on any large set. So it cannot vanish in particular on even a set of positive Lebesgue measure. Okay. So even if it vanishes on a set of positive Lebesgue measure, we know that f will have to be 0 because it's a holomorphic function. So this can be considered as a very elementary form of an uncertainty principle. Now, the question that was asked is, what if we replace this a mod psi by a function? Okay. So we want to replace this a mod psi by another function. So we consider some general locally integrable function psi, say on non-negative real numbers, which also takes non-negative values. And we want to ask whether there exists a non-zero f in L1, vanishing probably on a set of positive Lebesgue measures such that f hat satisfies this condition. So we are replacing this condition, this a mod psi, by a general function psi. Okay. And in this estimate, and we are asking whether f can vanish on a set of positive Lebesgue measure, or maybe other sets like open sets and all. That is what so the classical theorems I'll describe at first. So I'll describe the classical theorems of Ingham, Pelli-Wiener, and Levinson on R. These were done around in the 1930s. So I will describe it in a unified sort of way. Okay, in a describe them in together at one place. So we consider a psi, again a locally integrable function, and we consider this integral. This integral will be important. Okay, So I call this integral I equal to 1 to infinity psi over xi square. Okay, so remember this integral. And we will consider a function f in LP. So we can define the Fourier transform of L1 functions, and yeah, this is standard theory. We can also define the Fourier transform of LP functions between 1 and 2. So for those functions, we assume, for that Fourier transform, we assume this decay for almost every xi with this psi. Now, so first I'll state the result of Pelley-Wiener, because I would like to state Ingham and Levinson together. So Pelley-Wiener's result says that if such a function f vanishes on a half line, so on one side of a point x naught in R, and this integral is infinite, then we can prove that f is 0. Okay, Pelley-Wiener proved this. And also the converse is true. If this integral is finite, then actually there exists a non-zero f in L2. So one can construct a non-zero f such that which vanishes on a half line like this, and also which satisfies this estimate. Okay, so Pelley-Wiener proved this. I will go into what was used in the proof and all after stating the theorems. Okay, so let me state the theorems first. So this is Pelley-Wiener's result, and so here note that Pelley-Wiener did not use any extra condition on psi. For them, psi was just a locally integrable function. Ingham and Levinson both imposed some extra conditions on psi. So Ingham actually took psi of the form like this. Psi is like theta into xi, where theta xi into xi, where theta is actually a decreasing function which goes to 0 at infinity. Okay, so Ingham took a function psi like this and proved a similar result, but he proved actually what the version which I'm stating here is not exactly what occurred in the original papers. These are versions which can be easily derived from the original papers. Okay, for example, Ingham's result also, when he stated in his original paper, it was for a compactly supported function. But using his techniques, whatever he used, and a simple convolution argument, one can easily get this much stronger version. The stronger version is this: that if f vanishes on a non-empty open set in R on any open interval, say, and the integral is infinite, integral that I described, then f is 0. And conversely, if the integral is finite, then given any positive number, so this positive number is anything. So you can actually construct a function compactly supported in any interval minus AA. So since this A is general, you can take this support to be as small or as big as you want, okay, satisfying the decay condition. So this is Ingham's result, and in Levinson's result also the conclusion is similar, okay, but the condition on psi is different. Psi is an increasing function here, and the conclusion is similar again, that if f vanishes on a non-empty open set and the integral is finite, f is 0, and conversely again, if the integral is infinite here, I mean, and conversely, if the integral is finite, then one can construct such a compactly supported continuous function supported on any interval like this, and satisfying such that the Fourier transform satisfies this estimate. Now, these are the classical results. So by Ingham, Pelley-Wiener, and Levinson. Now I would like to state the classical result by Boiling. What Boiling did was, Boiling actually generalized Levinson's result. Okay, so and he did it for a measure. So for a complex measure also, you can define the Fourier transform in a similar way. And then we have this result that if psi is an increasing function satisfying this integral to be finite, and mu is a complex measure which satisfies such a condition. Now note that this condition is the L1 version of the condition we had on f hat. So here, if you look at the condition on f hat, so if you take e to the power psi this side, f hat e to the power psi, so has a sort of L infinity condition here. Okay, so instead of that, instead of f hat, we are assuming, Boiling is assuming that it's for a measure, and he's giving the vanishing condition on the Fourier transform side. Okay, so here e to the power psi with respect to measure satisfies a sort of L1 condition. Then if you assume that the Fourier transform vanishes on a set such that here, yeah, this is a bit more general than again what Boiling originally stated. Sorry. So here we can actually say that if this mu hat vanishes on a set capital lambda, where capital lambda closure is a set of positive measures. So as you can very well understand, this also includes sets of zero Lebesgue measure. So if capital lambda is a set of zero Lebesgue measure, but its closure is a set of positive Lebesgue measure, even that will do. This is actually very easy to see because mu hat is continuous. So if mu hat vanishes on lambda, it has to vanish on lambda closure. So that will give it. So there's nothing much difficult in that, but it actually generalizes this a lot. So then also you can conclude that mu is 0. So note that Boyling's result is much more general from Levinson's. So it's a direct generalization that can be told, because Levinson's he had assumed that the function vanishes on a set of on an open set, whereas here we're talking about a set of positive Lebesgue measure, and that to its closure is of positive Lebesgue measure. Okay. So these were the classical results. I'll first give, I'll keep on giving references in between so that it's easier to follow. So Pelley-Wiener's result actually appeared in this paper and also in his book, this famous book. And Inham's result appeared in this paper. So these are all, as you can see, the dates 33, 34. And Levinson's result appeared in this paper, as well as it also appears in his book. Hello? Is there a problem?
Excuse me, who is that? Please mute yourself.
Okay. Okay. So Levinson's results appeared here, and Boyling's, actually we could not find the original paper. We could only find this book where his result is there. It is also contained in Cousis's book. Cousis is a very nice book called Logarithmic Integrals. I'll come to that book later in my talk. Okay, so these are the original references of these classical results on R, which we have talked about. Okay. Now let's go to so I'll just say something about the proofs. So what Inham used, basic ingredients of the proofs. Okay. So what Inham used was, so there's this concept of quasi-analytic functions, and there's this classical Denjoy-Kalaman theorem which characterizes quasi-analytic functions. So Inham basically used this to prove his result. Okay. Now this theme of quasi-analyticity actually occurs recurringly in all these results. I'll tell you how. So Inham directly used this Denjoy-Kalaman theorem. What Pelley-Wiener did was they used some complex analytic techniques. So because they assumed functions vanishing on one half line. So you know, if a function vanishes on a half line, its Fourier transform will have an holomorphic extension to half space. So they used that holomorphic extension and used some complex analytic techniques. But here, what is interesting in terms of quasi-analyticity is that in their book also, they have referred to this result, which is of an uncertainty principle, I should say. It's in a different form in their book, and what I've stated is in an equivalent form. But they have called it the fundamental theorem of quasi-analyticity, and they have used it to actually prove again Denjoy-Kalaman theorem. Okay. So what they've mentioned is that for Denjoy-Kalaman theorem, because it characterizes quasi-analyticity, so these functions, which are essentially non-zero functions but vanishing on a half line, these are essentially non-quasi-analytic functions. Okay. So in that way, they have connected. So next is Levinson. What Levinson did was, Levinson took functions in L1R and used a certain transformation to convert them into functions which vanish on a half line, and then he applied Pelley-Wiener's result. Now the problem with this is, problem while generalizing this to Rn is that this technique is very difficult to generalize in Rn. So there's an alternative proof of Levinson's theorem available in Cousis's book, for example. So which is this thing will be very important again in the later part of my talk also after this, that using some completeness of exponentials in certain nonlinear space of continuous functions, using this density of this exponential type of function in this space, we can prove Levinson's result. Okay, so this actually was used in proving Rn, the analog on Rn. I'll come to that later. So the last is Boyling's theorem. What he used was he used some contour integrals and a result called the theorem on two constants, and he involved harmonic measure into the picture. Okay, so this theorem on two constants is basically a kind of fragment Lindelof type result involving harmonic measure. So using this concept of harmonic measure, he could generalize this vanishing type set much into a set of positive Lebesgue measure. Now here also, how is it related to quasi-analyticity? Boiling also in his original, in his book, for example, we have seen he has used these concepts to prove a result regarding quasi-analyticity, but his quasi-analyticity is a little different from Denjo-Carleman's sense of quasi-analyticity. So his is more general than this. So he defines the notion of quasi-analyticity and uses and actually proves a result on that and this uncertainty principle type result comes as a corollary of that quasi-analyticity result in his paper. But the methods used are this, and so it is directly proved in Cousis's book. Okay, so using this. So let me give the okay. So no, before giving the references, I just like to speak a bit about this problem because this is a separate problem of interest of completeness of exponentials. So this is called weighted approximation result of exponentials. I'll call it WAP in general. So whenever I refer to this, so let us assume that psi is an increasing function and we assume that it blows up at infinity. Okay, it goes to infinity at x goes to infinity. Now we consider this space of continuous functions on Rn. This is my notation for continuous functions, and this is C psi, where f by e to the power psi, this quantity goes to 0 at infinity. And we can define a norm here as a supremum norm. So as you can realize, it is like a weighted space of C0. C0 is continuous functions vanishing at infinity. So with a weight here, modulo this weight, it is like C0. So in fact, this is isometrically isomorphic to C0. And the norm is also given in this way with the supremum norm. Now what we do is, we consider any subset of Rn and we consider the span of the exponentials where this lambda is coming from this capital lambda set, and exponentials are of course these functions. E lambda x is defined by e to the power minus I lambda x here. So we consider we define phi lambda to be the span of all these e lambdas where lambda is coming from this capital lambda. Now what is this weighted approximation problem? It asks this question that for which subsets capital lambda is this space phi lambda dense in the given space C psi. You can assume some more conditions on psi if you want. For example, you can the integral condition which I have already mentioned, that you can assume the integral to be infinite and all that. So for that, when does this set phi lambda become dense in C psi? Okay, so this sort of problems constitute weighted approximation problem. There are also various other versions. I'm just talking about one version here. So this is related to that problem. That's why I mentioned here. And I'll now state the references, and we'll come back to this later and how it was used and all later. So yeah, a very nice introduction to quasi-analytic functions and Denjo-Carleman theorem is available here. Rubin's real and complex analysis, and it is also a simple proof is also available in Cohen's paper. And this is Cousis's book I was talking about. This contains this exponential density result, exponential density way of proving Levinson's theorem, as well as Boyling's theorem and all these things. So, and this exponential density kind of result, if anyone is interested in, there are some references here. This paper by Digiu and this by Paul Tarasky. So one can look at this if one is interested in this kind of a problem. Okay. So now let me go to the versions on Rn. Now So in order to prove the versions on Rn, what we do is we consider a psi function again from 0 infinity to 0 infinity, and again consider this integral. And again here we consider some f in LP with p between 1 and 2. And here the general version which have been proved now is for f hat e to the power psi to have a LQ type of estimate. Remember, we had talked about L infinity kind of estimate and L1 kind of estimate. This actually can satisfy a LQ type of estimate with q between 1 infinity and also and n is any positive real number, and also for q equal to infinity. So this was the first version that was proved, and later this was generalized to any q. So for q equal to infinity, this condition looks like this. Okay, so f hat e to the power psi by some polynomial is in L infinity, that sort of a condition. Okay, so for p, where p is any polynomial. So if you assume such a condition on f and f hat, okay, so then we have Pelley-Wiener, Levinson, and Inham's result. So Pelley-Wiener's result, what we assume is that f is supported in a half space. So on one side of a hyperplane, okay. So if f is supported instead of a half line, we assume that it is supported in a half space. Then if I is infinity, then f is 0. That is the result. I'm stating the one side of the result first. Converse, I can state it together. Inham's result again of a similar type. Psi is taken to be of this type at theta into xi, where theta is a decreasing function going to 0 as I going to infinity. Then again, if f vanishes on non-empty open set, then the integral is infinite, then f is 0. And again, Pelley-Wiener's Levinson's result is also for psi increasing, and f vanishes on a non-empty open set, and I infinity, then f is 0. So these were the generalizations done for Rn. And the converse for all of this is also true. So if I is finite, one can actually construct and given any positive a. So there we had an interval minus AA, and here we have a ball. So this is my notation for a ball centered at the origin of radius a. Now one can actually construct a function in CC infinity supported in this ball as small or as big as you want, satisfying these estimates to this estimate 2 if q is between 1 and infinity and not including infinity, and this estimate if q is equal to infinity. Okay, so let me mention, for Inham's you have to assume that size of this type. For Levinson also you have to assume size of increasing type of Levinson type, and for Pelley-Wiener you can assume either of these. Okay, so either size of the Inham type or of the Levinson type, then the same result actually works as a converse. So because once it's compactly supported, of course it vanishes on a non-empty open set as in Inham on Levinson, or it vanishes on a half space as in Pelley-Wiener. Okay, so this is the version of Inham, Pelley-Wiener, and Levinson's theorem on Rn. And we also have a version of Boyling's theorem on Rn. So for that, we first need a definition. So for the definition, we first note that we would define a set of positive rectangle type. So first we note that an open set U inside Rn, this will always contain a set of this product form. Okay, so any open set, inside any open set, you can find such a product of open sets U1 cross U2 cross Qn. Okay, where each of these is open in R. And this is actually an important tool while using, actually Levinson's result on Rn was proved by this exponential density result, and for extending the exponential density result from R to Rn, this is an important tool. And Boiling is also proved by the same technique. But unfortunately, this is not true for sets of positive Lebesgue measure. Okay, so if you take a set U, say, of positive Lebesgue measure inside Rn, you may not have a product set of this type. An easy example is, if you suppose in R2, if you take unit square and if you take out the rational diagonals, then that will give you a set of positive measure which does not have a product set of this type. So we have to incorporate this into the definition so that this method works. So that is the reason why we define capital lambda to be inside Rn to be a set of positive rectangle type if there exists lambda 1, lambda 2, lambda n inside R such that their product is inside this capital lambda. Okay, and here, as we have seen in Boyle's theorem, we can assume that this lambda, each lambda j closure has positive Lebesgue measure. That is enough. Okay, so this is what we mean by a set of positive rectangle type, and this is the reason behind it. Now let's define state Boyle's theorem on Rn. So here we assume psi again, a function like this. Or we also need continuity on psi because we want to, as I told you with C naught, we have to establish a relation between C psi and C naught, and that's why we need psi to be continuous there. And here we take this integral as usual, and we assume that mu is a complex Borel measure which satisfies the condition same as in Boyle's theorem on R. And we see that if mu hat vanishes on a set of positive rectangle type and the integral is infinite, then mu is 0. Okay, so this kind of theorem could be established, and also the converse is true. If I is finite, then also there exists a non-trivial measure which satisfies this estimate and such that mu hat vanishes on a set of positive rectangle type. Yeah, so this is the result of Boyle's theorem on Rn. So now let me go a little bit into the just idea of what has been used in the proofs. So in case of Inham, Levinson and Pelli-Wiener, as I've already told you, the first it was done for one case and then it was later generalized for any Q. So actually for any Q, by some convolution techniques, actually you can reduce it to one case and then prove that one case. Okay, so I'll just tell you what was involved. For Inham's version, remember for Inham's version on R, Dane-Jock-Alleman theorem was used on R, which was available on R. Thankfully, a several variable version of Dane-Jock-Alleman was available on Rn, which is due to Bochner-Taylor. And also, so this was used, and also the notion of radon transform was used to establish a connection between Rn functions on Fourier transform between Rn and R. And so these methods were used for Inham. For Pelli-Wiener, what was done was everything could be reduced to the one-dimensional case. Okay, the support is in the half space using the nature of the Fourier transform, the explicit expression of that. Things could be reduced to the one-dimensional case. This was relatively easier. For Levinson's, so WAP, remember we have denoted weighted approximation problem by WAP. So for Levinson, there was a weighted approximation result for open sets, which was generalized, open sets in R, which was generalized to open sets in Rn. There are some standard techniques to do that. So that was generalized in that way, and that was used to prove the Levinson's result on Rn. And for Boiling, the interesting thing happened was, till now we know, as in even in Cousis's book and everything, we know that this weighted approximation result was can be used to prove such uncertainty type results. Okay. For Boiling, what happened? We did not have a weighted approximation result for a set of positive Lebesgue measure, unlike the open set version. So interestingly, this is very interesting to note, is that we could obtain such a result using Boiling's original result on R. So Boiling's original result on R gives us a weighted approximation result for a set of, not really a set of positive Lebesgue measure, but a set whose closure is of positive Lebesgue measure. So we could, such a weighted approximation result could be proved. And again, this was generalized to Rn for positive rectangle type. This is why we need positive rectangle type for this extension. By the standard methods. So we have a weighted approximation result for sets of this type. And this in turn again will give us a Boiling's result, the Boiling's result on Rn that we have already stated. So the interesting point here is that previously we knew that this weighted approximation actually implies this uncertainty type results. Here we could also sort of establish the converse. So it sort of establishes a equivalence between the weighted approximation kind of results and Boiling's result here in this case, so an uncertainty type result. Okay, so this point is very interesting and can be explored further, and this is certainly a point which can be explored further. Okay, so these are the basic ideas of proofs, and let me just give the references here. So Bochner-Taylor's analog, several variable analog of Denjoy-Kleiman theorem is available here. And yeah, the results on Rn for Ingham, Levinson, Pelley-Wiener initially appeared in this paper. This is for the L infinity kind of decay, and the later Q decay, LQ kind of decay is here in this paper. It's an archive. I've given the link. And the Boiling's result is contained here, and this also contains this exponential density result, as I have already mentioned in this paper. This is also in archive now. Okay, so these are the reference to the papers in Rn. So now let me go to, so this is more or less the story on Rn. Now, this has been, so this is where it started, and after that, it has been also generalized to many other spaces. So I'll talk about them one by one. So first, let me start with Pelley-Wiener's theorem. So for Pelley-Wiener's theorem, it was done for two-step nilpotent Lie groups. It is in this paper itself, this initial paper, Bulletin Science Mathematics paper. Now here, it could be done on two-step nilpotent Lie group. This is just by reducing it to the result on Rn. Okay. Then it could also be generalized to any nilpotent Lie group, not only two-step, but for continuous compactly supported functions. This is again in this paper in this, which is in archive, improved Ingham type result, and on connected, simply connected nilpotent Lie groups. Okay. So these are the results on nilpotent Lie groups. As I have already told you, I'm not going into the details or technicalities of this. I'm just mentioning what has been done where. So, and there are some results on Euclidean motion group where again continuous compactly supported functions are considered, and also on semi-simple Lie groups with finite center and arbitrary rank. So here the notion was basically the decay on the Hilbert-Schmidt operator, so looking at the Fourier transform, the Hilbert-Schmidt norm of the Fourier transform. So if you have a decay on that, that gives a decay on the matrix coefficients, and that allows us to use a complex analytic result related to this, and that gives a proof. So after this, actually, it was done in Damac-Ricci spaces for functions supported on one side of a horocycle. Now, remember, Pelley-Wiener's theorem is about functions supported on one side. So one side of a, so in case of R, it's one side of a point, which is a half line. In case of Rn, it's one side of a hyperplane, which is a half space. So here in symmetric spaces, actually, you have an analog of such a thing of a hyperplane is given by horocycle. So you can consider, one can consider functions supported on one side of a horocycle, and then this was proved here for Damac-Ricci spaces. Now the references are here. The this paper on RNTN and two-step nilpotent. This I've already mentioned. Yeah, the Euclidean motion group and initial semi-simple Lie group result is here, and yeah, this in this you have this horocycle on one side of a horocycle result on Damac-Ricci spaces. Okay. So, and yeah, the nilpotent Lie group result is also here. This is mentioned. Yeah. So these are the more or less analogs of Pelley-Wiener's theorem. Now let's go to Ingham. So for Ingham, actually, we also have a version on torus. So remember, torus is compact, we know. So for Ingham, we were assuming functions vanishing on an open set. But for Pelley-Wiener, it was like 1/2. So in torus, we don't know what is a 1/2 of a space. So that was not there. So this is also was in the first paper for torus. So we have Ingham and Levinson on torus, but not Pelley-Wiener. So torus is there. And also in the first paper only this two-step nilpotent is also there. This is again by reducing it to the result on Rn. And in this semi-simple Lie group first paper, there was a version proved for bi-k invariant functions for non-compact complex semi-simple Lie groups. Okay, so this was done by using some explicit form of the spherical functions, but later this was much more generalized by recently. So where what happened was, so Dane-Jock-Kleiman, I've already mentioned about Dane-Jock-Kleiman theorem. Now Chernoff had proved the L2 version of Dane-Jock-Kleiman theorem using iterates of Laplacian. So that could be used, and actually both Inham's result and Chernoff's result, both of these results could be extended to Riemannian symmetric spaces of non-compact type in general. And also it could be proved that Inham's theorem actually follows from that of Chernoff's theorem. Okay, so this actually generalized the result in much more in the context of symmetric spaces. So the references are here. This is an initial first semi-simple Lie group paper. This is Chernoff's paper where he proves that version of for quasi-analyticity, and the one in which these results have been extended is here. It is in archive, available in archive. Okay, so these are the analogs of Inham's result. Now let's come to the analogs of Levinson's result. So again on torus and two-step, it was done in the first paper, and it has also been done for Riemannian symmetric space of non-compact type recently. And there is also a version of local Levinson theorem for compact symmetric spaces. So here in this Riemannian symmetric spaces of non-compact type, here also a kind of exponential density was used in the proof. Okay, and for this compact symmetric spaces, duality with non-compact symmetric spaces, that concept was used. Okay, but this is only a local kind of a Levinson theorem for functions in a small ball. Okay, so these actually appear in these two papers. So the Levinson's theorem for Riemannian, so this Riemannian symmetric space of non-compact type appear here. It's in IMRN already, I think online, published online. One has the DOI, and local Levinson theorem for compact symmetric spaces, that has also been published in Journal of Lie Theory. So this, as well as now, and yeah, Boyle's theorem, we have an analog on torus. The difference of the proof of this with the origin, this Inham, Levinson and Pelli-Wiener on torus was that there we could reduce Rn's, reduce the torus proof, so explore the connection of functions on torus with functions on Rn, and reduce it to the Rn proof. But here one had to run the whole exponential density kind of argument and equivalence with that. That whole argument had to be run for torus. And also there is a version for two-step MW groups. It is not in archive yet. And these, yeah, so this for Rn and torus, it appears in this paper, the Boyle's theorem. It's already in archive, one can see that. Okay, so lastly, yeah, so these are more or less the analogs of these theorems here. Lastly, let me see if I have few more minutes, I hope. So I'll just mention that there's also a relation with Schrodinger equations. Okay, so the thing is, there's this unique continuation property of solutions to Schrodinger equation one can look at. So one can consider the Schrodinger equation of this form. And so it is known that if, say, f is in L2, then there exists a unique solution of this, of continuous, which is a continuous function on R, taking values in L2 in the sense of distribution. And the aim is to obtain some sufficient conditions such that if you know the values of W at t equal to 0 and t equal to t naught, then you'll have that W is 0. So this kind of problem actually can be connected with an uncertainty type of problem that is already known. So this is also a related problem. So in some of these papers, I'm not mentioning this in detail, but in some of these papers that I have already mentioned, these uniqueness properties also studied. And in general, these uniqueness properties have been studied. I'll just give some references in these papers. This Esquariza, Koenig, Pons, Vega, this paper, and Chanillo's paper with respect to complex semisimple Lie groups. Angela Pascal and Sundari had also studied in terms of Riemann symmetric spaces of non-compact type. And Thangvelusser and others, Wenku and others studied this for H-type groups. And this was also done by Ludwig and Müller for two-step nilpotent Lie groups. So here in all of these papers, this relation is studied well. So one can also look at these. Okay, so yeah, I think I have finished. Thank you.
Yeah, thank you, Dr. Sen. And I think we can take some questions. We have about 12 or 13 minutes left before the next talk. Organizers, did you get some questions through some channel?
Not yet.
Not yet.
Okay,
Not
so I think here itself we can allow people, if they want to ask questions, they can unmute and
Yes.
ask questions. So one by one, I don't see any raised hand or anything. So
okay.
So I have a question. So Parna,
Yes.
this is
Yes.
Gautam.
Hello, sir. Nice
Hello.
to see you.
Good to see you too. Could you just go back to the slide where you were talking about, you mentioned working out the exponential density property for the n-dimensional torus Tn.
Yes.
You just made a, you said this is not yet in preprint form. You're working.
Oh, this is in preprint form. The torus is in preprint form.
Okay.
Only the two-step one is not.
Okay.
It is in archive.
All right.
Yes. So you just wanted to know about the preprint, or there is?
No, the question was, you said that some aspect of the proof cannot involve reducing to the problem, to the analog of the Berling theorem on Rn. So what exactly is the obstruction? You see, normally one expects things to be simpler for the torus, but you seem to mention an obstruction relating to the exponential density thing. So what is the nature of the obstruction that you actually have to do it ab initio on the n torus?
Actually, the thing is, in these reductions and all, there are some convolution techniques used. Okay. So what happens if a function vanishes on an open set using this convolution technique? So if you convolve with a function which vanishes on a which is supported on a very small set, then the resulting convolution, so f star g will then vanish on a, you can make it such small that f star g will vanish on a on another open set. But again, here Boiling type result is for functions vanishing on a set of positive measure. So this convolution technique does not work.
I see. Okay.
That is the obstruction, main obstruction.
I see. Okay.
So one
this is
has to run the initial thing.
So this is an obstacle analogous to how you cannot just use a convolution argument on the classical Ingham result, because what you stated is a little stronger than the Ingham result. And generally one uses a convolution type argument to sort of spread out a support, right?
Right.
But for Berling's theorem, one cannot go from Ingham to Berling in any which way. So is this a sort of analogous difficulty?
No. See, Ingham's for Ingham also the function is supported on a or vanishes on a open set. Okay.
Yeah.
So there you can actually use a convolution.
Yeah, that's what I'm saying. There you can. But
for
you cannot prove an Ingham type result and in any way, shape, or form go to Berling from there. So
yes,
is this a similar sort of difficulty?
that is difficult. Yeah, actually, boiling can be thought of as a generalization of Levinson because the condition, because psi is increasing, that is what is assumed.
Right.
It is not really a generalization of Ingham because psi is different. Okay. So that is why boiling is sort of considered as a generalization of Levinson. But anyway, the main difference is in boiling, we assume, that function vanishing on a set of positive measure, and there this convolution technique does not form. That's a main difficulty here. So for Ingham and Levinson, many times these generalizations are done. This convolution technique is a very important tool used here, which is not applicable for functions vanishing on a positive Lebesgue measure set. That is the problem.
Yeah. Thank you.
Yeah, you're welcome, sir.
Yeah, we can take a few more questions. We
Yeah,
have
sure.
another 10 minutes, So if somebody else is willing to ask a
I'll-
question, please raise your hand, and then we can go ahead.
I don't
Yeah,
know
so
where
I think
should be.
Professor Ajit Iqbal Singh
Yes.
wants to ask something.
Yes, I
Yes,
listened.
Go ahead. Yeah.
I listened to a talk by Laura D. Carley on CUNY group of seminars, and she was talking about replacing certain parts of basis by another part, and also there is Curry's work on subsets A, for which the exponentials form a complete system and things like that.
Yes. This is actually a very well studied problem. That is what I mean. There are lots of references. I just gave two such references.
I know.
It is a extremely well studied problem, and there are so many different versions.
Right.
So this is interesting that there is a relation between this uncertainty kind of problem and them. Actually, there is an equivalence. That is what is very interesting.
Right.
Yes.
So and I'm in touch with Laura D. Carley.
Okay. Okay.
Thank you.
Okay.
Good talk. Very good talk.
Oh, thank you, ma'am.
Okay. Thank you, Professor Singh. Anybody else? If not, then might be we will end this here. And thank you, Dr. Sen, again for such a wonderful talk.
No, actually, I just want to. Sorry.
Yeah, sure.
So, are you trying for an analog of Berling's theorem on the semi-simple part?
Can you please introduce
yes,
yourself?
actually, I think it's I can recognize the voice. I think it's
This is Sundari. Sorry,
yeah.
I'm sorry about it. I mean, this is Sundari. Yeah, no, sorry about that.
Yeah, I recognized your voice anyway.
Please go ahead.
Yeah, actually, Borel's theorem is it's only done for Rn and torus, and I said there's just a corollary kind of in two-step. All other thing is wide open. So one should.
Yeah, but the version, I mean, at least the theorem is not so easy. If I'm not,
that is the point. The general
in the semi-simple part, and so
many
things one has to make sense, and so what is the best definition for which can give the result is going to be troublesome, isn't it?
Right. And this, as you know very well, that this positive measure thing is much difficult to handle than open set. So that creates a problem, and of course one should look at all these spaces. We'll try to look into all these spaces after this. So whatever versions are there, whatever works and whatever doesn't, so we should look into that. Of course.
Okay, thank you.
Anybody else, please? I don't see any raised hands.
Okay.
So we'll stop with this. Thank you, Dr. Sen, again for such a nice, wonderful talk.
Okay.
And the next talk is a contributory talk at 3 p.m. So we have a break of 9 minutes.
Okay, so maybe we can utilize this time by filling up a survey form, a feedback form. So I'm keeping one link in the chat box for everyone, and feel free to provide your feedback on this conference. Today is the last day of the symposium on analysis and PD. So yeah.
Yeah, that's a nice idea actually. Yeah, so it will help for future
Sure.
initiatives as well. Yeah,
Sure.
good. So I think you have already uploaded it on chat box, so people can just fill that form, in these 5-6 minutes. Great. So we'll start again at 3 p.m. So Dr. Amardeep Sarkar, can you please share your screen, so we can just check whether things are fine?
Yeah, sure.
Yeah.
Can you see the slides?
Yes, it's perfectly fine. Yeah.
Yeah.
So we'll just wait for 2 minutes and we'll start.
Okay.
Okay, so we can start now, and welcome back. So we have three contributory talks lined up today. The first one is by Dr. Amardeep Sarkar, who is a postdoctoral fellow at the Harishchandra Research Institute, Prayagraj. And today he's going to talk on some aspects of the characterizing metrics. So over to you, Dr. Sarkar.
Thank you. First, I'd like to thank the organizer for giving me an opportunity to talk here. Today, I'm going to talk about characterizing metrics. Most of the person, let me tell that today I'm going to talk a little bit different than I initially thought of giving. So I will talk about characterizing metrics, and most of the part of this talk has been done during my PhD. And so let's begin. Let's. I will outline the first. I will outline the what are the things I'm going to talk today. First, I will define what are conformal metrics. Actually, these conformal metrics arise in geometric function theory a lot, and many often these conformal metrics is studied through external problems in complex analysis. So initially, I will define that these conformal metrics. Then I will talk about the scaling principle, which has been used to prove the theorems I am going to present. And then I'll give a connection between the Alford map characteristic metric and zero kernel and the Gabellian kernels. Then I'll talk about the boundary behavior of this characteristic metric. And then I'll talk about their curvatures and higher order curvatures. And at the end, I'll talk about the submultiplicativity property of the characteristic metric. Let's begin with the definition of conformal metrics. On domains in the complex plane, the characteristic metrics, a general metric is denoted by this tau d z mod dz. Here, tau d denotes the density of this metric, and it is just a positive valued function on the domain, on the given domain D. We say this collection of metrics is conformal metrics if it satisfies the pullback property. That is, if you have a biholomorphic map from a domain D1 to another domain D2, so when you pull back the metric tau D2 with respect to the map F, that should be same equal to the metric tau D1. That is, we want this property to hold to be a collection of metrics to be conformal metrics. And the pullback formula is given by this formula, tau d2 of f of z into modulus of f prime of z for all z in D1. Some examples of conformal metrics are the hyperbolic metrics. Hyperbolic metric wants as example, and at any point z on a domain D it is defined to be the infimum of 1 by f prime of 0, where f varies over all holomorphic functions from the unit disk into the domain D such that the 0 maps to Z. Another example of conformal matrix are the Characterizing matrix, which I'm going to talk about today. And at any point of a domain, it is defined to be the supremum of the quantity f prime modulus f prime of Z, where it varies over all holomorphic functions from the domain D into the unit disk such that Z maps to 0. If you see the unit disk, the hyperbolic metric and the Characterizing metric are same, and it is given by 1 by 1 minus mod Z square, and it is the Poincare metric of the disk. And in general, they are not same. If you take the punctured disk, they will be different. Now let me briefly say about the scaling principle. This scaling principle has been used in higher dimension to solve several kind of problems. And let me say about it a little bit. For that, we take a domain D in a complex plane and a C2 smooth boundary point of that domain, call it P, and then we'll have a defining function psi near in a neighborhood of the point. We're calling it U, and any point in U intersection D is written as all points where psi is negative, and U intersection the boundary is where it is 0, and we also want that the gradient of this defining function to be non-zero on U intersection D. Now the scaling principle comes. For that, we take a sequence of points in the domain which converges to the boundary point P, and using the defining function psi and this sequence, we define this sequence of affine maps Z minus Pj divided by minus of psi of Pj, as psi is the defining function. Now, if you see the image of the domain D with respect to the affine maps Pj, it will give a sequence of domains. We are going to call these scale domains, and we can show that these scale domains obtained in such a way converges to the Hopf space in the Hausdorff sense. I'm not going to say what do I mean by the Hausdorff sense here, but let's note that this sequence of domains will converge to the Hopf space in the Hausdorff sense. So this is going to help us transform the problem of the boundary into an interior problem. Let's see how. Here, Hopf space is defined as real part of omega bar z minus 1 is 0, where omega is nothing but just the gradient of the defining function at the point at the boundary point P. So now we want to transform the boundary problem into an interior problem. If you see, if you take any conformal matrix, then we say that we already have this sequence of affine maps. Now what we do, we pull back it is pushed forward here with respect to Pj, and with respect to Pj inverse, it will be pulled back. When you pull back this tau d, the conformal matrix tau d, with respect to this Pj, you will get another by the pullback formula this matrix. When you substitute z equal to 0, we notice that these scale domains will always contain the point 0 because at the point Pj it is 0. So when you substitute 0, and these are metrics on the scale domains, when you substitute 0 here, on the right hand side we get tau d of Pj into minus of psi of Pj. This is a boundary problem, as we see that j tends to infinity. And here this is not a boundary problem because the point inside is fixed, but the domain is changing. So thus we have converted the boundary problem into an interior problem, but at the cost of varying the domains. But we already have seen these domains actually converges in the Hausdorff sense, and we are going to make use of that fact. Now let's connect what the Characterizing metric and the force map. If you recall the definition of the Characterizing metric, it is just supremum of the quantity mod f prime of a at the where f is varies over all holomorphic function in this collection, and we want f of a equal to 0. Actually, we can ask the question, does there exist a holomorphic function which attains this extremum? Actually, there is a holomorphic function whose derivative at the point A is positive, and that function is called the Alfors map. If you have a, now let's see how Alfors map can be written in forms of in the form of ratio of two kernels. And if you have a bounded domain which is infinity smooth, then the Alfors map at any point A in the domain can be written as just ratio of these two quantities. The SD z comma A is called the zero kernel, and LD z comma A called the Garabedian kernel at the point A. And how how this zero kernel and Garabedian kernels are obtained, I'm not going to talk about that, but I'll just say that these zero kernels are the reproducing kernels which comes from the reproducing kernel Hilbert space known as the Hardy space, and the Garabedian kernel obtained as a conjugate kernel of this zero kernel. Let's talk about some properties of these kernels, and we see that the zero kernel is holomorphic in the first variable and anti-holomorphic in the second variable. And if we fix A, that the Garabedian kernel is holomorphic in D minus A, and it has a simple pole at the point A. And we see that the zero kernels are Hermitian symmetric. Using the Hermitian symmetric property, we can easily see that it is greater than or equal to 0 along the diagonal, and hence we can also show that the zero kernel is a real analytic function for any domain which is infinitesimally bounded. Now, the remarkable thing is this, that the Characterizing metric can be written as 2 pi of the zero kernel along the diagonal, and this will say that the Characterizing metric is a real analytic function. Hence, we can define the curvature of the Characterizing metric as well. Now, let's give you the formula for the zero kernel of the half space, where because we are going to use this, and zero kernel, Garabedian kernel, and the Alfors map. The Alfors map of the half space is given by this formula. A mod of omega is this same omega to define this half space, and the zero kernel is defined by this formula, and the Garabedian kernel by this. If you take the ratio of these two, you will get the Alfors map, as you can easily see here. And along the diagonal, the zero kernel is strictly positive, as you can see here. Because real part of omega bar z minus 1 is strictly less than 0, so this should be strictly positive. And this is we also mod omega is always positive because it is the gradient of the defining function, as we have seen before. Now let's come to the first theorem of this talk. We're going to prove this theorem in the following setup, where D is a bounded domain which is the smooth boundary, and we want P a boundary point psi with a local defining function as before, and we also define the collection of defined maps by Tj with the same formula we did before. And as we know that this Dj converges the half space in the Hausdorff sense. So in this setup, we have the following theorem. We showed that the sequence of Alfors map of the scale domain Dj converges at the point A converges to the Alfors map of the half space uniformly on complex subsets of the half space H. Also, we have the sequence of zero kernels of the half space of the scale domains converges to the zero kernel of the half space uniformly on complex subset of H cross H. And we also have this convergence of the Garabedian kernel on complex subsets of H minus the point A. Now, using the theorem, using this theorem, we can also prove this following theorem, which says that for a bounded domain and for a point in the boundary which is C2 smooth, and hence we are taking a defining function psi of near that point. In that case, in this setup, the theorem says that if you take the product of the Cartesian metric and negative of the defining function psi, this limit will go to the Cartesian metric of the Hausdorff at the point 0, which is mod omega by 2, as the point z goes to the boundary point p. So hence, if you take in place of this defining function psi, if we take the special kind of defining function, we'll get this theorem, which says that in the same setup we have this theorem that says that the Cartesian metric can be compared to the quasi-hyperbolic metric of the domain D. This quasi-hyperbolic metric is 1 by distance between z and the boundary of the domain D. And near the point there, we can compare these two metrics, and actually explicitly we can compute the ratio of these two metrics as the point z goes to the boundary point P. Next, I want to talk about the Gaussian curvature of the Cartesian metric, and the Gaussian curvature of the Cartesian metric is defined to be minus of Laplacian of log of the Cartesian metric divided by square of the Cartesian metric. And if you expand this formula, you will get this expression here. Actually, this would be a negative in place of positive. We'll get this formula, and in this formula, if in these terms, if you see here the partial derivatives of the Cartesian metric, which is written here, CDij bar is the derivative of the Cartesian metric, I plus j derivative of the Cartesian metric with z and z bar.
Dr. Sarkar, you have 5 minutes left. Okay.
Yeah. So now this theorem says that if you take the sequence of scale domain, then this Cartesian metric of the scale domain will converge to the Cartesian metric of the Hauss space uniformly and complex subset of the Hauss space. And also we can prove this, the curvature of the Cartesian metric of the scale domains converges to the Cartesian metric of the Hauss space, the curvature of the Cartesian metric of the Hauss space, which is equal to -4. And hence, since the curvature of the Cartesian metric is conformal invariant, we get this for a convergence of the curvature of the Cartesian metric of the domain D. Now let's define higher order curvature of the Cartesian metric, and it is defined to be this quantity j and j sub and d z divided by cz of n plus 1 whole square, and here j and d is determinant of this quantity, and this is the derivative of the Cartesian metric. It turns out that this higher order curvatures are conformal invariant, and these are useful quantities. And when you put n equal to 1, it is the standard Gaussian curvature. And Berger showed that for any domain, the curvature is bounded, higher order curvature is bounded above by this quantity, and equality holds if and only if this is the domain is simply connected. Now we have the following theorem, which says that the curvature of the higher order curvature of the Cartesian metric of the scale domains converges to this quantity. Using this, we have this following theorem, which says that we can compute the higher order curvature of the Cartesian metric of a domain. Means we can say about the convergence of the higher order curvature of the Cartesian metric, and that will exactly converge to this quantity as z goes to the point P for any bounded domain, such that we have the point P to be a C2 boundary point. This is the last theorem of this talk I'm going to talk about. This connects the Cartesian metric of any two domains such that the intersection is not empty, and we want the domains to be smoothly bounded. And this says the following: the Cartesian metric of the intersection of these two domains product with the Cartesian metric of the union of these d1 and d2 is less than equal to some constant into characteristic of D1 and the characteristic of D2 for every point in the intersection D1 intersection D2. And this constant is obtained which will depend on the domain D1 and D2, and this constant will depend on bounds on the curvature of the characteristic matrix. So thank you. I'll stop it.
Thank you, Dr. Sarkar. And we have about 6 minutes left before the next talk. So if people want to ask some question, please go ahead. If somebody has a question, please unmute yourself and you may ask.
Hi, Amar. This is Gautam.
Yes, hi, sir.
So I have a slightly naive question. During your talk, you mentioned an asymptotic comparison to the pseudo-hyperbolic metric. And you sort of gave a very quick definition, an expression which you call the pseudo-hyperbolic metric. This is the
quasi-hyperbolic.
Yeah. So this is this particular expression. Is it under the assumption that one is at an interior point which is close to a C2 smooth boundary point, or is this in fact the definition itself?
Yeah, to define the quasi-hyperbolic metric, we don't need this C2 smoothness.
Okay.
And you can define for any domain.
Okay.
But to hold this condition, that means the characteristic metric can be compared with this quasi-hyperbolic metric.
I see.
In this scenario, to explicitly compute this limiting case, we want this to be C2 smooth, and in that case, we can use this function, distance between Z and boundary of Z, to define the defining function of the domain.
Okay.
And we can use this formula to obtain this.
Yeah. And you can guess why I asked this question, because minus the definition, it somehow looks like it is very dependent on Euclidean coordinates, whereas being conformal, it shouldn't. But what you are basically doing is just stating the result in the above context, yes?
Yes, right.
All right. Okay. I now understand. All right. Thank you.
Thanks.
Any more questions or comments? So it seems we don't have anybody else. So thank you, Dr. Sarkar, again. And yeah, so the next talk is now at 3:25, and that will be by Mr. Anvoy Maitra. So Anvoy, can you please share your screen now?
Yeah, I will do that.
Sure. Yeah.
So is it visible?
Yes, it's coming perfectly fine. Yes. So we'll wait for 2 minutes and then we'll start.
Okay.
Okay, so we will now start the next talk, and the speaker is Mr. Anvay Maitra. He is a PhD student at the Indian Institute of Science, Bengaluru, and today he's going to talk on the continuous extension of complex geodesics. So over to you, Anvay.
Okay. So first of all, I would like to thank the organizers for giving me the opportunity to speak at this conference. So today we will be talking about the continuous extension of complex geodesics. So in order to define that concept, we need the notion of Kobayashi pseudodistance. So let's get on to that. So it would be very useful to construct for every complex manifold X a distance kx such that holomorphic mappings are contractive with respect to this family of distances. A useful consequence of this, for example, would be that whole xy, the space of all holomorphic mappings from x to y, where x and y are two manifolds admitting such a distance, would be equicontinuous. In the 1960s, Kobayashi introduced a family of pseudodistances. They are not distances in general that satisfies the above properties. So how are these pseudodistances defined? So given a complex manifold X and points A and B in X, we define KXAB, the Kobayashi pseudodistance between A and B, to be infimum of the set of all summation from j equal to 1 to m rho d 0 zeta j, it is the rho d is the Poincare distance, such that there exist holomorphic mappings f1 dot 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 fm from d to x such that a equals f1 of 0, fj of zeta j equals fj plus 1 of 0 for all j equal to 1 to m minus 1. This is the linking up condition, and fm of zeta m equals b. So what we are basically doing here is that we are taking a chain of analytic disks, chain because of the linking up condition, joining A to B, calculating the length of this chain using the holomorphically invariant object at our disposal, namely the Poincare distance, and then infimizing over the lengths of such chains to get the Kobayashi pseudodistance. So this is the same sort of thing we do in Riemannian geometry. So this is a natural definition. So we move on to isometries with respect to the Kobayashi distance. Whenever we study distance spaces, a natural object of study is isometries between them. So for complex manifolds X and Y, a natural object of study, provided Kx and Ky are distances, is the set of all maps from X to Y that are isometries with respect to the Kobayashi distance. Such isometries need not be holomorphic. A trivial example is the map Z goes to Z conjugate from D to D. Since D is the complex analog of the unit interval -1, 1, of particular importance are holomorphic isometries between D and a given complex manifold X. These are called complex geodesics of X. So it is elementary to show that Kx is a distance, true distance, in bounded domain Cn. Note, however, that we have not addressed the question of the existence of isometries. So turning to this question, Lempert proved the following famous theorem in 1981. If omega subset of Cn is a convex domain, then C omega equals K omega, where C omega denotes the Carathéodory pseudodistance on omega. The Carathéodory pseudodistance is a standard object. I won't define it. Its definition is similar to what we saw in the previous talk. But the importance of this theorem is that it implies that in an arbitrary bounded convex domain, there exist complex geodesics passing through every pair of points. In order to prove this, one uses a standard argument involving tautness because bounded domains are involved. So it's not very difficult, so I won't deal with that. That is a standard theorem. So, however, in many potential applications, existence is not enough. One needs information on boundary regularity. Turning to this question, Lempert proved the following. Lempert 1984. If omega subset of Cn is a strongly convex domain with Ck smooth boundary where k is greater or equal to 2, then every complex geodesic phi from D to omega extends in a Ck-2 smooth manner to del D. So our assumptions are strong convexity and Ck smooth boundary where k is greater or equal to 2. Then we get extension. So in view of this, it is natural to ask what weaker conditions on omega will guarantee the continuous, if not smooth, extension of complex geodesics to del D. Some conditions are needed, as the following example shows. So example, it is easy to show that a holomorphic mapping F equal to F1, F2 from D to D2 into the bidisk is a complex geodesic if and only if at least one of F1 and F2 is a holomorphic automorphism of D. Choose a holomorphic function G from D to D that does not extend continuously to del D. Infinite Blaschke products are examples of such functions. Then F, defined to be Z going to Z, GZ from D to D2, is clearly a complex geodesic because one is just the identity. Complex geodesic that does not extend continuously to del D. So some conditions are needed. So we turn to some recent results on boundary regularity. There have been a couple of recent results on the boundary regularity of complex geodesics. A result by Borel, 2016, states that in a bounded convex domain with C1 smooth boundary that is supported from the outside by a certain kind of surface, ensuring, for example, that there are no points Xi in del omega at which del omega contains line segments starting at Xi in certain directions, every complex geodesic of omega extends continuously to del D. So I will just give an illustration to show what this supported from the outside means. So just bear with me for a minute. So this is roughly what it means. So there is a certain kind of surface given in the diagram by the graph of a certain function f, such that near every boundary point, the boundary of omega lies above the graph of that function. So in this sense, it's supported from the outside. So that's roughly what we mean. So returning to the main discussion, another result by Zimmer, 2017, states that in a bounded convex C strictly convex domain omega with C1 alpha smooth boundary, where alpha is in 0, 1, every complex geodesic of omega extends continuously to del D. So first of all, what do we mean by C strict convexity? In the C1 smooth case, which is the only case we are interested in, it simply means that if you take any boundary point and you consider the affine complex tangent space at that point, then that does not intersect the closure of the domain at any point other than that point. So in that sense, it's C strictly convex. That's what we mean by C strict convexity. As for C1 alpha smoothness of the boundary, that means that the domain has a defining function whose total derivative is not merely continuous, but also alpha Holder continuous. So that is what we mean by C1 alpha smoothness. Neither of these results subsumes the other. This talk arises from a conjecture motivated by these two results. So first we make some observations on the stated results. First we introduce some notations. Bold J will denote multiplication by I in Cn, viewed as an R-linear map. So in particular, JV will be orthogonal to V relative to the usual real inner product on Cn, which we identify with R2n. D subscript V will denote the directional derivative in the direction of V for a unit vector V. And eta upper Xi will denote the unit inward normal to del omega at Xi, where omega is C1 smoothly bounded and Xi is in del omega. A careful reading of Zimmer's proof already shows that we can replace the condition del omega is C1 alpha smooth by there exists a defining function rho of del omega such that the particular directional derivative d j of eta Xi rho is alpha Holder near every Xi in del omega. So this motivates the conjecture because we have already significantly reduced the smoothness assumption, regularity assumption. It suffices for a bounded convex domain in Cn to be C strictly convex and have just a C1 smooth boundary for all complex geodesics of omega to extend continuously to del D. This is a conjecture, but our result is a step towards this conjecture. So we turn to our results. So let omega subset of Cn be a bounded convex C strictly convex domain with C1 smooth boundary. Assume that there exists a defining function rho and r greater than 0 and a non-decreasing function omega from 0 to r to 0 infinity satisfying a Dini condition such that for every Xi in del omega, that same directional derivative d j of eta Xi rho restricted to the n-dimensional ball bn Xi r has modulus of continuity dominated by omega. Then every complex geodesic of omega extends continuously to del D. So that is the result. So now we turn to main ideas behind the proof. So the main idea of Zimmer's proof and also of our proof is to adapt the proof of the fact that if we have an isometry between two Gromov hyperbolic distance spaces x and y, then it extends to a continuous map from x union x infinity to y union y infinity, where x infinity and y infinity are respectively the ideal boundaries of x and y. So it would be desirable for bounded convex domains in Cn to be Gromov hyperbolic with respect to the Kobayashi distance, because then we could at least hope to apply this method to prove an extension. However, bounded convex domains in Cn are not Gromov hyperbolic with respect to the Kobayashi distance in general. So we need a weaker result R that acts as a substitute for Gromov hyperbolicity. So this is that result. Let omega relatively compact in Cn be C1 smoothly bounded and C strictly convex. Let P nu and Q mu be sequences in omega converging to boundary points. Suppose limit as mu and nu tend to infinity, P nu Q mu O. So this is the Gromov product. You will see it defined below. Gromov product with respect to the Kobayashi distance is equal to infinity whenever P nu and Q mu converge to the same point, and that a weak form of the converse of this holds true. Then every complex geodesic of omega extends continuously to del D. R is implicit in Zimmer's work. So that's, I wanted to point that out. Now I need to say what a weak form of the converse of this means. So I will just tell you that. So just so this is what it means. So in one part, we demanded that if P nu and Q mu converge to the same boundary point, then the limit, double limit of the Gromov product should be equal to infinity. In the other part, we suppose that P nu and Q mu converge to boundary points x and y, and we suppose that we know that lim sup nu and mu tend to infinity, P nu Q mu O is equal to infinity. Then while we may not be able to conclude that x is equal to y, we will be able to conclude that the complex affine tangent spaces at x and y are the same. So that is what we mean by a weak form of the converse. So that is what we mean. So returning once again to the main discussion. So we had dealt with this slide. This is done. So we are reduced to obtaining the conditions in R. The main technical tool that shows that the hypothesis of R holds true for omega as in our theorem is the parametrization of inward pointing normals as K almost geodesics. These K almost geodesics are essentially geodesics up to a bounded error, namely log K, and their work is that they facilitate computation of the Gromov product, which is important because the Gromov product makes an appearance in R, result R. In turn, what allows us to parameterize inward pointing normals as K almost geodesics is the ability to embed copies of a model planar domain script D, whose Riemann map behaves well at 0 in del script D. Via the embeddings, Z goes to Xi plus Z eta Xi into omega in such a way that Xi plus script D eta Xi, the embedded domain, osculates del omega at Xi. This is an idea due to Zimmer. So I would just like to point out that the embedding in question is very natural. We are placing ourselves at the boundary point Xi and using the inward pointing normal to basically place our planar domain into the bigger domain. So the embedding Z goes to Xi plus Z eta Xi allow us, due to the distance decreasing property of holomorphic maps, to deduce K omega measurements from K script D measurements. In turn, the Riemann map condition allows us to write K script D near explicitly using rho D, the Poincare distance, with excellent estimates arbitrarily close to 0 in del script D. So this is where we need the invertibility of the derivative of the Riemann map at 0. So as I just said, parametrizing inward pointing normals as K almost geodesics only requires the Riemann map of our script D to have non-zero derivative at 0 in del script D. So searching in the one variable literature, we located the following result by Warshawski. If D is a relatively compact subset of C bounded by a Jordan curve gamma that has, in a neighborhood of some point P in gamma, a continuous tangent angle whose modulus of continuity satisfies a Dini condition, then the Riemann map of D has non-zero derivative at P. So the Dini condition in our theorem comes from the above. That is the Dini condition in Warshawski's result. So we end by defining a model planar domain that works. So first I'll give the definition. I will provide an illustration a little later. Script D C tau is defined to be set of all Z in C such that 0 is less than real part of Z less than tau. Modulus of imaginary part of Z is also less than tau. And real part of Z is greater than C times H of imaginary part of Z, where the function H is defined as follows. H of y is defined to be integral from 0 to y omega of t dt if y is greater or equal to 0, defined to be integral from y to 0 omega of minus t dt if y is less than 0. Please note that omega is the modulus of continuity that is given to us. It occurs in the statement of the theorem. So we are using that to cook up our domain script d c tau. So I will give an illustration of what these domains look like.
So Anway, you have 4 minutes left.
Okay, yeah. So this is what they look like. So this is roughly what they look like. As you can see, they are constrained within a box of width tau and height 2 tau. And this curve is, I mean, the curve you can see CH of y. And clearly one can see that as one increases C and decreases tau, the domain script d C tau shrinks. So that is the point I will end on, that one can choose C large enough and tau small enough so that affine images of script d C tau fit into omega. That will allow us to parameterize inward pointing normals as key almost geodesics. That in turn will allow us to obtain the conditions in R, and then we will get our result. So that is concludes the talk. Thank you.
Okay, thank you, Anway. And the floor is open for some questions. Actually, we have 7 or 8 minutes left before. Yes, so if there is any question, please unmute yourself and ask the question.
So, Envoy, a quick question. I'm sorry, I know that we have discussed the ideas behind this proof very often.
Yes.
But then, I mean, since ultimately the execution was yours, there's one thing I have forgotten.
Yes.
So you mentioned that you have these parameters capital C and tau.
Yes.
Which you adjust to be able to fit this this planar domain in that obvious C affine manner.
Yes.
At a boundary point.
Yes.
Now the boundary point is completely arbitrary.
Yeah.
What you're kind of saying is that one can choose. What is the order of quantifiers?
Yeah.
You can choose C and tau once and for all.
Yeah, once and for all, independently of all boundary points, such that it can be done at any C in del omega. Okay. That is the thing.
Yeah, go ahead. And you were saying?
I mean, the regularity that C1 Dini, in fact, the regularity C1 Dini, and because omega is fixed, it is given in the theorem. So that is also a kind of uniformity that allows us to find C and tau. That suffices.
I see. So the choice of the parameters doesn't depend on the oscillation point because that omega has been stated as in the hypothesis as being independent of the boundary point.
Yes, yeah? Yes, it has been stated like that. Yes.
Okay. All right. Yeah. Thanks.
Yes. Anybody else? Comments or questions? Anything? So it seems we don't have any further questions. So thank you again, Anway.
Thank you.
And the next talk is now at 4 p.m. So we have a break of 15 minutes. Okay.
আর এখন
Yeah, Mr. Soros Sabantari, are you here?
Yeah, I'm here. Hi.
Yeah, so can you please share your screen now?
Sure. Excuse me. Hello. Actually, I'm facing a little bit of problem with sharing my screen. So
is it saying something? Soumya or
so
Sai,
Yeah,
can
what
you
is
please
the
help?
problem?
so this is I'm using a Mac. So what it does is I go for the sharing of screen, and it gives me a pop-up window where the only two options are given, that cancel and share, but share option is not available, it seems.
So are you using a browser or the app of?
I'm using a browser only.
Might be you will have to
It's
actually.
better to use app. You have an app?
I don't have actually.
You can install quickly.
Okay,
Yeah,
I will just
yeah.
try it out.
I also faced the same problem actually. So
Okay, all right. Let me just try to find the app.
for those who have joined us now, the talk will start soon.
Hello.
So is it installing?
Is my screen shared now?
No.
No.
Not yet.
It is not.
Maybe you need to give some permission, some place, the settings maybe. It's showing something, or maybe Shanda, can you help?
Yeah, the problem is I don't understand what's happening.
Sorry?
Okay, Saurabh, are you installing the Zoom software there?
So did you install it already? Saurabh?
So he joined using another device, I guess. I can see two showed up Shamundara now.
Okay.
So to all the participants, there will be a slight delay in this talk. So Saurabh is trying to fix it up. So please bear with us.
Hello.
Yes. Did you install it?
I was not able to, but I have arranged another laptop. I think from this I can share.
Okay.
So I have actually joined the meeting with a different laptop now. Can you please add me as a host?
Soma, can you
Sorry?
add him? Can you add him as a host?
So for sharing, you need not be a host.
Right.
Any participant can share it.
Share, yeah. So have you joined by some different name or something?
No, same name I have joined with.
Okay, so please try sharing again.
Okay.
Yes.
Yes, it's coming now.
It's coming now. Okay, perfect.
Okay, so apologies for the delay, and we will start now. So the final talk of this session, and actually the final talk of this symposium on analysis in PDs, will be by Mr. Saurav Samantare. He's a PhD student at Indian Institute of Science, Education and Research, Thiruvananthapuram. And today he's going to talk on asymptotic preserving and asymptotically accurate finite volume schemes for low Mach number isentropic flows. Yes, over to you, Saurav.
Thank you. First of all, I would like to apologize for the delay. It was a technical issue. And I would like to congratulate the organizers for successfully arranging this entire Math Fest. And I would also like to thank them for providing me this opportunity to present my work. This is a joint work with my PhD supervisor, Dr. K. Arun. And in the course of this talk, I plan to define most of the jargons involved in the title of the talk, so one doesn't have to worry much. So to start with, I would define what is called a Mach number. A Mach number is a non-dimensional quantity, which is defined as a ratio of reference fluid velocity to a reference sound velocity. So for our usual flows that like atmospheric flows and for ocean flows, one can understand the Mach number is very low because the fluid velocity will be very small in comparison to the sound velocity in the medium. In the low Mach number regime, or where in the vanishing Mach number regime, the solution of the compressible flow equations converge to the solution of its incompressible counterpart. Most of the current flow solvers are inadequate and they don't satisfy this condition, or they don't simulate the transition. Most of the current flow solvers, the compressible solvers suffer from pathologies such as reduction in order, instabilities, and a lot more things when they have to face this transition as low Mach number goes to 0. To develop schemes which actually support this transition from compressible to incompressible regime, we need to have more strong mathematical analysis of the governing equations. Recently, a study by Lassery revealed that the pathologies suffered by the compressible flow solvers are because of the inability of these schemes to preserve a well-prepared space of constant densities and divergence-free velocities. Depending on this analysis, a new concept of accuracy called called asymptotic accuracy or low Mach number accuracy is introduced. To this end, we consider the Euler equation of gas dynamics with isentropic equation of state. An isotropic fluid is characterized by the fact that the ratio of the density variation to that of the temperature variation is a constant. Equation 1 is the mass conservation equation. Equation 2 is the momentum conservation equation. In equation 1, rho 1 and 2, rho is the density and u gives the velocity, and the pressure P is given as a function of density rho. Epsilon is a reference Mach number, and as epsilon goes to 0, the solution of the compressible system converges to the solution of its incompressible counterpart given by 3 to 5. The incompressible system 3, 5 is nothing but the incompressible Euler system or the incompressible Navier-Stokes system. To carry out analysis in the low Mach number regime, we consider the non-conservative form of the isentropic equation Euler equations, where H is an advective operator and L is a convective operator. The problem is posed in a d-dimensional torus tau d, and we are looking for L2 solutions. The well-prepared space E is defined as a space of constant densities and divergence-free velocities, and its E tilde gives its orthogonal complement. The well-prepared space E is also the kernel of the operator L. De Lasserie observed that if U is a solution of the Euler equation system with U0 as the initial condition, and if U bar is a solution of the projected subsystem where the projection is taken to the well-prepared space E with the initial condition given as projection of U0, if the initial data U0 is well prepared in this sense, then at a later time t, the solution at any later time t, the solution also stays well prepared in this sense. And this is only true for epsilon very, very small. And we also note that the system 12, 13 is equivalent to the incompressible system. So what this theorem says is, if the Mach number epsilon is very, very small, then if initially the solution of the compressible system is close to the solution of the incompressible system, then the solution evolves closely to the solution of the incompressible system at any later time t. To further understand this phenomena, we can linearize the isentropic Euler equations around a constant density and a velocity rho bar u bar to obtain the linear wave equation system. A linearized version of Soy's result was proved by De Lasserie, which says that if U0 is the initial condition for the wave equation system, and if U is the solution with this initial condition, and if U bar is the solution of the projected subsystem, the projection again being taken to the well-prepared space E, then the acoustic as well as the incompressible energies are individually preserved, and if the initial data is well prepared in this sense, then the solution also remains well prepared. It was seen by De Lasserie that most of the current flow solvers or the explicit flow solvers that are available suffer from pathologies because their solutions do not satisfy this estimate. For example, if we consider fx as a linear spatial differential operator, then for an initial condition U0, if we assume that 21, 22 is well posed, then it satisfies the estimate 23. Even though the initial data U0 is well prepared, we see we can only obtain the solution to be close to U bar. U bar, we have to note that U bar is not the solution of the incompressible system. So he proposed a sufficient condition for any numerical scheme, for any linear spatial differential operator, to ensure the condition 20 is if the spatial differential operator is E invariant, that is if initially the solution is in the well prepared space E, and if the scheme leaves the space invariant, that is the solution of the scheme stays in E at any later point of time, then we obtain the estimate 20 given by 24 here. We see that the transition from the compressible to incompressible flows is of singular nature. That is, the compressible system is of hyperbolic nature, whereas the incompressible system is of hyperbolic elliptic nature. Shijin proposed a robust framework to design schemes for such singularly perturbed problem. Let's assume if P epsilon H is a scheme for a singular perturbation problem, P epsilon, which converges to P0 as epsilon goes to 0. The scheme is called asymptotic preserving if, as epsilon goes to 0, P0H becomes a consistent discretization of P0, that is, the diagram commutes, and more importantly, the stability constraints of the scheme, that is the constraint on the discretization parameter H, should stay independent of the singular perturbation parameter E. The advantages that we have for AP schemes is that they enjoy much better error estimates than the classical schemes. For example, if we consider a pth order accurate scheme, P epsilon H, for a classical scheme, it would satisfy the estimate 26. We can see that in the estimate 26, we have epsilon in the denominator, that is, when epsilon goes to 0, the order of the scheme reduces. But because of estimate 27 that is enjoyed by the AP schemes, we will never face the same problem. Rather, as epsilon goes to 0, an AP scheme becomes better and it achieves the pth order accuracy. This estimate 27 is nothing but the estimate that the Lassery speaks about. And depending on this, we define a new concept of accuracy called asymptotic accuracy. A scheme is said to be asymptotically accurate for the isentropic Euler system if it leaves the incompressible space E invariant. One has to note that the asymptotic accuracy is just a sufficient condition to obtain the previous estimate. To define AP schemes for the isentropic Euler equations, we consider the IMX-RK time discretization framework for stiff ODEs. Equation 30 gives a stiff ODE in the additive form, where F is the stiff part and G is the non-stiff part, and epsilon is the stiffness parameter. An S-stage IMX-RK scheme updates the solution yn at time tn to the solution at yn plus 1 at time tn plus 1 through S intermediate steps given by yi's and a final update step given by yn plus 1. An IMX-RK scheme is usually represented by a double Butcher tableau and is characterized by the coefficients given in the vectors and matrices C tilde C, A tilde A, and W tilde and W. We only consider a special type of IMX-RK scheme called Dirk or diagonally implicit RK schemes, where the matrix A is a lower triangular matrix. We also restrict ourselves to schemes of type A, that is, the matrix A is invertible, or schemes of type CK, where the matrix A has first row 0 and first column 0. Other than that, it is an invertible matrix. A scheme is called globally stiffly accurate if the last row of A tilde is equal to W tilde and the last row of A is equal to W. To design a S-stage IMX-RK scheme, we take the mass flux and the pressure gradient of the momentum flux implicitly, and rest of the fluxes are taken explicitly. Note that to solve this scheme, we do not need to solve the entire implicit system. We rather go for a reformulate, we rather solve a reformulated scheme where we derive an elliptic reformulation and we solve an elliptic problem which is derived by eliminating the momentum qk between 31 and 32 to obtain 35. First, we solve for the pressure or the density rho k, and then the momentum qk for the kth stage is updated explicitly using the obtained density rho k. The schemes, the time semi-discrete schemes are proved to be asymptotically consistent. That is, if the initial data rho and un has the form 36, 37 and satisfies the gradient and divergence constraint, then if the scheme at at the kth stage rho k uk satisfies 36 and 37, then the divergence and the gradient constraints are satisfied as well, and the scheme converts to a scheme for the incompressible system as epsilon goes to 0. To obtain a stability to carry out the stability analysis, we consider the linear wave equation system and the scheme for the linear wave equation system, and we carry out a modified equation analysis by plugging in the exact solutions to obtain the modified equation 44. We obtain a sufficient condition depending only on the Runge-Kutta coefficients independent of epsilon for the L2 stability of the scheme. The time semi-discrete schemes are proved to be asymptotically accurate, that is, the scheme leaves the well-prepared space E invariant, and also the solution of the modified equation system leaves the well-prepared space E invariant. To define a fully discrete scheme, the implicit part of the implicit fluxes are approximated using central fluxes, and the explicit parts are approximated using the usual Rosenhoff fluxes. The fully discrete schemes are also proved to be asymptotic preserving, that is, they are proved to be asymptotically consistent with the low Mach number limit, and the stability constraints are also proved to be independent of epsilon. 57 gives the stability constraint for a fully discrete scheme. One can note that the stability constraints are independent of epsilon. The fully discrete schemes are also proved to be asymptotically consistent, and the solution of the modified equation is also proved to be E invariant. In order to show the efficacy of the scheme, we provide some of the numerical case studies that one numerical case studies that we have carried out. We consider a moving vortex problem where 59, 60 and 61 give the initial condition, and the problem is posed in a square domain 0, 1, 0, 1, and the exact solution is just a translation of the initial condition given by 62.
Saurav, you have 5 minutes left.
The schemes are seen to enjoy uniform order of convergence. That is, we can see from the 4 tables available here, given for epsilon equals to as low as 10 to the power minus 6, ranging from 10 to the power minus 1 to minus 6, we can see that the schemes achieve second order convergence irrespective of the value of epsilon. In this, we provide the Mach number plots of the for the vortex problem after one time circle, one full time period where time at time t equals 1.67, where the top profile is the Mach profile at time t equals to 0. One can see that for all the values of epsilon chosen here, that is values ranging from 10 to the power minus 1 to minus 6, the Mach number profile is well preserved. The schemes are seen to have the energy dissipation property, that is, and they are seen to have the dissipation property more or less independent of epsilon, and we also show a plot of the vorticity we show the plot of the vorticity of the fluid, where we see the vorticity hardly changes depending on the epsilon. We conclude that the schemes accurately capture the low Mach number limit and are asymptotically accurate. These are some of the references that we have considered. For more details of this work, one can look into this publication. Thank you.
Okay, thank you, Saurav. And now we can let some questions come in. So people may unmute and ask questions. It seems there is none. So we'll thank Saurav again.
Thank you.
Okay, and that brings us to the end of this symposium on analysis and PDs. And the next talk today is at 5, which is a public talk by Professor Siddharth Gadgil. So organizers, would you like to say something now?
Yeah, thank you, Professor Beth,
you're
for
most
chairing the
welcome.
session, and we'll come back at 5.
Sure.
Yeah, thank you.
Yeah, thanks a lot, everyone.
Sorry? Can you hear me? Yeah, we are live.
Okay. Yeah, I'll keep my angle this way. Just one moment, I'll be back.
Sir, are you using Beamer presentation, by the way?
No, this is not Beamer. This is Zornal, as it's called, Zornal plus plus. Oh yeah, sorry. It is hybrid Beamer. So I made slides in Beamer. I imported them as annotate PDF in something called Zornal plus plus, so that I can write on it a little bit, write or draw a little bit.
Oh, okay.
So it's not. It's a hybrid version. Yeah, that's my current experiment. Sorry, did you say something?
No, I didn't say anything.
No.
It's somebody else, I guess.
Yeah. I thought I heard someone say, "Can you dim?" And I didn't understand dimming what. So, yeah.
Yesterday, Subhaj's presentation, he used something. I'm still trying to get what he used. His background is sort of like this old scroll type of papers, and everything was written there. It's kind of like ancient text.
I think that was Keynote.
Oh, it was what?
It was Apple Keynote.
That's
so there
what
are some, yes. There are some preset formats, and it is one of the standard formats.
Oh, okay.
So he has an iPad and he lectures writing on an iPad. So this we'd be using the appropriate Apple software.
Yes, that's the Keynote one.
Yeah, I don't have a tablet. I have a Wacom tablet attached to a laptop. So that's why I use a different setup. Yeah.
Could you please try the full screen option, if possible?
For me?
Yeah, full screen, because we can see the menus and.
You'll see what menus then?
Yeah.
Okay.
So this, yeah.
Okay, fine.
Yeah. Okay.
So I'm only a little concerned. Let me see. Yeah, it's okay. Yeah, it's working. I'm concerned that there'll be interference between the top and the Zoom toolbar. Wait. Okay, let me just try one thing. No, I think I'll take a risk on this.
Okay.
Because I'm used to it. I'll go like this. So I'll get out of full screen if there's any interference. There isn't. There isn't.
Okay. So let's start. Welcome everyone. Today we are in the last plenary talk of the conference. So today we have Dr. Krishnendu Gangopadhyay from ICER Mohali, and he will be the chair for this session. Yeah, over to you, Krishnendu.
Okay, so good afternoon, everyone. It's a great pleasure. So today is the last working day of this virtual math fest. Tomorrow there will be a panel discussion and validatory function, but there will be no more academic, formal academic talks, I say. So I thank Professor Siddhartha Gadgil, who is our plenary speaker today, for accepting our invitation and for giving this talk. So Professor Gadgil works in the broad area of low dimensional topology So he did his PhD from California Institute of Technology in 1999. And after that, he held positions as a postdoc in Stony Brook and then joined Indian Statistical Institute as an associate professor. So currently he is a professor at the Indian Institute of Science, Bangalore from 2012. So Professor Gadgil has a broad, versatile interest. So he is one of the very versatile mathematicians of the country. So these days, I mean, he is also working in areas which we like to call interdisciplinary areas. Like you can see from his title, it's a combination of geometric topology and some aspects of biology. So I welcome Professor Gadgil to deliver his talk. Thank you.
Oh, thank you very much, Krishnendu, and I should thank the organizers for, of course, inviting me to speak, but also for organizing these things. I mean, very unfortunate circumstances have resulted in organizing these, but I think this is a wonderful thing even in happier times, especially it saves travel, it saves jet fuel and the costs of air travel, but also in India, especially, you can reach far more people this way. It's wonderful. Hopefully these things will continue even in happier times, maybe along with the more personal events. Okay. So this talk I'll be turning off my video soon because my network is not great. And if I keep my video on, you may not hear me so well. Okay. So let me begin. So this talk is going to be about various things, about free groups, mostly about free groups. It has some little relation to RNA, which I will begin with, but it's not really biology in this case. I mean, the biology is very real, but the results aren't really biology. Okay, so this is joint work with Manjunath Krishnapur, my colleague at IISc Bangalore, who's a probabilist. And this follows up on work that actually I did a decade ago, and then it was dormant for a while. And then Manjunath and I did this work, and then it was dormant for a while, and then we again got improved results recently. The improvement was actually prompted by Polymath 14, which some of you would have heard of, which was a very enjoyable collaboration on the internet, which involved many of the same things you will see today. But I won't say anything more about that particular thing. So that kind of revived this, and then here's what we're talking about. Okay. So let me begin the story with RNA and ribonucleic acid and secondary structures of RNA, to be specific. So what do I mean by secondary structures of RNA? So these macromolecules, DNA, RNA, proteins that you have, they're all long strands, and they are strands made of specific smaller units. In the case of proteins, these are amino acids. There are 20 of them. Now there are some more synthetic ones as well, but in nature there are 20 amino acids. These 20 amino acids form a strand, and that strand then folds up. It folds up first by forming bonds among itself, forming what's called a secondary structure, and then eventually a tertiary structure, which is a three-dimensional geometric structure. And one of the fundamental problems in science is understanding how the linear sequence of amino acids results in a three-dimensional geometric structure. So input and output are purely mathematical in this case, but we really have very little idea of how this does. Now, DNA, as you all would know, has boring secondary structure, meaning it's not boring, it's a double helix, which is wonderful as an information store. It allows replication and it allows stability of information. But that's about all. On the other hand, the proteins folding into complicated structures allows them to perform the role of enzymes as catalysis. Okay, but here I'm going to talk about neither DNA nor proteins, but RNA. Now, in the original central dogma, as it was called, in the original view of molecular biology from the 50s and 60s, the main role of RNA was just an intermediary. That is, it translated, carried, etc. messages from DNA to proteins. So DNA told you the information, which was like an abstract code, and proteins translated that into a structure, they folded, and they did the real work. Okay, and RNA had that value in between. But then one knows two other rules that RNA has. Okay, so one of which is that there are viruses where RNA is the store of information. There is no DNA at all, including what is currently the most unpopular organism, at least to our species, the SARS-CoV-2, the virus that causes COVID-19 is an RNA virus. So it has no DNA. It uses RNA as its store of information. But also even later it was discovered, that this is not new now, this is 20, 30, maybe even 40 years old, though in more recent times the roles have grown, that RNA can also play the role of catalysis like proteins. So like you have enzymes, you have ribozymes. And in particular, the ribosome is believed, earlier they thought RNA was just structural and proteins do the work. It's now believed that the ribosome, which is where proteins are synthesized, it's the other way around. Proteins are just helpers. The real work comes completely from RNA. Okay, so these were biological preliminaries. I'll just say one last thing about this, which is that today, of course, ribozymes are important, but there is another role. If you go back to the origin of life, in the origin of life, this used to be a mystery that you have a chicken and egg situation. DNA as an information store is like the theory is useless without the proteins doing the real world work. And proteins are useless without the guidance as to what they are supposed to do in terms of what shape they have. And so how would one evolve without the other? But now that we know RNA can do both the roles of DNA and proteins, it is widely believed that RNA was once playing both these roles, that it was both the catalyst and the store of information, and the world was an RNA world. Perhaps it was a somewhat similar molecule rather than RNA, which started and then RNA world took over from that. But nevertheless, so both in today's world and in the origin of life, RNA is quite very important. Okay, and in particular, the catalysis of RNA, just like catalysis of proteins, depends on secondary structure. So understanding RNA's secondary structure is a fundamental problem in biology. Okay, so what we'll be looking at, I'll be precise in a moment, is a simplified model, but not a silly model. It's close enough to the reality of RNA. We won't answer any biological questions though. Okay, so we'll just do mathematics inspired by the biological question, but inspired in a real sense. So let's look at this RNA. So there are two pictures here. This one, the yeast tRNA here that you see, is just a elaborate picture. But what we'll look at in more detail is the helical junction, which is a little piece of it. Let's see how it looks. Okay, so let's take the single strand. And now I'll straighten this out. And we'll think like topologists. That is to say, we don't care about the geometric shape, we care about the topological shape of these. So let's look at these guys. So if you see in the strand, the top strand of this is here and the bottom strand is at the end, final end of this. And this bond here, for example, becomes an arch, which starts here and ends here. Okay, let me try a slightly better arch. It starts here and it ends here. Inside it is another arch. And a lot of them. Okay, but let's turn to another thing, which is, let's look at this region, which is now purple. How does this guy look? Well, it comes soon after this. It will give you arches like this soon after this guy. And let me take orange or something like that. For this helix, oh, I haven't switched colors. Here it is. For this helix, so that's why the term helical junction. You end up with pictures like this. Okay, so you see some nice geometry here. Okay, I've straightened this out and I'm simply noting the bonds. The key point to notice is that they don't cross each other. Okay, that is the one point to notice. The other point to notice, which is basic biology, is almost all the bonds, if I see an adenine here, okay, so suppose this was adenine, then on the other end, I'm bound to have uracil. Okay, uracil plays the role of thiamine in RNA. So ATGC is something we would all have studied in our school biology, and you know this is general knowledge. So you have an AU, in this particular case, the next one is a UA, that it could be a GC. Okay, so most of the bonds connect A to G. Sorry, not A to G, of course, A to U and G to C. Okay, so these are the Watson-Crick pairs. Like in the case of DNA, this would be T, thiamine, instead of uracil. So you have two features here. One of which is that you have this nice non-crossing matching. So you have these bonds, they're non-crossing. And the other feature that you have is that the pairings are of a very specific sort. Adenine pairs with uracil and guanine pairs with cytosine. Okay, and we want to understand the secondary structure. Now, this will not tell you very well because of the approximation, the secondary structure of a specific molecule. It might still tell you something about it. I haven't checked with experimental data, but it's certainly at a conceptual level, if you're thinking of the origin of life or many other functions that the RNA does, a good model may tell you something. Okay, I'm not going to speculate on what it will tell you today. I don't know. Right. But we'll soon move completely to a mathematical model. But first, let me just say what I said earlier. The Watson-Crick pairs, AUGC, are the strongest bonds that you have for an RNA molecule. And stereochemical forces oppose what are called pseudoknots. Okay. So, it's very high. So for example, if I have this guy is blue, and let me again take a straight line. Here, in this case, the blue guy forms some bonds, 3 of them, but let me just draw 2. And let's look at the orange guy here. It forms some bonds. And now you trace, you see you get a blue stretch and then soon you get an orange stretch. So in fact, these cross each other. Okay, this is what is called a pseudoknot. Of course, if you're a topologist, it looks more like genus. And indeed, that's what it is. If you think of these as fat graphs or something like that. So these are pseudoknots. So, but while there are pseudoknots in nature, just as there are wobble pairs, that is pairs which are not AU and GC, but I don't know which are the wobble pairs. I think G and U pair together to form a wobble pairs. So just as there are other pairs, there are also pseudoknots, but both of these are rare. That is to say, to a reasonable approximation, you can think of RNA as folding in such a way that you bond as much as you can without allowing pseudoknots, okay, which is topologically very nice, it's crossings, and where the pairs are all Watson-Crick pairs. So henceforth, we'll take that as our model. Okay, so right now we'll move away from biology. To summarize the biology we have seen so far is simply that RNA is very important. In particular, its secondary structure is very important to understand because of its role in catalysis and so on. And what we have here is a very reasonable model of the secondary structure. Okay, but something which becomes mathematically very nice. So this is what I find attractive about RNA, though I'm not currently working on this very much, which is that something which is biologically reasonable translates to something which is mathematically not complicated. And why I'm saying nice, you'll see soon. I think already this is relatively nice, just 4 letters and a condition that we will like, non-crossing, whether you're thinking combinatorially or topologically. Okay, so here's the picture. Just for fun, this is computer generated. You'll see letters A, U, G, A, etc., etc. So here's the randomly generated RNA. This is not actual RNA, but the same alphabet. And you see matching. The colors will tell you what the bond is, what the left and right hand side are. They have no particular biological significance in the sense that AU and UA have different colors. For just visual effect, you'll see 4 different colors depending on both on what is left and what is right. This is just so this is our model. We have a string and we have things that go from left to right, meaning arcs like this, and they don't cross. So this is a nice picture. This is the picture we want to understand. Okay, so now with this we'll move to a slightly, with this we leave biology. We'll come back to it if there are any questions at the end. Completely, we have a completely geometric topological combinatorial problem where we have a linear string of letters and we are looking at non-crossing matchings with this constraint. Okay, and what is nice is we can make this algebraic. And so if I identify A with alpha and U with its inverse alpha bar, and B with beta, and G with beta, and C with beta inverse. Okay, so now these guys, alpha inverse and beta inverse, are simply formal inverses. Okay, they're not actually inverses in anything, but as you know, you can put these formal inverses in the free group. So what we'll be looking at are, these are letters. You can think of them as alpha, beta, alpha inverse, and beta inverse. And we are looking at words in these letters. So as far as words are concerned, they're just letters. But when we look at them as elements in the free group, which we will soon, you think of alpha cancelling with alpha inverse and beta cancelling with beta inverse. And let me remind you, in the free group, there is no other relation. So then things are very nice. It's not just that letters are matched with other letters, but specifically letters are only matched with their inverses, and there are no crossing. Okay, so let's take the energy. This is a biologically reasonable notion of energy, is the number of unmatched letters. So you want to match as much as possible. You want to minimize potential energy. The potential energy is given by unmatched letters. So given a word, we look at the minimum number of unmatched letters. There are also lots of non-crossing matchings. It is a very rich structure, and we look at the minimum number of non-crossing matchings. Okay. So what properties does this have? So now let's do some work. First point is, this depends only on the equivalence class W in alpha beta. Okay, so let me quickly sketch a proof of this. So what we are trying to say is that if I look at a word, so remember the equivalence here is, if I look at G1 and alpha bar G2, this is going to be equivalent to G1 G2. And this is the basic equivalence. Up to symmetry, I can as well assume that. Okay, so what I want to show is that the length of, let's draw it like this. So this part is G1, and then I have alpha bar, and then this part is G2. Okay, I want to show that this is equal to length of G1 G2. Okay, let me dispose of the easy part first. Okay, so the easy part I'll just use this like a board, is that the length of the when you add this pair, you do not increase the length. So this is actually the easier part, even though the left hand side is a longer word. That is because if I have a non-crossing matching of G1 G2, okay, so let's just take some arcs. Maybe some of the arcs are like this. Some of the arcs may go from G1 to G2. Okay, I may have some arcs like this and some arcs like this. You notice that I can just make the same corresponding arcs. Ignore alpha and alpha bar. If I had an arc that went from this to this guy, I'll have a same corresponding arc here, and then this one, and then this one, this one, this one. And in addition, let me color it in purple, have a new arc which is alpha to alpha bar. So what I did is I simply took the same arcs. By same, of course, I don't mean literally the same indices. I just shifted if you have alpha bar in between, and then added, I don't know if my two pictures are correct. Yeah, but I just added alpha paired with alpha bar. Now, how many guys are unmatched here? It is exactly those that were unmatched earlier. So if these guys are unmatched here, they continue to be unmatched here. Alpha bar are matched. So what this tells you is, suppose I take a non-cross. So remember, the length is the minimum number of non-crossing matching. So I can take a non-crossing matching with the number unmatched being the length. Okay. Yeah.
Siddharth.
Yeah.
Sorry for the interruption.
No problem.
So there are many questions actually. So
okay,
all of them have a common question.
Yes.
What is matching? Could you please define what?
Oh, thank you. Thanks for asking the question. Let me go to this picture. Matching is something like this. Okay. So matching means that I have a word. Okay. Thanks. So I have a word X. Okay. So this has letters, let's say X1, X2, Xn. Okay. So matching will mean M is contained, so it's contained in pairs. Okay. So matching, so let me call this N as 1, 2, N. Okay. So M is contained in n cross n. Literally. Well, okay, more than that. So M is a subset set of pairs ij, and 1 is less than or equal to I is less than j is less than or equal to n. This is a formal way of saying matching means I decide that C here is matched to this G here. This G here is matched to the C that sits next to it, etc., etc. Okay, so if I have a linear sequence here, just of indices of letters, a matching means that I just choose pairs, and those pairs are matched to tell me that one letter is matched to the other, with the condition that the pair should be disjoint. So a letter can't be matched to two different things. The other condition is that a letter can only be matched to its inverse, or in this picture, it will be guanine matched to cytosine and adenine to uracil. So matching would mean that Xi and Xj are complementary, that the pairs are distinct from each other. Okay. And for definiteness, we can say the first element is before the second element. So things are not matched to themselves, they're matched to other things. So matching is a collection of pairs which tell you what is bonded to what. So the picture is what arches, left end of the arch is mapped to right end of the arch. Or if I took a bond in the previous picture, it's here, it is that this adenine is matched to you. So it's where the bond is or where the arch begins is mapped to the arch. Okay. Is this clear or some other questions? Yeah.
Is there any other doubt? Then you can ask to the speaker. Okay. That's what people are saying is clear. Thanks.
Yeah. Okay. Thanks for asking the question. I just forgot that I had not said clearly what matching is. So matching is RNA bonds. In this case, it's arches. Okay. So saying that, let me get back here again. So identifying these with the letters alpha, beta, alpha bar, and beta bar. Okay. Then RNA secondary structures, they correspond to matchings, which means letters matched with other letters. Okay. Such that letters can only be matched with their inverses and there are no crossings. No crossing you can formally define in terms of inequalities, but you see the topological picture also. Okay. And as I said, what we try to do is what RNA tries to do when it folds, and what we are going to look at mathematically as a length is look at all non-crossing matchings with the condition that letters are matched to their inverse. For each one of them, there's a certain number of unmatched letters. And I'll take the minimum of these. The minimum is not unique. There'll be many non-crossing matchings with that. But the number of these letters, what is the minimum number that are unmatched? Okay. So if you want, while we are here, let me just put an example in this guy. So for example, if I had a word alpha, beta, and then I had alpha bar and beta bar. What is the best matching I can find here? Well, I can match alpha with alpha bar, for example. But now beta and beta bar are left unmatched. Okay, that's because if I try to match them, I'll be forced to have a crossing. Otherwise, I could match beta and beta bar, and then alpha and alpha bar will be matched. So the length of this, as I'm calling L in the next slide, is 2. Because the minimum number of uncrossing, non-crossing matchings is, minimum number of unmatched letters is 2. Of course, if there are more alphas than alpha bars, for an elementary reason, some alphas have to be unmatched. But this is an interesting example because it's the non-crossing condition that forces things to be unmatched. And this is what you immediately realize is a little bit of a subtle notion, this number of non-crossing matchings. It's the non-crossing condition is a subtle topological condition, if you wish, but it's a subtle condition. Okay. So again, now to come back to this, okay, what do I want to show? What I want to show is in the free group, okay, the condition is, let me redraw this and make it, let me make this in 2 lines. Okay, I was trying to show this in just 1 line. Okay, so this is a short lecture, so please feel free to interrupt. So what I want to show here is that, so G1 alpha bar G2 is equivalent to G1 G2. This is true in the free group, and this is the only relation in the free group. So given this relation, what I want to show is that the length of G1 alpha bar G2 is equal to the length of G1, G2. And of course, a common way of showing such inequalities is to show two equalities. And let's show two equalities. Okay. So let's take first of all length of. Let me take a line here. Okay, let me be lazy and draw the other line here also. Okay, so what did I have on the left hand side? Okay, so let me, that line is longer. Okay, so that's all right. So if I have G1 here, and then I have these 2 points, alpha 1 and alpha 2. And then here I just have G1, G2.
Yeah, so there is one more question.
Yeah.
So could you please, could we have a formal algebraic definition of a crossing?
Formal algebraic definition of a crossing. Okay.
Yeah.
So let's do it here as an exercise. Let me find, I know where I'll find. So I've kept blank paper at the end for these questions. Okay, let's just work it out. Here we are. Okay, here's a line. Okay, so I have I here, I have J here, I have K here, and I have L here. Okay, so crossing means we have pairs IK and JL in the set of all matchings. Okay, so IK and JL, and they cross such that I is less than J is less than K is less than L. So here's a formal algebraic definition of crossing, if you wish. So crossing is a set of pairs. So M, if we want to be formal, let me write what M is a subset of. M is a subset of all pairs. Let me not use I and J, which I've used, AB, such that 1 is less than or A is less than B is less than N. Okay. So M is a subset of these. So these are matchings. We have the additional condition. So we require XA is XB bar. Okay, so we require the letters to be inverses of each other, but that has nothing to do with crossing. So crossing is a geometric condition. This is the condition letters paired with their inverses. Okay, so here's the formal definition of crossing. You simply write this as this inequality. Yeah, is that clear, or any other questions?
No, I think it is clear.
Okay, yeah, so thanks for all the questions. Yeah, I've kept the material. Okay, so back here, let's try to see. We want to show that L of this, which inequality were we in the middle of showing? So the easier inequality is actually that the longer word is shorter. Okay, so somewhat, so that it is, yeah, that's right. So remember, L means that there is a non-crossing matching with exactly these many unmatched. Okay, so let's draw such a non-crossing matching. It might look something like this. Now I've drawn a slightly simpler picture than I did last time in some sense. Okay, so you simply find the corresponding non-crossing matching here. This one will jump over alpha beta. Oh, the picture looked more like this. Like this. So you see, you can translate the picture on the right, non-crossing matching, to that on the left, simply by shifting indices. So whenever you have an index which is either I or I plus 1, whatever the index of alpha. Oh, I've written alpha 1 and alpha 2 here because of course they have to be inverses, which without loss of generality are alpha and alpha bar. There are 4 cases, and then we add one more matching, one more pair. So our matching consists of the old ones shifted and the new ones. And now obviously something is unmatched here means it's already unmatched in the same place here. Okay, alpha, the new letters are matched. What this tells you is that the number of non-crossing matchings on the left, unmatched letters on the left-hand side is less than or equal to the number of unmatched letters on the right-hand side, which was chosen to be the length. And so maybe there's a way you can do better than this. Okay, so all you know is the length, which is the minimum, is less than or equal to these. Okay, so now let's try the other way around. So again, yeah, so I was a little quick through this, but okay, so let's take the length of, okay, this time I'll make sure that I have space is greater than or equal to length of this. This is more complicated. Let's get some lines here. Okay, and as you remember, let's break it. And here we break it like this. Okay, let me break them closer to each other. Okay, so what this means is this guy is G1, this guy is G2, this is G1, and this is G2. And here we have alpha and alpha bar. Okay, and what I want to show is that this length is greater than or equal to these. And this actually has a subtlety, because if you look at a non-crossing matching of the left-hand side. So on the left-hand side, we have a non-crossing matching. So number of unmatched letters is the length. That non-crossing matching may have some things like this, and then maybe something like this, and maybe something like this. But crucially, alpha and alpha bar may be matched to some other letters. Okay, there are different geometric configurations, but I'm just sketching an argument. It's easy to formalize this. So alpha and alpha bar may be matched to these letters. So if I delete them, what happens is that these two matchings go away. And so this guy and this guy, if I just simply delete alpha and alpha bar, I'm be forced to delete things. So two additional guys end up being unmatched. And this is not good. So now then what has happened is those that are unmatched on the left hand side remain unmatched, and then two additional guys remain unmatched. Alpha alpha bar have gone away, so their matching doesn't matter. Well, the trick here is that you can rewire. So if I see these two arches, then what I can do is I can go from here like this and like this. And if you wish, I can think of alpha and alpha bar as being paired to each other. So given a non-crossing matching on the left-hand side, I can change it. So alpha, alpha bar are paired with each other without increasing the non-crossing matchings. Okay, there's a couple of other cases, but those cases are easier, where one of alpha and alpha bar is not matched at all. Then you can simply delete. But if both alpha and alpha bar are matched, you have to do this slightly elaborate, you have to do this rewiring. And this rewiring, excuse me, will tell you so that you have a matching. So alpha and alpha bar are matched, and the number of unmatched letters is the same as the length. Once I have this, I can just delete the red arc, and sorry, so the orange, now these two letters are paired with each other. They went from being red to orange, and there is an orange arc connecting them. Simply delete alpha alpha bar and the red arc, and now the number of unmatched letters on the left hand side is the same as the number of unmatched letters on the right hand side. So that shows this inequality. Okay, so this was a crucial part of showing that this is well defined. Okay, so what we showed here is that this is well defined. Namely, that if two words give you the same element in the free group, that is, they're related by cancellation. By the way, alpha bar is alpha inverse, let me remind you. So if they're related by cancellation, the length does not change. So this length is actually a function on the free group. What I have not told you is what I mean by saying it's a length and proving that it is a length. That we'll come to next, because that will be also an ingredient of that will also be a crucial in the proof of the main result. Okay. Also, conjugacy invariance. By the way, conjugacy invariance, the picture is very similar to the picture that we have for. Sorry, I'm searching for my pen. So what does conjugacy invariance mean? It means I have a letter G here, and then I have alpha here, and then I have alpha bar here. So this is actually just like alpha and alpha bar next to each other, except cyclically. So exactly the same proof will work. So you can take it as an exercise. If you understand this proof, that is to say, you can find a matching where alpha and alpha bar are paired with each other by rewiring. So it's the same proof, except that here they're next to each other, they're at the other ends to each other. What I have not established is that it's a length, and I haven't even told you what I mean by length. Okay, so a length function on a group must satisfy the following. This is more or less like a norm, except for abelian groups. The length of the E, the identity is 0. Okay, here that is very easy because E is the empty word. Take the empty matching, nothing is unpaired. Length of G inverse equals length of G. That is again easy. Just make a mirror of it. Okay, the third one is not hard. So let's look at this. Namely, if I have G and H, and if I have a non-crossing matching for G, it may look like this, and I have a non-crossing matching for H, just put them next to each other. You get a non-crossing matching for GH. The unmatched letters are those that are unmatched in G and those that are unmatched in H. And so the number is going to be the sum. So you take one's optimal one on the left, optimal one on the right, just next to each other. The final thing is often trivial, but in this case, this is also a lemma in the proof of the main result. I haven't told you stated the main result yet. So I'll spend a couple of minutes saying what this is. That if the length is 0, then G is E. Okay. So recall what the length means. The length being 0 means. Length being 0 means that there is a non-crossing matching with nothing unmatched. Every letter is matched. Okay, so here let me draw a little bit of a non-crossing matching just for the sake of doodling. But all the letters are matched here. Okay, so there is nothing other than the end points of these arcs. Well, what we'll do is we'll look at something like this, which is an innermost arc. Now, because it's a non-crossing matching, there cannot be a letter in between here, because if there is a letter here, it'll have to cross to match somewhere else. Okay, if there are two letters here matched with each other, then this arc is not innermost. So you can look at the innermost arc. Formally, you just look at an arc so that the difference between right endpoint and left endpoint is minimum. This is a finite set of differences. You look at one which is minimum and claim that the left endpoint and right endpoint for such an arc should be next to each other. But also remember they are inverses of each other. So they must be of the form alpha alpha bar, or maybe for a change, maybe they were beta bar and beta. Okay, so look at an innermost arc and then you have beta bar and beta. So they can cancel and you induct on the length. And from this, you can show that you have a series of cancellations. Your non-crossing matching will give you a series of cancellations, which will take you to the trivial word. Okay, so if the length is 0, that is, if there's a non-crossing matching with nothing that is unmatched, then it has to be a trivial element in the free group. Okay, this will come later. That's why I spend some time proving it right now. Okay, this will be one of our key lemmas. Lemmas for what? Okay, so this slide is a digression. Yeah, question?
Okay, so
yeah,
sorry, there is one more question.
Yeah.
So why are we particularly transfer the model of RNA in two-dimensional setup? Why not in three-dimensional to avoid such crossing setup?
I did not actually assume it's two-dimensional. All my pictures are two-dimensional, but if you write it as a formula, it's a set of indices. Okay, and the condition of non-crossing is so the condition of no pseudoknots becomes, if you wish, a two-dimensional non-crossing condition. Okay, so pseudoknots translated to two-dimensional non-crossing, and that is nature, that is biology. It's correct biology that there is stereochemical resistance to pseudoknots. As I said, it's an approximation. There are a few pseudoknots in an RNA molecule. Many of them have none at all. Some RNA molecules have some pseudoknots, but it's a rather good approximation to say no pseudoknots. That just translates to this. It is not that I chose a translation. I chose the approximation, but it is the strongest positive force and the strongest negative force was my approximation. It just mapped to this. Yeah.
Okay. Okay. I think that answers the question.
Yeah. Yeah. Okay. So to go on, we know this is a length function. In particular, if the length is trivial, it's a trivial word in the free group. And my next slide is a bit of a digression. This is what I did many years ago. So what I call Watson-Crick length is, so it has some very attractive properties here. So I defined it explicitly with non-crossing matching, but here are two algebraic definitions of it. So you can go from, we started with RNA, we went to combinatorics and geometry. Now we are going to actual algebra. Let's look at lengths which are conjugacy invariant. So length of GH, G inverse is the same as length of H. Okay. and so that the generators have length less than or equal to 1 or equal to 1. Both will give you the same result. Look at all such lengths and look at the largest such length. This is a very Gromov style of defining things, that you look at the largest length. This turns out to be exactly the Watson-Crick length. I'm not going to prove this today. We can discuss later if you want. It's in these papers, and it's the maximum among such length. It also has another purely algebraic definition. So the generators, of course, alpha, beta, and their inverses generate the free group. But I can look at a bigger generating set, which is not just alpha, beta, but it's conjugates as well. Okay, and then I look at the word length, which is how many generators do I need to write a given word. This is less than that in the original generating set because we have more generators, but it is a length. And this L Watson-Crick length is also exactly the word length in this generating set. Okay, 1 and 2 being equal, you can see, but the nice thing is these two purely algebraic definitions, which by the way are also related to what's called the edit distance, the equality between these two. I should thank Apurva Khare, because of him I know some the relation between 1 and 2. It's well known. It's not that he discovered it, but it's thanks. I don't know if he's in this talk, but if he is, yeah. I know these two are equivalent because of this. But so you have two algebraic characterizations of the previous length as well. Okay, so what we are studying is a mathematically very natural object. It has some nice geometry. Okay, so now we want to find lower bounds on length. That is the key thing. And there is an obvious lower bound, which is your abelianized. Namely, if there are more alphas than betas, or than alpha bars, or more betas than beta bars, or the other way around, okay, then you will end up with some alphas not paired, because alphas have to match to alpha bar. This is kind of obvious thing. And what I worked on long ago, and I'm not going to say anything more about it today except to state this, is that to me, this looks just like linking numbers in topology. Okay, it does. It is formally the linking numbers. And Milner, in his both undergraduate thesis here, constructed things called Milner invariants, and he has further things in his PhD thesis, where you look at not abelianization, but extend linking to higher linking. Okay, which is you look at quotients in the lower central series. So in particular, if you look at the first term in the lower central series, you get a number associated to this. This is also geometrically nice. It's an area, what I call Heisenberg invariant. Okay, so that F over F3 is a nice group in particular. And this is a story I won't go into today any more than this, to say that I did this long ago. It is interesting. There are interesting things you can do with the length, simply from an algebraic viewpoint of view. Okay, and there are people who work on conjugacy invariant lengths, including Arpan, whom I know is there. And they're very non-trivial things, relations to stable commutator length and quasimorphisms and so on. So here we are looking at something which is nice mathematically and even studied mathematically. Okay, so let's go to the question of the day. Okay, in 15-20 minutes, I will try to explain. Here's the question of the day. This is joint work with Manjunath. I started discussing with him soon after he joined our department, actually, and then it lay dormant for a little while. So here we are. Let's take a random word in alpha, bar, beta, bar, by which I mean alpha, bar, beta, bar each have probability 1/4 of being a given letter, and they're all independent of each other. How does L behave for a random word? Well, not a specific random word. How about the average? So let's look at all random words of a given length. Look at the average. Of course, these words are getting longer. So we want to look at average normalized by n. This means this is the proportion of unmatched letters. If I take a long word in the free group, or RNA if you wish, and you take the best matching, what is the behavior of the proportion of words? Well, there is something called Fekette's lemma, which tells you that because L bar n is what is called subadditive. Okay, so let me just write down that formula. I don't actually need this. So what we know is L bar n, n1 plus n2 is less than or equal to L bar of n1 plus L bar of n2. And the reason for this is if I took a random word here, I could take a random word here xn1, and I could take a random word here xn2, and I put them together, I get a random word of length n1 plus n2. Okay, and triangle inequality, or more directly looking at non-crossing matchings followed by non-crossing matchings here, will tell you L bar of this random word is less than or equal to L bar of those two. Okay, so this is subadditive, and if it's subadditive, we know this limit always exists. So that's very well. The crucial question is, what is the limit? Specifically, is it a positive number or is it 0? And in probability, it being a positive number has strong consequences. That is, asymptotically, is the number of unmatched letters or fraction of unmatched letters, is it asymptotically a positive number or is it 0? Okay, so this is the question that we are going to address today. Okay, so here's our theorem also. Yes, so namely that if I look at rho of n, which is this average, it converges to lambda 2. The 2 is because this is the free group on 2 generators. The same result, as I'll say in the end, works for any free group. Finitely many generators at any rate. So sorry. So if I look at rho of n, it's this average, it goes to a positive constant. Okay. So first of all, the average number, to show that the average number is positive, it's bounded above by, you can see, n lambda 2 times probability of where is my highlighter? It's bounded by this. This is elementary. And so you have, so it's enough. So let's take n to the other side. So expectation of this by n is greater than lambda 2 times this probability. Okay. And so it's enough to show this probability goes to 1, or equivalently the probability that, now the final statement you can concentrate on if this is not obvious to you. The final statement says that if I take a word of length n and think of lambda 2 as 1 in 100, it says what you have to show is just the probability that at most 100th of the letters are unmatched. Very few are unmatched. Just 1% of the letters of unmatched goes to 0. If for any lambda 2 you can find this, you know expectation is greater than or equal to lambda 2. Okay, so this is the first reduction. So we have to bound the probability that a given random word has in its optimal matching a very tiny fraction that is unmatched, where that tiny fraction is the fixed number as n goes to infinity. We'll prove this by counting words, okay, that have non-crossing matchings with only a small fraction unmatched. Okay, let's get to counting. So first observation, if you have the right parity condition, so m is the number of matchings, okay, then r, which will be the number unmatched, n minus 2m. So if you have a non-crossing matching with at most r unmatched letters, if there are at most 100 unmatched letters, maybe there were 96, then you can find another with exactly 100 unmatched letters, throw away a few matchings. Okay, simply by dropping a few. This of course doesn't change the parity. That's why I stated that carefully. That is, if you had 97 unmatched letters, then you would get 101 unmatched letters. So your parity cannot be affected, but parity is just determined by n. So as long as, because the number of matched letters is always even, but as long as your parity is correct, if you have a very good matching, just throw away a few pairs and you got this. So what it suffices to show that if m is this appropriate quantity, that is the number is almost everything is matched for some appropriate m, and r is the n minus 2m, then the fraction of words with non-crossing with r letters unmatched is small. Okay, so again you have 1,000,000 letters and your n is say 1,000,000, r is 1,000 because my lambda 2 was 1 over 1,000, let's say. Then what you want to show is that the number, the fraction of words with matching with only 1,000 unmatched is small. There are not too many such words. Okay, so we'll find an upper bound on this. So the n of nr, which is number of words with r unmatched letters. And just remember the total number of words is 4 to the n. So n of nr should be small compared to this. Okay, so let's see what this is. So here is an idea. Okay, so we tried various things, and this is one way of, actually there are other equivalent combinatorial arguments, but this is one way that works quite nicely. Oh, sorry, I don't want to highlight it. So let's look at our word x. Okay, so this is x. Now some letters are matched. and some things are unmatched. Okay, and there'll be segments that are unmatched. So what I'll do is the matched letters, this guy, this guy, this guy, this guy, take them in the order they are here. Okay, and they constitute Z. These guys continue. So this guy is Z1, Z2, Z3, etc. And I haven't marked them here, so let me mark them. There are certain letters that remain unmatched. Maybe there's one here, maybe there's one here, maybe there's nothing there, maybe here. Okay, so the purple guys constitute Y. So this guy is Y1, Y2, etc. So this is some Y. We know the lengths, by the way. So the number of unmatched letters is R. So Z has length 2m, Y has length R. Okay, so I'll just look at the letters that are matched and the letters that are unmatched. They both form subwords, and I'll take them in the same order. Okay, so Z forms, so these are two things. And the key observation is Z forms the trivial element. Why? This is what I emphasized earlier, right? So Z has a matching with nothing unmatched, because I just separated out the unmatched things into Y. So it represents a trivial element in the free group. Okay, that's what we showed when we said that this was a length. So now let's count these. So when I have a word X with a non-crossing matching, okay, so if it has R unmatched letters, so this is determined by, so you want to determine this word. If I know Z, I know Y, and I also know which indices are in Z and which indices are Y, then I know the letter X. I can rebuild it from these three pieces of data. So I know the word Y, I know the word Z, and which indices are unmatched. The remaining ones are in match. So if I know this triple, Y, Z, and R, and there are indices, then I know X. Okay, so now some simple combinatorics. So what does this tell you? What is, I hope I have a pen. Yeah, let me make this guy black. So the choice of R indices out of N, of course, we learn in school is N choose R. Word Y we have no control over because these are unmatched, but it has length R, so there are 4 to the R. Okay, and what about Z? I'm just giving it a name. I'm calling it T2M. This is a word of length 2M, which is a trivial element in the free group. And so what we are left with is to count T2M. Okay, so that is the key point. And the warning here is N choose R is quite big. I mean, it's exponential in N. So it's the evil combinatorial term. We need to control T2M well enough to defeat this evil combinatorial term. Okay, so let me give a quick heuristic. What happens here? Okay, so this is a picture. So we can think of trivial words in the free group in terms of random walks. This is what's called a Cayley graph of the free group. Namely, if I start at the origin, the edges coming out of this correspond to A, B, A inverse, and B inverse. So a trivial word could be something like A, B, A inverse, A, B inverse, maybe A inverse, A inverse. Okay, so a trivial word in the free group, the one that I wrote just now was A, B, A bar, and then A, and then there was a B bar, and then an A bar, and an A. And then you'll see these two cancel with each other. Let's draw a non-crossing matching if you wish. These cross cancel with each other. Just keep canceling and you get the original word. Okay, so a trivial word in the Cayley graph, this is pretty much a definition of a Cayley graph, is exactly a random walk. So this is fine. These are paths, and this is a random walk. And the random walk takes you away or towards the origin. And the key point, and this is a key idea in a lot of results on negative curvature, not just with groups. In fact, the first important result I know of this nature is one of Dennis Sullivan. Mike Anderson gave a different proof at the same time of the result that manifolds with negative sectional curvature, universal covers of such manifolds, have harmonic functions on them. And Sullivan's description was that a string of results he had were all based on one simple idea. Namely that suppose I'm here and I take a random step, then 3/4 of the time I'm moving away from origin and only 1/4 of the time I'm moving back towards the origin. So this is not a symmetric random walk. You're not just going left or right. You're much more likely to go away from the origin than come towards the origin. Okay, so this one is not recurrent. It's not even ergodic. It has a Poisson boundary. There's a lot of interesting thing here. But the simple point is that you tend to run away from the origin. So the chance of returning is small and exponentially small. Okay, this can be explicitly counted more or less, but there's a twist to the tale. So given a path, we can count the number of paths. This is what's called a Catalan number. And the probability is, remember, a path of length m has m steps to the away from the origin and m towards the origin. So it's more or less the probability of a step away from the origin is 3/4 and towards the origin is 1/4. If this was not just more or less true, if it was true, you could get an explicit formula. But the catch is that if you are at the origin, you are guaranteed to move away from the origin. So there the probability becomes 1. Okay, so this was a heuristic to tell you that because of your tendency to run away from the origin, the fraction of the paths that return to the origin is bounded. Okay, now so to turn this into a complete proof takes work, but this work was done long ago by Keston in the 1950s. Okay, so here is the result. So let tau k be the proportion. So the proportion of random walks that end up at the origin, which is to say represent the probability that a random word of length k represents the trivial element. By the way, if k is odd, this is 0. Doesn't matter. And Keston showed that tau k is less than or equal to square root of 3/2. Here's the result for all free groups, free group on 2 generators. So let me just highlight the things we want. This probability is less than or equal to root 3/2 to the k. Okay, and as a result, the number is of course root 3/2 to the k times the total number 4 to the k. Okay, there's a little bit of an outline. Keston doesn't state it like this. What he shows is the limp soup is root 3/2, but actually log of tau k is subadditive. So from that you can deduce this. I have a little bit of an explicit deduction here, but let me skip that. So where do we get? Okay, we get with a calculation. Just a couple more slides and then I'm done. So here is a calculation. Remember, so I've changed notation to the notation in our paper. So I'm letting W and delta be N and R. Delta is now the proportion. R is N times delta. Okay. So what is W and delta? Remember, it had an N choose R combinatorial term. 4 to the R, this was unmatched letters. And then this was TK. Okay. So in terms of what we called this earlier, sorry, T2M. This was the T2M. And 2M is just N minus R. Okay. So T2M was exactly this, which we can put. So now I'll pull out all the 4s here. And so we get this. And now we use a bound on N choose R. This is a Chernoff bound. You can use more elementary bounds. You would all have heard of Stirling's formula. So this is of that same nature. This is an elementary bound. N choose R is less than exponential times something in terms of delta, which is delta is, remember, R over N. Okay, it grows at the level of N times delta log delta. If you want to get a rough idea what this is true, use your Stirling's formula, which will tell you N factorial is about N to the N plus half e to the minus N. Feed that in and you'll get something of this kind. Stirling's formula is an approximation, not a bound. And this is slightly better than what you get from, well, not better than that. So it's of that nature. Okay, so we don't have anything really beyond that. Okay, so now we are in good shape. What do we know? N choose R. So this quantity here will go. So what is the probability? So probability, we get rid of this term. So when we take probability, we are quotienting. We just have N choose R, which is this term, and root 3/2 to the N minus delta, which goes here. So we regroup this and we get a probability is bounded by exponential of this quantity here, which we just bounded, and log root 3/2. This is the Keston bound on the number of paths. Okay. So now with this calculation behind us, let's try to understand. What do we want to know? We want to know whether this probability goes to 0. Well, it's an exponential. When does an exponential go to 0? When the exponent is negative. Okay, if it's positive, it goes to infinity. If it's negative, so it's negative when this happens, minus delta log delta. And for delta small enough, we can show this is true. In fact, we can have a explicit bound, which is lambda 2 is 0.03. Okay, so since it's been an hour, I'll skip the next slide, which is we can refine this bound a little bit by just, let me just say, I chose YZ arbitrarily. Instead, we make a canonical choice of Z, which is, and then our choices drop from 4 to 3 for Y, for most of Y, which looks very nice, but the numerical bound is only a very slight improvement. So since it's just past 6, let me skip the details of this. Let's just conclude. So here are my final remarks. First, our proof works for all non-abelian free groups. There's nothing special about 2. RNA corresponds to 2, but the mathematics is fine for all free groups. And then this is an additional result. I won't go into details of this. In fact, you should better ask Manjunath if you want details of this. It's not just that the average is lambda 2, but standard probability techniques will tell you that most words, that is all but an exponentially many, the fraction of unmatched letters is actually very close to lambda 2, which is not 0.03. That's a lower bound for lambda 2. That's a true value, which may be 20% or whatever else, 0.2 or something like that. That's what experiments suggest. But what you can deduce is that for most words, the minimum number of unmatched letters is actually close to some lambda 2. Okay, and the final 2 remarks are just because, given the context, I thought let me try to look at this slightly more generally. So I like this result, but it's special to free groups. Is there a more general question at least we can ask? Well, remember, we can think of the length as being the word length in generators and their conjugates. This is an infinite generating set. Now, as is easy to see and well known, if I took 2 finite generating sets for a group, the lengths in the 2 of them are comparable. They differ by constants. But of course, lengths in infinite generating sets are not comparable to lengths in finitely generating sets because the generators have length 1. But if you took these nice infinite generating sets, which is conjugates of your finite generating set, then the ratio of length here is generically bounded. Okay, this is true for free groups. So let me just end with a question. For what groups does this hold? Okay. By the way, this is a loosely formulated question. Don't take it from me that this is some kind of expert view that this is important or anything like that. But I thought, let me try to end by saying, well, for all free groups, we have this result. These are techniques. Okay. But what would it be for all groups? There are other questions one can ask, but let me just end with this. And I'm ready to answer any of your questions.
Okay, Siddharth, thanks very much for this wonderful lecture. Now, as I can see, there are already lots of questions. So let me ask one by one. So the first question is, can you suggest some paper or books where I can find more ideas about this topic?
Well, I don't know about which part of this topic. This spanned, I think, several fields. So I assume you mean, so if you want to see this proof, Manjunath and I have a paper. And it's on the archive, but there needs a small correction had to be made. The small corrected version will go on Monday on the archive. It's already posted, but archive doesn't post on the weekend.
And,
so after, yeah.
And
but if you want,
question,
more general background, maybe geometric group theory, there are many books about it. But this is, as I said, this is just this is a mix of many things. Yeah.
The second question is from these final remarks. What do you mean by most words?
What do I mean by most words? Okay. So I mean that you pick a random word, okay, and you have lambda 2. Okay. So then, so I have a, so what do I know? I know that x, so I have the quantity lambda 2, let's say. Okay. So I'll take an epsilon. So I look at probability that, let me take the length of xn by n, and I think you have a square root term. So suppose I take the probability that this is the fraction of unmatched words. Sorry, let me put my n a little better. I have this fraction of unmatched words minus lambda 2. That this is big compared to, I believe it's 1 over root n, or in fact epsilon over root n. For any epsilon, if I look at the probability of this, this is exponentially small, is less than exponent of something like that. Okay, so for most words, as you look at the fraction of words where the number of unmatched pairs differs from lambda 2 by a largish amount. Okay, large compared to square root of n, and need not be large compared to n. Then this, and in fact, Manjanath conjectures into the 4 decay you have, then this proportion is small. Yeah.
Okay. So Gianluca, does it answer your question? I think it answers the question. Now there are more questions, so maybe it's a good idea if the speaker, if the concerned person can ask it himself or herself.
Yeah, I think now you
that would be nice. So I request the organizer perhaps to unmute the person who wants to ask. So raising
Dr.
hand is a
Gadgil,
good option.
my question is, could you mention that this is what everyone is unmuted now?
Yeah, I think too many people are unmuted.
Yeah.
I was asking, you said that
Yeah, now we can ask.
Yeah, go ahead, please.
Please unmute yourself and ask the question.
Okay, I was saying that you said that this the length function is the maximal length function on the free group, which is conjugate invariant. So what would the maximality here be like? So what is the order in which it is maximal?
Yeah, that's a very good point. Okay, so there is a partial order, and this is an utterly naive partial order. Okay, so suppose we look at length functions. Yeah, so this is Gromov's green book, by the way, is a source for lots of these things. So some of the ideas go before that. So I'll simply say L1 is less than or equal to L2 if for all G in G, L1 of G is less than or equal to L2 of G. Okay, so this is a naive partial order. It's very easy to define this partial order. What may be less obvious is that there is a maximum because it's clearly only a partial order. What happens if every length is less at some point and greater at some other point, etc. Okay, so the general trick is that you look at the set of all length functions L, which map G to whatever it is, 0, infinity. Okay, so L is a length with all the properties, and you let length of alpha 1 is less than or equal to length of 1, etc. You have these conditions. So you look at the set of all these lengths, and for each point G, you define L max, let's say, of G as the supremum of L of G, where L is in this scribble, sorry, where L is in the script L. Okay, and this turns out to be maximum. So the maximum exists. This is bounded by triangle inequality and so on. Yeah, so maximum is with respect to this naive partial order, where it means point-wise maximum. This is only a partial order, but there is a maximum.
All right, thank you.
Okay, so here are actually two questions of the same nature that I would like to combine. So the question is, does this result hold for symmetric group of n letters and for the small cancellation groups?
Okay, so with symmetric group of n letters, it is a finite group. So if you're talking about things being comparable, nothing will, I mean, everything will hold for rather trivial reasons. Okay, so this result, yeah. So I'm taking this geometric group theory view that you take things as comparable. Okay, but as I learned from this really nice talk of Arpan, that people do work on effective bounds in finite group case. You may want to refine things and may be interesting. As far as the question is concerned, I just loosely formulated it while making this talk. I really have no idea whether it holds or not for, well, I mean, there are examples like abelian groups where you can work it out in 2 minutes, but for any non-trivial examples, I just loosely formulated it. maybe people have worked on it. Maybe there is a literature which knows this, or there's no promise of anything that it's unknown or anything like that. But I don't know any case other than the free group. I mean, I've been working on the case for the free group, both as an interesting geometric combinatorial problem and its relation to RNA. But yeah, so I don't know. Yeah.
So
But it's not obvious. Huh? Sorry.
Yeah.
Yeah. Are there? Do you see any mathematical constants down the road, and do any of them have an implication for biologists?
Yes. So does this have implication for biologists? Actually, this is
No. Wait. The first question is: do you see any mathematical constants down the road?
Constant?
Mathematical constant.
What do you mean by mathematical constant?
So E and pi are very famous mathematical constant.
Do I see a mathematical constant down the road?
Yeah.
Well, I mean, all sorts of these limits give mathematical constants, like lambda 2 is a mathematical constant, but I don't think it's an important mathematical constant. Yeah. So, I mean, any quantitative result with an estimate will give you, I mean, there is a fraction, so it is a mathematical constant. It is interesting that it is positive. Actually, you have a point there, because you do have phase transitions in groups and so on. So where the phase transition occurs is often interesting, though there it is often at half or such things. So similarly, you have a number, but I don't see, I mean, I don't think something like lambda 2 is an especially important or interesting mathematical constant. Yeah. And
any implication for biologists?
Implication for biology of a particular mathematical result, no, this result, but this result, by the way, sorry, let me say, it has a meaning in RNA. Okay, so the meaning is the following, that if I take a random long strand of RNA, okay, the question is whether you need to have folds which go a long way from here to here. Okay, so I'm drawing these non-crossing matchings because I can't draw RNA folded. Do you have bonds which cause parts of RNA very far away to fold from each other, or all the foldings are only very local? So what this result tells you, because you converge to a positive constant and hence you have this concentration result, what this result tells you is that you can have only local foldings, and that gives you something that is near optimal. So there is a meaning, at least in terms of RNA behavior. Okay. On the other hand, if you want to apply it to biology, you have to really start with biological questions about RNA. Yeah. So when I started, I did consider certain things. For example, one important thing is allosteric structures, and these things illustrate them nicely. So allosteric structures are structures where you have, so this is a concept for proteins. I mean, it works for RNA as well, where a protein has two different local minima, which are very different from each other. So remember, a protein, as I said, it starts as a line and then it folds. So it can fold in one way and it can fold in another way. And these two are very different folding from each other. Okay, so these are called allosteric structures. This, for example, is very important in real life. So what's called mad cow disease, bovine spongiform encephalopathy, and various of these prion diseases, as they're called, are because our proteins in the brain, they switch from one configuration to the other. And what causes it is if that you have, there's an autocatalysis. Once you have a few proteins that are what are called misfolded, folded in the wrong configuration, it causes slowly the other things to misfold. And this disease progresses over 30 years and so on. That's why it has remained, it never got selected out, because it's a very slow acting disease. They were called slow viruses, but they're not viruses. So there are allosteric structures, autocatalysis. Yes, so there are phenomenon, and as I said, you want to try to understand the origin of life. You want to understand what properties of RNA facilitate them. So no particular mathematical result will straight away give it to you. What is true here, and that's why I worked on it, but over a decade ago at some length, then I moved to other things. I moved to other things for a certain reason, which I'll come to in a moment. What is nice is that there is actually an attractive mathematical model which is reasonable for biology. So there may be lessons for it. So if you're an experimentalist, you understand this and you want to think about free groups and you want to conduct an experiment, you can look at RNA and ask how random is it from this point of view. So you take actual ribozymes in nature and see whether they are somehow atypical in a way that you can capture in their words in the free groups. It is possible. You have to make a connection with experiments. I don't know the answer. In general, the larger lesson is, of course, two larger lessons. One of which is that you should, of course, understand biological questions and understand the biology well. The other larger lesson, though, which is why I moved away, is that especially true with protein foldings, you see, biomolecules are a product of evolution. So they're like engineered things. So you don't take a car and study it mathematically. I mean, or even this computer on which I'm lecturing. If you try to have a mathematical theory, when designing it, you can put in the mathematics. But if it's already built, you don't try to reverse engineer with a mathematical theory, because a lot of things are optimized to work in nature. And they're also local optima. So because of the role of evolution in biology, one must be quite careful about using this kind of toy mathematical models. That is not to say that they're not useful. It is just that they should be used with due care and due humility. Okay, so yeah.
Yeah, and thanks for this. And since you mentioned phase transitions,
yes.
Could you state the algorithmic complexity of finding out the Watson-Crick length of a given string?
Yeah, so that is actually it's a very good question. So I do find it in my in the polymath project, and when I plotted these things and so on, I did compute it. For example, this was an explicit computation using a simple recursive method. But this recursive method grows exponentially. Okay, and as far as I can tell, and this is Manjunath's view also, I don't think there is a simple way. Okay, so there is the usual problem. We don't really know how to prove things are hard. If P is NP, everything could be polynomial. So so on the one hand, okay, there are a few interesting things one can say. You see, so let us first formulate the correct algorithmic question. So the correct algorithmic question is to ask if the length is bounded above by a certain number. If you can find the upper bound, then you find the best one. Okay, so you want to know whether the length is bounded above by a certain number, which is asking whether there is a non-crossing matching, which leaves only, let me be concrete now. Let's give some concrete numbers. I have a string of 100 letters. I want to know if there's a non-crossing matching so that 90 are matched, only 10 are unmatched. You see, this is NP, because the way I can prove there is such a matching is simply exhibit it for you. I can give you this picture and you can just check letters are matched with their inverses, count those that are not matched. Okay, so this is NP in the sense that you can give if an answer, once you have the answer to an upper bound, you can prove the upper bound. Okay, I don't know if it's NP complete. Perhaps it is not. Perhaps it is even. Perhaps it is in reality, but it is just very hard to prove because this is a bit of a rigid problem. So yes, so the algorithms that I just use, I mean, so in real life, sometimes things are not so hard, even if theoretically they're supposed to be hard. That is, you can do useful things, and I have done useful things just calculating many of these things. They have not just here, they've resulted in a different theorem and so on. So sometimes things work in practice, even if theoretically they're large, but then they'll blow up for large n. So in practice, when I was trying to find the proportion, it does start blowing up when you have 40 and so on length things. The naive algorithms are exponential. It is NP. So NP implies exponential anyway, at most exponential. I don't know if it's NP complete. The problem, again, let me just say it briefly. So the problem is if you try to think about how are you going to find a matching, okay, then let me yes, this is an interesting question. I'll answer it here. So how are you going to find a matching? The problem is fundamentally, if I see a here and let me be algebraic, I see an alpha and an alpha bar here. Should I match these or not? Now I can match them, but if I try to be greedy and match whenever I see an alpha and alpha bar, I may do something quite terrible. That is to say, maybe I have a bunch of betas here and a bunch of beta bars here, and the numbers are the same. Okay. So I chose this, but this is a horrible way of matching it. If instead let me just color this. Sorry, if I instead matched betas to the beta bars, then almost nothing will be unmatched. Only the alpha and alpha bar will be unmatched. So what I'm saying is that if you choose one bad choice, it could lead to a very bad suboptimal everywhere. So this is the reason why this is complicated. So yeah, it's like Sudoku. If you think you put a wrong number, things can go bad, even if it solves your local problem. So fundamentally, computationally, things are hard of this nature. If your things are locally solve your problem, but it globally messes things up, which happens here. Yeah.
Okay,
Sir,
so
if I may ask a question.
I
Thanks
request.
for that elaborate answer and the insights.
Thanks. Yeah, are there further questions?
Yeah, so Indrajit Devnath, he has raised his hand for a long time.
Okay,
so maybe
sure.
the organizers can unmute and he can ask a question.
Yeah, he can unmute. Indrajit, are you here?
Okay, I mean, you can also write on the chat box if you want.
Sir, good evening, sir. If I may
Yeah.
ask a question. Just hello.
Yes, I can hear you.
Yeah. Good evening, sir. The talk was very good, actually.
Thanks.
So I'm Krishna from Pondicherry University. I have a rather general question. So I would like to take up research in TDA, topological data analysis. So I would like to know what should one get started or equipped with, like in the basic terms, to get into the TDA.
Yeah. No, I am not an expert in topological data analysis. I'm familiar with it to some extent. You should know algebraic topology. That is one thing. Okay. And the second thing that I think I can just quote, I said the same thing in a different context, but let me quote Professor Rajiv Karandikar from 2 days ago. I think you all heard him say this, that if you want to apply mathematics to any domain, you must learn that domain. Okay. So if data is just an amorphous quantity to you, I mean, it's just a bunch of numbers and you have to play around with it and use some topology there, then it won't work. Okay. I mean, it'll work not work very well. Okay. So you have to be immersed. So one thing is, as far as topology is concerned, the topology in topological data analysis is algebraic topology, not very complicated ones. It's an understanding of homology and things like Morse theory, which let you compute homology. You need a good understanding. By the way, this is a general meta point. That is, when you're applying one field in another field, whether it's within or outside mathematics, typically the important thing is not knowing a huge amount, but knowing the core of it extremely well. So you need to understand algebraic topology, not necessarily a huge amount. You don't need a Steenrod square or any characteristic classes, but what you need to know it well. And the other thing is that you should be familiar with data analysis. You should be used to using SciPy and NumPy or whatever else in whatever language you like, and plotting things, working with your hands with numbers. But beyond that, I'm not an expert. You can. I'm only weakly familiar with topological data analysis. Beyond that, I can't answer.
Yeah. Okay. And one more question, sir. So how is the trend of TDA in India? If you can just give some details on, because research
trend
in TDA,
of what?
as far as trend of, I mean, how is TDA practiced in India? So research and all this.
Yeah, I don't actually know people working in topological data analysis. I'm sure, I don't know of too many actually. I know one person who did a bit, but he's gone off to Germany. So I haven't yet met somebody who does TDA in India. This doesn't mean there aren't people doing TDA in India. The person I know closest to that is Vijay Natarajan here in computer science, who does do topology applied to data analysis. But this is a little bit different. It's not what one calls TDA. It is interesting work. Certainly, there are. It's quite likely that just I haven't come across them, so I can't really tell you much about this. Yeah, if you're saying.
Sir, I can add to this.
Yeah.
Priyavrat is currently working on topological data analysis.
Yeah. Who is Krishnendra? I didn't hear the name.
Priyavrat.
Okay, I don't know him. Yeah.
Thank you.
So there is another question in the chat.
Yeah, so anybody wants to ask any question? Yeah, in the chat there is a question that could you please specify what maximality of length functions would mean? What would be the order of the length function?
Huh?
What would be the order?
I think this was a question asked already earlier, right? Here I wrote this function. L1 is less than or equal to L2 if it's pointwise less than or equal to L2. So you say one length. So length means at each group element you give a number. So there is an obvious partial order on functions on any set where you have pointwise ordering. That is, at each point one is bigger than the other. Okay. The non-trivial point is that in many of these situations you do have a maximum. Otherwise, if you, namely, you can look at all length functions in this class and take the maximum of this pointwise, and this becomes a length function. It satisfies triangle inequality and so on. It is very interesting that it happens. It's been used. It's the Kobayashi metric from long ago is of this nature. As I said, yeah. I learned of this, and a good way of learning all these things is from Gromov's classic metric structures on Riemannian and non-Riemannian spaces, with the caveat that nobody pretty much actually understands that book, but you still can learn quite a lot from it. Yeah, I mean, there are people like Mike Anderson who do, but yes, but most people don't actually understand that book, including me, but you can learn a lot from it anyway. Yeah.
Yeah. Okay, so
could I ask one more question?
Yeah.
Yeah, instead of, this is a very typical question actually, instead of taking the linear string, what happens if we take a cyclic one?
Oh, this is conjugacy invariant, right? So actually in this case, it makes no difference. So what you're saying is if it's only cyclically ordered, in this particular case, in general, it could lead to subtleties, but in this case, as it turns out, if you think of it on a circle, what you're doing is just pushing things out from the end. So conjugacy invariant means that so if you took a cyclic string, you get exactly the same thing as the linear string. Yeah.
Right.
Okay.
I see.
So any more question? Okay, so if there is no more question,
what if we have an array of such strings? Sorry, not a rectangular array.
You mean you have several elements in the free group? Yes.
Yeah, so it's like you have a matrix basically.
Right.
You have an m by n matrix, and then you want to match alpha and alpha inverse and beta inverse, but you could match it row wise or column wise.
Yeah, you can make variations of these. This depends on the non-crossing condition. You have to correctly specify what you mean by non-crossing, right? So for the linear case, it's clear what you mean by non-crossing. So you could generalize this by looking at an appropriate configuration, and this non-crossing definition which is sitting in front of us, you could try to have a variation of the non-crossing definition depending on your context and study this question. There are variations of these. Yeah. So this particular thing, you see, I mean, okay, I don't know much and I don't do much combinatorics. The thing is that there are three views of this. This is a combinatorial view, but it's also biology and it's also algebraic. And I primarily tend to look at it as an algebraic question. If you turn it into a rectangular array, you still retain the combinatorial question, provided you have your correct notion of non-crossing. Okay. Many of these techniques
the notion of non-crossing can be extended directly. It just applies in the column or in the row.
Okay. Yeah, you can. I mean, it can be extended directly, but not uniquely. You can decide how to extend a non-crossing, right? Yeah. So yes, there are ways in which you can generalize this to the square. I don't know what happens. Perhaps you can use the similar ideas. Perhaps not. I don't know.
Okay. Okay, so
Okay, thanks a lot.
so if there is no more question, then on behalf of the organizers and everyone, thank you, Siddharth, for this wonderful session. I think people really asked lots of questions, and that shows that it was very interesting to everyone. So I thank you virtually, and I request everyone to thank virtually on Zoom. So I give it over back to the organizers. So Somo, could you please?
Thanks a lot. Thanks a lot. Thanks for this opportunity. It was a lot of fun, and I hope people enjoyed it too. Thanks.
Thanks a lot, Professor Gadgil, for this wonderful lecture and answering so many questions. And also to Dr. Krishnendu Gangopadhyay for chairing this session. Thanks a lot. Thanks to all.
Thank you.
হ্যাঁ ওটা ঠিক আছে, ওটাতে যেতে
Should I keep the video on or?
না না, তুমি প্রথমে স্টার্ট দ্য ভিডিও, স্টার্টিং এ ভিডিওটা অন রাখো, তারপরে আফটার 2 মিনিটস যখন স্লাইডে স্টপ করবে অফ করে দেবে, তাহলে ইন্টারনেট কানেকশন ও স্টেবিলিটি থাকবে। তারপরে কোশ্চেন অ্যানসারের সঙ্গে
File, no?
হ্যাঁ
You can see the file, right?
yes slides here.
প্রণবে খালি মাথা দেখা যাচ্ছে, মুখ দেখা যাচ্ছে।
হ্যাঁ কি হবে,
আরে লোকজন বলবে একটু মুখটা দেখাও।
আরে কি দেখা যাচ্ছে আমি নিজে বুঝতে পারছি না, কি করে দেখছি, তোমরা দেখতে পাচ্ছ কোথায় সেটাও তো
আমরা দেখলেই হবে।
না এবার ঠিক আছে।
তোমাদের ওই গুয়াহাটির কনফারেন্সটা এমনি করে দিতে পারতে, ওয়ার্কশপ।
হ্যাঁ ওটা করলে ভালো হতো। যাই হোক, এটা তো হয়ে গেল, এটাই তো এটা মিটিয়ে দিচ্ছে আর কি।
এই রে, এটা কি এলো সামনে? তোমার স্ক্রিনে কিছু দেখাচ্ছে?
হ্যাঁ
একটা বক্স দেখাচ্ছে। আবার স্ক্রিন শেয়ার করতে হবে মনে হচ্ছে।
প্রণবদা, তোমার স্ক্রিনের সামনে একটা বক্স চলে এসেছে স্লাইডটার উপরে।
মোহন দা আসছে ওকে?
না।
Is it okay now?
Yeah, it's okay.
Okay.
এই রে, আবার চলে।
Again it
It is saying that your internet connection is not stable.
Oh. Then it's better to switch off the video if that's
Yeah, I guess
too much pressure.
Few minutes.
Just switch.
I have to.
Okay, I guess we can start, right? So, hello everyone. We are in the last day of the symposium on topology, geometry, dynamics symposium. We have today with us Dr. Arpan Kobiraj from IIT Palakkad, and he will be the chair of this session. Yeah, welcome. Over to you.
Thank you, Somo. So good evening, everyone. So our first talk today will be by Professor Pranav Sardar from IISER Mohali, and he will be talking about groups, negative curvature, and combination theorems. Professor Sardar.
Thank you very much, Arpon, and I also thank Sumo and other organizers for allowing me to speak here. So, okay, so I'll go on. So first introduction. So what is this combination theorems? What is this all about? So what are combination theorems? So in geometric group theory and combinatorial group theory, sometimes we start with a collection of groups with certain properties. And then we try to construct new groups out of these groups following some procedure. And we ask if the new group that we construct is again inside this collection. So these type of theorems are called combination theorems. Okay. And in this talk, this collection of groups C will be finitely generated infinite groups with some negative curvature property that I will define next. And the process of combining these groups. So this will be the graphs of groups construction, or more generally complexes of groups construction, and something a little different from this, but more or less these are the two procedures that we follow. So first of all, I will introduce these objects, these groups C. So this is the first part of the talk. So the collection C of groups. So there are three groups that I will introduce. The first one is the hyperbolic groups. So I will need some definitions. So suppose G is a group with a generating set S. So generally we'll assume it is a finite generating set. Towards the very end, I will need infinite generating set. But most of the time we work with finite generating set. Then the Kelly graph of this group with respect to the generator set S, gamma GS. So this is a graph where the vertex set is G, and a pair of vertices G comma H is joined by an edge if H equal to GS for some element small s in capital S. So this is the Kelly graph. So for instance, if you take the integers, then suppose I take the generating set to be the one containing simply the number 1. Okay. So then n will be connected with n plus 1 for all n. So essentially we'll get the real line in that case. But in general, so if I take a group G and a generating set S, then it is easy to see that this group gamma GS, it is a connected graph. And what we do is that we assign length 1 to every edge in this graph, and this makes it into a metric space. Because given two vertices, we just find edge paths joining these two vertices, and then we find the minimum of the length of such paths, and that we define as the distance between the vertices. So this defines a metric on this thing. And the length minimizing paths, this we refer to as geodesics. So the Kelly graphs, so these are graphs, but we work with more general graphs also, where edges are allowed to have any possible length, any positive length. Okay, but yeah, so to make it into metric space, we always work with graphs which are connected. So I use the notation Vx for the vertices and Ex for the edges of a graph X. We need that given a pair of vertices VW, there is a geodesic joining them. There is a length minimizing edge path joining them. So our graphs are like this only all the time. Although the lengths can be different, but we need this kind of thing because we have to talk about the properties of geodesics in a graph and so on. So now I define hyperbolic groups and hyperbolic graphs. So what is a hyperbolic graph? So a graph is called, so again, it's connected graph. So a graph is called hyperbolic if there is a constant delta bigger than equal to 0, so that given three vertices x, y, z, and any three geodesics joining this x, y, z. So I have a triangle kind of thing. Then the side xy, the geodesic joining xy, is contained in the delta neighborhood of the union of the remaining two sides. So in the picture below, so I don't know whether you can see. So there is a red thing that is supposed to mean the delta neighborhood of yz, and the green one that is supposed to be the delta neighborhood of xz, and as in the picture, so xy is contained in the union of these two thickened line. Okay, and then we say that group G is hyperbolic if for some generating set S, this Cayley graph gamma GS is hyperbolic metric space. I mean hyperbolic graph. Okay, we define hyperbolic graph. So if the Cayley graph is a hyperbolic graph, then we call the group G hyperbolic. So yeah, so properties. So hyperbolic groups. So basically this kind of this picture, this triangle kind of picture, this is very typical of a tree. So if I have a tree and if I take 3 points, then the geodesic. Given any pair of points, there is a unique geodesic connecting them in a tree. And then you can see the tree, in the tree, all the geodesic triangles, they look like tripod. So in fact, in this case, delta can be chosen to be 0. Okay, and another place where this kind of phenomena happens is typically hyperbolic space, HN. There also all the triangles are, so this property that there is a delta, we refer to this as saying that triangles are delta slim. So this delta slimness thing also happens in hyperbolic spaces. Okay, so that is why the hyperbolic, as I said, the title said groups with negative curvature property. So that is the reason behind calling this hyperbolicity or negative curvature property. So triangles are slim. So the first important point here is that although we say that Cayley graph is hyperbolic, but Cayley graph depends on the generating set. So I have to stress here that whenever I am saying the Cayley graph is hyperbolic, here I mean the generating set is finite. Okay, so the fact number 1 is that it does not depend on the finite generating set. Although if you choose a different generating set, then your delta will be different. Delta may be very big, but you don't worry about that one. So you just happy that this is hyperbolic. Okay, so this hyperbolicity does not depend on the particular finite generating set. Okay, so next is that so hyperbolic groups have many interesting properties. So this is one reason why one should study hyperbolic groups, but I will not have a scope to go into properties of hyperbolic groups. Okay, and then the most important point is that there are plenty of hyperbolic groups. It is not very like pathological definition. So the main set of examples that you can appreciate, I have listed only three examples. There are lots of other examples, and the whole point of this combination theorem business is to construct new examples. But I have given only 3 examples here, which are appreciable by people who work in geometry and other things. So fundamental groups of closed negatively curved manifolds. So these are hyperbolic. So this requires what is called Milnor-Schwarz lemma to prove this. It's not very difficult. So namely, for instance, if I take hyperbolic manifold, closed hyperbolic manifolds, then the fundamental groups of such things are hyperbolic. Okay, as per this definition, hyperbolic group. Okay, so, and these were really the motivation behind defining hyperbolic groups. When Gromov defined the hyperbolic groups, these were the motivation. Okay, and a particular case of this is orientable closed surface groups of genus bigger than, I forgot to mention here, genus bigger than equal to 2. Okay, so those are the interesting case. Genus 0 of course sphere trivial, and genus 1 is not hyperbolic, we know that, but genus bigger than equal to 2. So all of the surfaces we know is a smooth surface, let's say, so they admit hyperbolic structure, and it follows just like the number 1, and then that these groups are hyperbolic. There are elementary groups also, but yeah, this one way to see that this closed surface, closed orientable surfaces, smooth surfaces of genus bigger than equal to 2, these are hyperbolic groups. And also free groups are hyperbolic, because if you take a free group, finite tangent free group, and you take a free basis, then with respect to the basis, the Cayley graphs are just trees, and we commented that trees are 0 hyperbolic. So therefore, the free groups are hyperbolic. And another kind of example comes from what is called Newman spelling theorem. So he proves that suppose S is the generating set and R is just a word in the free group on S, and then you are taking the one related group S bar R to the K, where K is at least 2. So these kind of 1 mm groups, they are always hyperbolic. So there are plenty of hyperbolic groups. In fact, there is a theorem of Wolszewski which says that almost every finitely presented group is hyperbolic in some statistical sense. Okay, so if you Google for it, you will easily find out the reference. So the next what I'm going to do is that I am going to give you another characterization of hyperbolicity, because I am going to use it next. So so I'm going to define what is called convergence action. So suppose we have a group G which is acting through homeomorphism on a metric space X. Okay, then we call this action convergence action if the induced action on the space of distinct triples is properly discontinuous. So you basically take the subset of x cross x cross x consisting of all points x, y, z, such that x is not equal to y and y is not equal to z and z is not equal to x, like that. And so you take the diagonal action. In other words, g dot x comma y comma z is simply gx comma gy comma gz, so diagonal action. So if you take that action, then this the action should be properly discontinuous. So if that happens, then you call it a convergence action. So although it is not easy to see that this really, I mean, the term we are defining here is a convergence action, and the definition doesn't say anything about convergence action. I mean, there is nothing like limit or something, but this is not really the original definition. The original definition was due to Tukia, who defined it in a slightly different way, okay, inspired by the Kleinian groups and so on. So he gave another definition, and then Bowden showed that that is equivalent to this one. So since this is much more easy to understand, so therefore I am stating this definition. So this is convergence action, and under this convergence action, a limit point of G is the point of accumulation of some orbit of G. So you take some point small x in capital X and look at the orbit G dot x, and then you take the points of accumulation. Those are the limit points, and a limit point is called conical if something like this holds. So this is again a little technical, and one cannot appreciate the terminology here. But the definitions, the motivation behind these terms, they come from hyperbolic spaces really. So Kleinian groups. So what is the definition? So a limit point xi is called conical if there is infinite sequence Gn of distinct elements in G and a pair of distinct points alpha beta in X, such that limit of Gn xi is alpha, and on the complement of xi, so this Gn's converge uniformly. So Gn's are maps on this x minus xi to x. So on this complement, Gn's converge uniformly on compact subsets to the constant map beta. So in particular, if I take any point from x minus xi and apply Gn's, that sequence will converge to beta. So this is called conical. Okay. So typically, if you know what a little bit about the Kleinian groups and so on, hyperbolic geometry. So if you take a loxodromic element G, and then you know that G to the n is going to infinity and G to the minus n is going to infinity. So in this case, this is precise. That will these both of these points are going to be conical. These limits. Okay. So. So this is a definition of convergence action and conical limit point. So next, a limit point xi is called a bounded parabolic point if the stabilizer g xi is an infinite subgroup of G and it acts on x minus xi properly with compact quotient. So this is very special. Okay, so so generally one defines parabolic by saying that g xi is infinite. Okay, but we want more, so we want bounded parabolic. So we also demand that we should act on x minus xi with compact quotient. So just like if you take a parabolic element in the Kleinian group setting, then this, for instance, if you take, let's say, z going to z plus 1 on the hyperbolic plane, so then infinity, this is a parabolic point for this. So we know this, that is a parabolic isometry. Okay, and on the complement of xi, so this transformation acts properly and co-compactly. So just using that. So that is using that as a motivation. So here they define this bounded parabolic point. Okay, but why did I say all that thing? So now here comes the motivation. So Bowditch proves in 1996, following some ideas of Gromov, that a finitely generated group G is hyperbolic if and only if it admits convergence action on some compact metric space such that each limit point is conical. Okay, so this can be used as a new characterization or a new definition of hyperbolic groups. So here there is no calligraph geometry, nothing. So he just takes the group G and it is acting on some compact metric space. So you can do some analysis here. Okay, so this is Bowditch's criterion for hyperbolicity. So next, this is all about hyperbolic groups that I wanted to say. So next, I want to define the next group with negative curvature properties, so namely relative hyperbolic groups. So for that, I need some preparation. So here is the thing. So what is called hyperbolic cone. So what is hyperbolic cone? So suppose X is a graph. So then we define a new graph x to the h for hyperbolic. So I'll call that hyperbolic cone over x. So this is a new graph. So the vertex set of this one is that so you take Vx cross all the non-negative integers. Okay, and edges are defined as follows. So number one, V0, W0 are connected by an edge of length 1 if VW are adjacent in X. So point is that for every integer n, Vx cross n, so that level set that has the same graph structure abstractly, but the point is that the lengths will be different. So for instance, in number 3, it is saying that V and Wn are connected by an edge of length e to the minus n for all n. If VW are adjacent to X. So all the Vx cross n, those level sets, they have the same graph structure as Vx, but the lengths are decreasing when n is going to infinity. And if you fix a point of Vx, some vertex V, then you take the small v cross this z non-negative, then you will get a line. So Vn, number 2 is saying that Vn comma Vn plus 1 are connected by an edge of length 1, okay, for all V and all N. So this is typically the so if you know what it is, so if you take these horoballs, okay, so horospheres are like Euclidean planes, okay, so and then the horoballs can be thought of as this Euclidean plane cross 0 infinity, and this okay, so that is playing the role of Vx here, okay? And if you go upward towards infinity, then this distance in the horospheres, so they are exponentially decreasing. So that is the motivation behind this hyperbolic cone. So I have defined a graph, but I am not checking here, but one can check that this is a hyperbolic graph, okay.
Hello, Pranabda.
What happened?
Can everybody hear him? I think we lost the connection.
No, I think, yeah, Pranab got disconnected. He's disconnected.
Okay, let me, I guess. Let me call him.
Yeah.
Yeah, he's trying to reconnect.
Okay.
Yeah, please everyone wait for some time. Pranabda is trying to reconnect. The Wi-Fi has gone. So he's trying with mobile hotspot.
Hello, Somo. The talk is on.
Yeah.
Yeah, there are some technical problems. We are waiting for.
There is some internet issue here.
Yes. Pranada is trying to connect.
I also got disconnected. Okay.
Maybe then he will also now try and reconnect.
So one of our network has down. Let me call him and ask him to change the proxy perhaps. Let me call him.
Okay, yeah.
Somo?
Yeah.
Shubhabrata was asking that there is an option in Zoom of whiteboard or something. Is it possible to write? So is it possible to write there directly?
Yeah. Sure. Sure. So he's going to use whiteboard throughout, or
no? He said that he might use it for some part of his slide presentation.
Yeah, sure. You just, he just have to go to new share and switch to whiteboard and then do it. So back and forth.
So what's the procedures? Like you can do it through using your mouse or something?
With mouse, it would be difficult to write. But if he has,
that's technical.
Technically, it's possible.
Okay.
Technically, it's possible. Yeah.
Ideally, one should use the pen
stylus
or something.
Stylus
or something.
Yeah. So does it include that annotation part, or it's separate from that?
No. It's not annotation. It's I have disabled annotation, by the way.
Okay.
Yeah.
No, I think he is meaning different annotation. You can just annotate the PDF with your PDF reader actually also.
Yeah, that's not connected to Zoom. It's
that's not connected to Zoom.
Device,
that's just
device.
Yeah, device.
But the Zoom's whiteboard there, if you are so, for example, if I'm presenting a slide or something with the Zoom's whiteboard, I can still write on the slide, or I will have some blank page for that.
Blank page, yeah.
No. On whiteboard itself, you can write using.
Yeah, but he will write on the blank page, right? Not on the slide.
Yeah, whiteboard to start with will be blank.
Yeah.
Pranabda is here. Please join me as a co-host.
Yeah. Okay. Yeah, Pranupta, can you share again? Yeah.
Good.
Yeah, so Pranab has come.
Yeah. And Pranab, please unmute yourself.
Yeah, we can't hear you, Pranab. Please unmute.
Okay. So can you recall where I got disconnected?
Yeah, I can tell you. So go to the next slide.
Next or the before?
Yeah, so you just explained this thing. Okay. What's the definition of it? And you were saying something about hyperbolicity of this thing.
Okay, so I recall, so this hyperbolic cone we have defined. So how do I define? So we take Vx cross z bigger than equal to 0. This is going to be the vertex set, and then the edge set 1, 2, 3. They are defining the edge set. So what I am doing is that every level set Vx cross n that has the same graph structure as same set of edges as there were in X. Okay. Only thing is that in the nth slice, the edges are of length e to the minus n. Okay. And then for any vertex V in X, V cross Z bigger than equal to 0, that is just a line. So Vn to Vn plus 1, I am joining by edge of length 1. So this is hyperbolic graph. So this is a mental picture. So as I go upward, this is decreasing. The diameter of these sets are decreasing exponentially. So this is the definition of, so why did I mention on this hyperbolic cone? Because I had to define relatively hyperbolic groups. So this is the next set of groups with negative curvature property. So what we do is the following. So G is a finitely generated group, and H1, H2, Hn, suppose these are finitely generated infinite index subgroups. And suppose S is a generating set, it's a finite generating set of G, such that S contains a finite generating set for each Hi. So generally, from the definition, these are omitted, but they are implied. But I'll assume everything for simplicity. And so now what I do is that each coset GHI, on that I construct a hyperbolic cone. So basically the idea is that these HIs, these are like non-hyperbolic pieces. So they are preventing preventing G from being hyperbolic. So we destroy the non-hyperbolicity there by constructing a hyperbolic cone over each coset GHI. Okay. And then the definition is that if after gluing these hyperbolic cones to the Kelly graph of G, if the resulting graph is hyperbolic, then we say that G is hyperbolic relative to HIs. So I have actually moved a lot of things under the carpet. So the hyperbolicity, this relative hyperbolicity was defined by Gromov, and then later on Favre defined relative hyperbolicity in a different way. Okay. So he called it strong relative hyperbolicity, and then Bowditch and some other people, so Bowditch was mainly behind this, proved that these two definitions, Gromov's and the Favre's strong relative hyperbolicity are equivalent. Okay. And also as for we have seen that we had the characterization of hyperbolic group in a different way. So similarly there are many other characterization of relatively hyperbolic groups, but I will not have a scope or time to say all that. So I'll just be satisfied with this one, and I'll now show the following theorem for you. So this is an analog of Bowditch's theorem. Bowditch proved that if group is hyperbolic if something happens, convergence action and so on. So here also Ashley Yaman, she proves in 2004 that if a group G is hyperbolic with respect to finite collection H1, H2, H10 of subgroups, if and only if it admits a convergence action again on some compact metric space. But in this case, we are assuming that the limit points are either conical or bounded parabolic. So this is a bounded parabolic is a new thing that we are allowing. And number two is that the stabilizers of these parabolic points, they are precisely the various conjugates of these HIs. So this gives a new characterization of this relative hyperbolicity. Why I am saying is that I will need this to explain one of the theorems later. So these are the two, you can think of them as alternative definitions of relative hyperbolicity. So now I'll show you another kind of equivalent definition. So for this one, I need this one. So suppose X is a graph and Y is a collection of subsets. So generally we'll assume these are connected subgraphs, YIs. So then what I do is that for every YI, I introduce a new vertex that is not inside X, new vertex Vi. And what I am doing is that every vertex of Yi I am joining with Vi. Okay. And constructing a new graph. So this is called electrified graph, because you see that in the new graph, each Yi has diameter at most 2. Okay. So Yi's are a priori, they are infinite subgraphs, but in the new graph, they have diameter 2. So that's why we are calling it electrified graph. Okay. So I will denote this new graph by X to the E for electrified, and a metric by D to the E. Okay. So now the point is that this I had a graph, infinite graph, and I have collapsed a lot of things. Okay. This Yi's, they were infinite diameter set, and I have collapsed them. I made them into finite diameter thing. So as I have lost a lot of information. So to remedy that, so what we do is the following. So this new notion is due to the Harmony-Girardel Oshin in the very famous recent paper. But the angular metric, this term I learned from a paper by MJ and Harmony. Okay, so what is this? So we had the electrified graph, and YIs are of course diameter 2 sets, at most diameter 2. But we are defining a new metric now. So what is this new metric? So if I have vertices UV inside the vertex set of YI, what you do is that you consider all the paths, edge paths in the X to the E that join UV but which do not pass through the vertex vi. Okay, so yi every, so what is yi? So yi is a subset of x, and every vertex of yi is joined to vi by some edge of length 1. Okay, so I want the path joining uv to be avoiding that vertex. Okay, so this is going to give you a new kind of distance. So this we are calling it angular distance of uv. Okay, so this priority will be bigger than 2, of course, and we will call it angular metric. It may happen that joining uv there is no path there. It can happen, but in our case it will not never happen. So yeah, here we are assuming that yi is almost all the time so connected subgraphs, but in general that is not assumed, and then they also allow this distance to be infinite. There is no harm in that. And why do I say all that? So here is a new so I give a new characterization of this periodicity. So I need one more thing, acylindrical action. So this was defined by Bowditch in a paper where he proves this that famous thing that mapping class group acts acylindrically on graph graphs. So what is acylindrical action? So suppose the group G is acting by isometries on some hyperbolic graph. Okay, then we say that the action is acylindrical if for every epsilon positive there are positive constant r and n, such that if two vertices x, y are given and they are far apart, distance of x, y is bigger than equal to r, then the number of group elements G, small g, such that distance of x and gx is less than equal to epsilon, and distance of y and gy less than equal to epsilon is at most n. So this is like properness on the induced action on x cross x. Okay, or you can think of this as the group is acting properly on the geodesics of x. Okay, so let me repeat. So what is the acylindrical action? So if I take two vertices which are far apart and I want to see what all elements move these endpoints just a little bit, so that's a finite connection. So this is the acylindrical action, and this is the thing that I wanted to say. So this is a kind of new characterization of relative hyperbolicity obtained from the work of DGO and this Dahomey Girard-Deleucin and independent and also the Oceans acylindrically hyperbolic groups. This paper. So they prove the following thing. Suppose G is a group generated by finite set S, H1, H2, Hn. This is a collection of subgroups. And for simplicity for us, we can safely assume that this contains a finite generating set of each Hi. Then G is hyperbolic relative to Hi. So we defined this notion before, which was due to Bowditch and so on. So what is this? So number one is this electrified graph, where in the Kelly graph I am electrifying the cosets GHI. So for every GHI I am constructing a new vertex outside the Kelly graph and so on. That electrified graph should be hyperbolic, okay, and the G action on this hyperbolic space, hyperbolic graph, should be acylindrical like we have defined before, and the angular metric on each GHI makes it into a proper metric space. Okay, so if all the three things are satisfied, then this hyperbolic. So this is the if and only condition. So you can think of this as a new characterization, different, or you can take it as a definition of relative hyperbolicity. Okay, but this has more to it. So so using these kind of ideas, now Ocean has introduced a new set of groups which are called acylindrically hyperbolic groups. So what are these objects? So G is any group. So in this case, we do not assume they are finitely generated. So this is called acylindrically hyperbolic if it admits a generating set S, which may not be finite a priori, such that the Kelly graph is a non-elementary hyperbolic graph. Okay, and the G action on this one is this Kelly graph is acylindrical. Okay. So this generalizes both hyperbolic groups and relatively hyperbolic groups. So I have defined for you Kelly graph, hyperbolic graph, and acylindrical. So I have to explain what is non-elementary. So for specialists, of course, they know what it is. So this simply means that these hyperbolic graphs have more than 2 points in the boundary. Okay. So for you, what I will say is for some people who are not familiar with this thing. So I'll go as follows. So given constants k bigger than equal to 1 and c bigger than equal to 0, and some interval I in R and a metric space X, a map from the interval to X is called a KC quasi-geodesic if these two inequalities hold. Okay, so if I did not have the constant C, then it will be simply some biellipses. Okay, but I allow some additive error, but it is independent of ST. So I allow some uniformly small bounded error. Okay, so these are called quasi-geodesics. When Kc are not important, we'll just call it quasi-geodesic. And when the interval is 0 to infinity, we'll call it a quasi-geodesic ray. So 0 to infinity, this interval to x, if I have a quasi-geodesic, then I call it a quasi-geodesic ray. Okay, so more generally one can define this for any metric space. If I have any map from some metric space y to x, which satisfies this condition, where of course I have to replace this absolute value s minus t by the distance of y and so on. So that will be called QI embedding. I will need that later and I will recall this one again. So this is a quasi-geodesic. Now when is a hyperbolic graph called non-elementary? If it has 3 quasi-geodesic rays, at least 3 quasi-geodesic rays starting from this point P, and let's call them alpha 1, alpha 2, alpha 3, such that when I join alpha I n and alpha j n by a geodesic, okay, I is not equal to j, then these geodesics, they are going far away from, I'm sorry. So I really wanted to say that they are not going to infinity, okay, but I typed going to infinity, no. So this distance, this is wrong, whatever I have added in the definition is wrong. So the distance from this this point P to this geodesic joining alpha I n and alpha j n, they should be bounded subgroups. Okay, so then I call it non-elementary hyperbolic graph. Okay, so the definition that I put here is wrong. It is not going to infinity. It is supposed to be bounded. So this is not something arbitrary or some pathological definition, because Cayley graphs of any non-virtually cyclic hyperbolic groups, okay, where I am choosing finite genetic set, they are non-elementary hyperbolic graphs. So those groups which are virtually cyclic, they are hyperbolic and they are called elementary hyperbolic. And all other hyperbolic groups are that's why called non-elementary hyperbolic groups. And similarly, if I choose relatively hyperbolic graph, a relatively hyperbolic group, okay, then this corresponding electrified graph, okay, assuming the group is not virtually cyclic, they will be non-elementary hyperbolic graphs also. Okay, so now after giving the definition of relatively hyperbolic groups and as cylindrical hyperbolic groups, now I want to give you some examples to show that these are not very rare. Of course, I gave you some examples of hyperbolic groups, and you can easily see that any hyperbolic group is relatively hyperbolic, because you can choose the trivial subgroup. With respect to trivial subgroup, it will be relatively hyperbolic. But the original motivation behind defining this relatively hyperbolic groups, so it was defined by Gromov. So they came from this following example. So if you take a finite volume complete hyperbolic manifold, or pinch negatively curved manifold, even manifolds, okay. So in this case, we can prove that there are one can show that there are finitely many cusps. So this is a result of Abel line, and let us call the cusps C1, C2, Ck, finitely many cusps, and you take the cusp subgroups Hi. So he proves that these cusps have a kind of colored neighborhood, some manifold cross 0 infinity kind of neighborhood, and these HIs are these fundamental groups of these manifolds. Okay, so these are cusp subgroups, and then G is hyperbolic relative to HIs. Okay, so this was proved by I think this was sketched by Gromov and rigorously proved by Fab in his paper on relatively hyperbolic groups. Okay, so this is the main motivation behind the definition of relatively hyperbolic groups. So another hands-on this thing that you can easily check is the following. Suppose H1, H2, Hn, this is a collection of non-trivial groups, and you take their free product. So then that is relatively hyperbolic with respect to HIs. Okay, so you can think of these as a combination theorem. And again, Fab proved that if I have a hyperbolic group G, and a quasi-isometrically embedded subgroup H, which is also weakly man-normal. So man-normal means subgroup intersected with its conjugates, non-trivial conjugates, that is trivial. Weakly man-normal means this intersection is going to be finite. So if I take hyperbolic group and a weakly man-normal subgroup, which is also quasi-isometrically embedded, so what does it mean? So H is finitely generated, so it has its Kelly graph, and Kelly graph metric restricts to H metric, and then the inclusion map from H to G, that is a quasi-isometric embedding, like I have defined this like in the definition of quasi-geodesic. So we have the inclusion map from H to G, and that is roughly speaking bi-ellipses up to additive error. So that is QI embedded subgroup. So in that case, G is hyperbolic relative to H. So this was Farb's result, but Bowditch also proved the converse, that if G is hyperbolic group and H is some subgroup with respect to which it is relatively hyperbolic, then it has to be quasi-convex, I mean QI embedded and man-normal, weakly man-normal. So this gives the set of some flavor, some ideas about examples of relatively hyperbolic groups. So next I'll say something about acylindric hyperbolic groups. As I said, so this generalizes all of this hyperbolic and relative hyperbolic. So because you see that if I have relative hyperbolic group, then I will take the electrified graph, and on that the group is acting as cylindrical. Okay, and as I said, if it is not virtually cyclic, then you will have non-elementary graph. So therefore they will be acylindrical hyperbolic. So relatively hyperbolic groups are acylindric hyperbolic group, but this is a much larger collection than relatively hyperbolic group, because we are also allowing non-finitely generated groups. Okay, so here are some other important examples. So all of these examples are taken from the paper of Oshin, which is titled Acylindric Hyperbolic Groups. So here are these examples. So if S is a finite type orientable surface, then mapping class group of S, we know that this is standard result, that it is not hyperbolic with respect to any finite collection of subgroups, but it is proved by this, for instance, theorem of Bowditch, that this is acylindrically hyperbolic. This acts acylindrically on the curve graph. And the outer automorphism group of Fn when n is bigger than or equal to 3, this is acylindrically hyperbolic. Okay, so this was essentially proved by Oshin and Westbina and Fujiwara. Okay, and so these are two groups, MCGS and OutFN. They are most they are very famous groups and the most studied groups in geometric group theory. So both of these are hyperbolic, acylindrical hyperbolic groups. And here is a funny example for people, algebra-minded people. So if you take any field K and take the polynomial ring in two variables x, y, then the automorphism grows. So we know about what are the automorphisms. Okay, this is a classical result. So this automorphism group is acylindric hyperbolic. Of course, we know that this is not, for instance, if K is an infinite field, this is not going to be a finitely generated group, but this will be acylindric hyperbolic. This was also proved in paper of Oshin and Minasian. Okay, and then one related groups with at least 3 generators. These are acylindric hyperbolic. Cat 0 groups with rank 1 elements. So I don't have time to explain all that. So these are acylindric hyperbolic. And if you want more examples, then you should look at this survey article by Anthony Genevois. So hyperbolicity in Cat 0 Q complex. So he gives a lot of examples, a lot of other examples, like which braid groups are acylindric hyperbolic and so on. Lots of examples are there. So this finishes the first part of the talk. So unfortunately we are running late. So now the second part, the combination theorem. So namely, we have described the groups. So now we want to know in which way can we combine these groups and create the same kind of groups. Okay. So the first and most important of this is this Base-Innerfeld theorem. So it was published in 1992 Journal of Differential Geometry. So what is this theorem? So it is saying that if I have a finite directed graph y and the script G is a graph of groups on y. Okay. So this means that every vertex V, for every vertex V we have a group GV, and for every edge we have a group GE. So we assume that these all these groups are hyperbolic groups, and then there are homomorphisms, injective homomorphisms from G to GV and G to GW whenever E connects V and W. Okay, so these these homomorphisms are assumed to be quasi-isometric embeddings. So you choose your favorite generating set for GE, GV, and GW. With respect to that, they will have metric GE, GV. So in the Kelly graph they are sitting, so they will have metric, and with respect to those matrices, so then with those metrics, then we have this quasi-isometric embedding. Then the fundamental group of this graph of group is hyperbolic if the always flare condition holds. So I will say a little bit about this technical, this always flare condition is technical a little bit. Well, but the point is here is that I have put this only if in bracket because they did not put the only proof was only proof this came from somebody else, some Gastain and other people. So they proved this only. Okay, so that is that, and this so I will explain this little bit about this theorem. So for so in this as we are saying, this is a directed graph. Okay, so here we are also allowing loops, and if I have loops, that means some direction is there. So depending on that, so there will be two homomorphisms always. For every edge I have two homomorphisms, one is forward and one is backward. So forward direction is going to the vertex V, so I have some homomorphism. I denoted phi EV, and then backward phi EW, GE to GW, that is the homomorphism. So this data is a graph of group data. Okay. So for instance, if I have just an edge VW, two distinct vertices connected by some edge V to W directed, so then I will have two groups GV, GW, and GE, just three groups, and two homomorphisms. That will be that. And then this resulting pi 1 of that will be simply the amalgamated free product, like that. So this number 2 is saying that the quasi-isometric embedding, I explained already what it means. Okay, and pi 1G, as I said, in general it will be slightly technical, but as I said, so if I have just an edge, so then this is I mean just line of length 1, then it is simply the amalgamated free product. Okay, so in general it is a little bit technical, so I'll quickly say what it is. So given this graph of group data, you construct a topological space by constructing KG1 of each vertex group and each edge group. So then we know that given these homomorphisms from G to GV, there is a corresponding continuous map, so simplicial map from KGE1 to KGV1, and similarly KG1 to KGW1. So using this homomorphism, what you can do is that you can construct the mapping mapping cylinder. So KGE1 cross -1 interval -1 1. So construct that cylinder and glue these ends to the corresponding the KG1 spaces of the vertex spaces. Okay, KGV1 and KGW1. So in this way, for every edge you do this. So in this way you get a complex. Okay, and you compute the fundamental, you find the fundamental group of that. So that is the fundamental group of this graph of group. Okay, flaring condition is technical. So so I will just say one example. So one application of very simple application of this theorem of Christian is that free products of hyperbolic groups are hyperbolic. So this is, in this case, flaring is really true. So I did not explain what it is, but these are easy. And then if G1, G2 hyperbolic groups and H is weakly malnormal common subgroup, which is Q embedded in both, then the amalgamated free product is hyperbolic. And this is where I will explain a little bit about flaring. So what is this? So Weiswiener defined what is called hyperbolic automorphism of a group. So given a group G and some automorphism F, okay. So if I have a hyperbolic automorphism, then the semi-direct product, corresponding semi-direct product, is hyperbolic. Okay, so I'll just quickly explain what it is. So what is hyperbolic automorphism? So suppose G is generated by finite set S, some automorphism given small f. So it is called hyperbolic if there is a constant lambda bigger than 1 and m bigger than equal to 1, such that if I take any element W of G, such that the distance from identity to W is bigger than equal to m, then the distance of 1 and FW and 1 and F inverse W, maximum of that will be bigger than equal to lambda times 1W. So at least F or F inverse will take W to some element which is far away, more far away from identity. So this is the flaring condition. Okay. So
Pranabda?
Yeah.
How many slides do you have?
Okay, so maybe I'll try to wrap up in 10 minutes. Is it fine?
Could you do it in 5 minutes because next speaker's
Okay.
timing is from. Okay.
Okay, so let me,
Please.
so I'll skip this part and go to the the next slide. So what is this? So this was a very nice theorem, and it has produced a lot of it inspired a lot of research in this field to find similar combination theorems. So I'll quickly say something. So Swarup proved that if I have amalgams of hyperbolic groups, does that H is QI embedded in both, but malnormal in just one of them, then it is hyperbolic. It's slightly general than Weiswiener-Fein's application. And Rita Gettig in 1997 proved a similar theorem for Lee Mosher. A very interesting example came from Lee Mosher, 1997, where he found an exact sequence like this, where G is hyperbolic, and F2 is a free group on two generators. So he took two pseudo-dinosaurs, independent pseudo-dinosaurs, and then he took certain power. So it is like a Schottky construction. Okay, this was a very new construction, very new example of this kind. And then in 1997, Weiswiener-Handel and Weiswiener-Finn-Handel, they construct free by free example. So in this case, in the above case, I have pi 1s and F2. They replace pi 1s by free group. Okay. So and yeah. So in particular, free bicyclic hyperbolic groups were constructed by this Weiswiener-Finn-Handel. And Brinkman then showed that so he completely characterized which free bicyclic are hyperbolic. So he said that it should not fix any conjugacy class. If the automorphism doesn't fix any conjugacy class, then this is hyperbolic. Okay. And in Kapovich in 2000 proved a similar combination theorem. So as I said, we have this free bicyclic. So this is coming from the automorphism, and similarly the pi 1s. And Kapovich generalized that. And Kapovich, this is Ilya Kapovich in 2000. He proved a theorem for ascending HNM extension. And some of the things, these are not important. So this one is very important. So Farb-Mosher defined a convex co-compact subgroup of mapping class group. So they find, so they were asking this example of Mosher, where this surface by free group. So they were asking in the quotient which groups are allowed, so that I get hyperbolic group. Okay. So they prove that if this is the case, then that quotient Q should be should have QI embedded orbit in the triangular space. So mapping class group acts on the triangular space. So they prove that if a finite group Q has a quasi-isometric embedding, orbit map is quasi-isometric embedding, then the corresponding this extension is hyperbolic. And then later on, Kent, Leininger, okay, and Hamilton independently, they showed they found the opposite direction of this theorem. That is, it is if and only if, okay, that is that. And so similar other things are there. So I will just skip some of the things. So Alexander Martin proved. So these are theorems about this complex group. I don't have time. Only thing that is very important here I mentioned this is Dowdell Taylor. Following the Farb-Mosher, they also found a new. I mean, they defined this. They found this general construction. They are giving sufficient condition for some free by some other hyperbolic groups to be hyperbolic. So they give a characterization. So which subgroups Q will have this hyperbolic extension. Okay. So that is in 2014. Okay. So what they do is that so they in their so they prove a general theorem, but they could not find a more general example than free by free. So these free groups, these are the new thing about this thing is that they are different from this Weiswiener-Finn-Handel in that they they generalize that condition. The Weiswiener-Finn-Handel example, the quotient free group was very special, so they removed that condition. And 2018, very recent. So this person C. Wianik, so he further generalized this. Okay, finding more free by free hyperbolic examples. Okay. So that was the thing for this thing for hyperbolic groups. But I'm afraid I don't have time to explain this thing for relative hyperbolic groups, the combination theorem for relative hyperbolic. I just mentioned a few. So Dahamani proves the combination theorem for relative hyperbolic groups in 2003. So the Swarup, Gadde Swarup, he asked can we find a similar combination theorem like Bismuth theorem for relatively high probability groups? So Dahamani proved in 2003 something like that, but his theorem was very special, and he assumed very strong condition. Only thing is that he used this Ashley Yeoman's criterion. So he also took a graph of groups, relatively high probability groups, and he made it act on some compact space and proved that it satisfies these conditions: convergence action, and then all points are conical or bounded parabolic, and he derived this. But his theorem was completely generalized in Mahan, MJ, and Lawrence Riff's theorem in 2006, who proved an exact analog of this Bayesian theorem. Under very natural condition, he proved this theorem. And one very recent interesting development was by Pritam Ghosh, our this thing colleague, and Dahamani Lee independently in 2020. They showed which free bicyclic extensions are relatively high probability. Okay. They show that if the automorphism that you are taking to this construction is exponentially growing, then it will be relatively high. This is very recent. And for this asymmetrical hyperbolic groups, we don't have much new developments. So we just have one single paper by OCM Inertial where they are giving sufficient condition on a graph of groups to be asymmetrical hyperbolic. So here is a kind of sample theorem. So if I have amalgamated free product A star C over B, and A not equal to C not equal to B, and C is weakly malnormal in one of them, then it is asymmetrical hyperbolic. And then some other paper of Indira Chatterjee and Alexander Matin are there. Okay, so like so this is can be thought of as a complex of group example. But these are all that is known about the combination theorem. So here I'll quickly say what are the questions. So generalized Bayesian theorem from graphs of groups to complex of groups. This is actually completely open. Only two cases are proved. In one case, the maps from the phase groups to the smaller phase groups, those are quasi-isometries, and when the complex is asymmetrically asymmetrical complex. These two extreme cases are known. Nothing else is known. So find new theorems in here. And the next question is that for graph of groups even, flaring condition is very mysterious. So can you find some special cases of graphs of groups where flaring will be implied and there will be new theorems? Okay. And combination theorems for asymmetric hyperbolic. This is, as I said, completely open. No, nothing is known almost. And the last one is that this free convex complex. So all the convex complex groups of MCGS that are known till now, they are all virtually free. Okay. So are they non-virtually free? So this is a very big open question. So with that, I will finish the talk. If you want the references, we can ask so more me. I will send you the references. Sorry for the delay. Thank you.
And thank you, Pranabda. So maybe if anybody has any question, please unmute yourself and ask directly to the speaker. Okay, so sorry, we are running a bit late, so I can't see any questions. So let us thank the speaker, maybe virtually, or if you want to clap, unmute yourself. So thank you, Pranabda. Thank you very much. Thank you. So our next speaker, Subhabratada, are you here? Can you start sharing your slide? Yeah, good. Okay. Please start sharing your screen.
Just a minute. Is it visible?
Yeah, it's visible. Are you ready? Shall we start?
Yeah. So shall we start right now or wait for it?
Up to you, whenever you are comfortable.
I'm fine.
Okay, then we shall start right now. Okay, welcome everyone. So we'll start the second invited talk for today evening, Geometry, Topology and Dynamics Symposium. The Professor Subhabrata Das from Presidency College He will be talking about small cancellation groups. So up to you, Subhabrata.
Thank you. Thank you, Arpan and Shinbuda and others for the invitation to talk at this virtual math fest. So I will be talking about small cancellation groups today. So the outline is here. So
Shobhrata, we can't hear you clearly. Can you please
can you
little
hear
louder?
me? Can you
Louder.
hear me? Can you hear me now?
Yeah, okay.
Okay. Maybe I'll sit a little closer. Okay, so small cancellation theory is a pretty old one now. That the main works. I should not say main. I mean, it started with Max Denn's work on the surface groups and his works on the decision problems for fundamental groups of these closed orientable two surfaces. And he solved those problems, the word problem and the conjugacy problem. And while solving those problems, he observed certain behavior of the presentation of the fundamental groups, and those behaviors. I mean, he used the hyperbolic metric in his deductions, but later on, I guess by Reidemeister, it was shown that those conclusions were not essentially dependent on the hyperbolic metric on where the group was acting on the hyperbolic plane. So later on, these ideas were picked up by various people, and these are few. Here are a few names like Tarkovsky, Grindlinger, Britton, Sheep, Linden, Schub, etc. Rips, Olshansky, and others. So Grindlinger proved a theorem which Max then had proven in the surface group context. He proved in a much more general context, and there started the theory of small cancellation, I would say. So let's get started. So here we have a group G with a presentation like S, and S is the generating set. We have not mentioned finite or infinite here, but for most cases we will stick to the finite presentation. S and R both finite, and we will mention where it is not, where it is otherwise. And here we, by this presentation, we mean that G is generated by S. That means we have G as a quotient of the free group on these letters S, and the kernel of this quotient map of this the kernel of this epimorphism is the normal subgroup, which is generated by these words. So a word is a finite string of letters, and the length of a word is the number of letters in it, and it's reduced when there are no such subwords like this. And we call these types of words in this set R to be defining relators. And a relator is cyclically reduced. If you apply a cyclic permutation on this relator, if you still do not have any such subwords, it is cyclically reduced, and it's symmetrized if all elements are cyclically reduced, and it has all the cyclic permutations of all R's and their inverses, and so on. Now, the most important definition here is of a piece. A piece is a word. It's a subword. A piece relative to the symmetrized set of defining relators R is a subword. Is a subword of at least two distinct elements from capital R, two distinct relators. And since we are taking things up to cyclic permutation, symmetrized R, so we can take U to be prefix in two distinct R's. If it appears in distinct ways in two distinct relators, we can choose the relators in such a way that they are the prefix. It really doesn't matter so much. So then we come to this thing called a Van Kampen diagram, and here we see what this diagram is. It is a compact, simply connected two complex, CW complex, which is in R2, and where each one edge, each one cell, which are edges, that will be oriented and labeled by a letter in S. See, here we have the generating set S. That means it's a symmetric generating set. We have the S letters and the S inverse letters. I mean, if we have a small s, then we have small s inverse also in this set. So this diagram, the edges, the one cells in this two-dimensional CW complex, they will be labeled by small s and small s inverses coming from this capital S. And each two cell, its boundary, it should be a word lying in R. So R is our set of relators. So essentially we are thinking words in R as some circles, some loops or cycles rather in this type of a diagram. So these are typically the elements of capital R. So each two cell has a boundary word lying in R. So what Van Kampen lemma talks about is that if a word is trivial, if a word in G is the quotient of the free group Fs by this by the normal subgroup generated by this subset of words. So in this quotient, if a word W is trivial, and it's trivial if and only if there exists a reduced Van Kampen diagram, a diagram of this type, over this presentation whose boundary word is W. So roughly how we get there is that since a word is here, is trivial in G, that means it must lie in the normal subgroup generated by R. That means it must look like a product of conjugates. So this type of balloons we can think of as a product of conjugates, this being a GI, this being a RI, and this being a GI inverse. So this is the identity. I can think of it as I'm traveling via GI, I'm traveling the relator RI, and then I'm coming back to the origin by GI inverse. So since the word is trivial here, so it should look like this, and then it should, in the beginning, it should look like this balloons, wedged balloons. And then we can see that there are a lot of cancellations taking place here and other places. So those other places would give rise to the pieces as we see, as we'll be seeing soon. So there will be a lot of cancellations taking place here in this product, and that will give rise to such a thing. That's the content of the Van Kampen lemma. That this would give us two-dimensional CW complex like this.
I have one question.
Sorry?
So can you hear me? Yeah, so I have one question. So I'm Abhijit. So you said that this is compact, simply connected two-dimensional CW complex, right?
Yes.
So if I just take, say,
a trivial word, for a trivial word, we have this.
No, you said the Van Kampen diagram over the presentation is compact, simply connected.
I think simply connected here is a typo.
Okay, thank you.
Simply connected here is a typo. I'm sorry, very sorry. Thank you. So simple connectedness would come from a trivial word. So yes, thank you for pointing out. Simple connectedness here is a typo. Okay, so in the next slide we see what are known as the small cancellation conditions. So there are a few variants of small cancellation conditions, and the most used or known ones are the metric small cancellation conditions, which is the following: that if G has a presentation like this presentation satisfies a small cancellation condition C prime lambda for a lambda greater than 0 is when a piece must be contained in a relator. So this is the relator R where the piece U is contained. So whenever U is a piece, the length of the piece U should be less than lambda times the length of the relator in which U is a subword. Okay, so that is the small cancellation condition C prime lambda, and we can see here for an example. This is the tessellation given by the presentation of genus 2 surface, a closed orientable genus 2 surface, and the relator here is the product of two commutators AB, commutator AB and commutator CD. So it's a one relator group. Now we can see here, these are the only possible pieces, right? So, a piece we call some subword a piece when two such relators, they come together on some subword where two relators overlap. The boundary of those disks overlap. So here we can see clearly in this example that they can overlap only along either A or B or C or D and so on, right? So the length of this word here is 8 and the length of this is 1. Sorry. Length of this is 1 and so clearly this presentation satisfies small cancellation condition C prime 1 by 7. Okay, so this is known as the metric small cancellation. Now there is another small cancellation condition called CP for P natural number. Here what it essentially, the definition says that presentation SR is satisfying small cancellation CP if no element in the set of relators is a product of less than P pieces. At least, the relator should not be a product of less than P pieces. Okay, so that means there should at least be P subwords, P segments on the cycle, if we can think of it. Then there should be at least P segments on that cycle where any other relator overlap with the given one, with any given one. So that is essentially the meaning of this condition CP, and this picture somewhat captures that that if you have a relator which is R naught here, there should be at least P pieces here. Okay, so here it can be more as well. So this presentation again, the previous one, it satisfies a small cancellation condition C8. It was a C prime 1 by 7. Here it's a C8 presentation, the same thing. This is a C8 presentation, as we can see very clearly. The pieces are only the generating letters. And from the definition, we can very well observe easily that a C prime 1 by n condition would imply that it has to be C of n plus 1, C n plus 1. So that's obvious because any piece has to be less than 1 nth of the relator. So there has to be at least n plus 1 pieces to give you a product, to give you a relator as a product. Okay. So there is a next condition which is called a TQ condition, and I mean, we won't be using this condition, especially the TQ condition much in this survey. But still, for the sake of completeness, this is a condition. The definition itself doesn't look very obvious, but you see here that if you have L relators, L is at least 3. The presentation satisfies TQ if you have less than Q relators, greater than 3, greater than or equal to 3. Then, if consecutive elements in this set, they are not inverses of each other. They don't cancel off. One doesn't cancel off the next one. So when you form a product, so in that case, if you take the products, then at least one of them is reduced without cancellation. So if it satisfies TQ, and you are taking L of them, not Q, I mean something less than Q. So here the meaning of it is reduced without cancellation. That means they don't have any such overlap like this. So if you take a bouquet like this of relators, and then if you have less than Q of them at a point, then there will be at least one such product, these consecutive products, which is reduced without any cancellation, right? So you can just think of removing this one or removing this one, and in that case there will be these two whose product will you will get without any cancellation. So this condition essentially means that so this is part of a Van Kampen diagram, and this vertex is an interior vertex of the Van Kampen diagram. So essentially this condition tells us that if the presentation satisfies this condition, then at any interior vertex there should be at least Q. There should be at least Q of these relators. So giving us the degree of any interior vertex being at least Q. So we can think of the presentation of the free abelian group of rank 2. There we can see that the presentation would satisfy both C4 and T4. You can think of it just looking at the dual graph. I mean, you just take the points corresponding to this, and when they're adjacent to join an edge and so on, and that would give you, I mean, the TQ condition. Okay, so here are a few examples. So this satisfies a C4 T4 condition, and as we have seen that for a genus G or genus G surface, the defining relator is a product of G commutators. So we have a 4G one relator with length 4G, and still here the pieces are only AIs and their inverses, BIs and their inverses. So they're all one length 1 pieces. So it satisfies C prime 1 by 4G minus 1. So this is a theorem by Pride, where he proves that this is C twice N group and so on. And this group, you can see in this presentation that the only pieces are AIs, not the squares, because the squares do not appear in two different ways. Only AIs appear in two different ways, so they are the pieces. So their two relators can overlap. So they are the pieces. So here it satisfies 1 by 2k minus 1. And here we can see another presentation like this. This is a very typical small cancellation word. AB square, AB cubed, and so on to AB 100. You can just calculate, check the length of this, and check which subwords can be a piece. So you should find subwords which appears in two distinct ways. So here you can see a subword b to the I a, b to the I plus 1. You get this subword here once, and again in this b to the I plus 1, a, b to the I plus 2, you can find the same subword again sitting inside this string b to the I plus 1, a b to the I plus 2. So you take the b to the I, the second, the last portion, and then a here, and then you take the first b to the I plus 1 from this b to the I plus 2. So you get this this subword appearing at least one more time. So pieces are of that type. So what would be the largest piece of that type? So you will find a b to the 99 here, a here, b to the 98 here, and you can see the pieces there of the form b to the I a, b to the I plus 1, and then you have also b to the i's as pieces. So you can calculate that the pieces are at least they're less than 1/20th of the length of the relator. So here is a very nice example of a small cancellation group. It's a very nice paper written by Rips in 1982, which says that given any finitely presented group G, and a positive real number, you can find a small cancellation group. This group is a small cancellation group. It's a finitely presented small cancellation group. So given any finitely presented group, you can find a small cancellation group here, so that G, the given group, is a quotient of this small cancellation group. And not only that, you can also, you have a control over this coefficient, over the small cancellation coefficient. So you can also choose that. I mean, the proof, the detail of the proof would tell you very obviously that you have a control. You can simply use words like this. You can use words like this to construct such presentations here, so that it satisfies small cancellation condition like C prime lambda. How do we, I mean, the outline of the proof, how do we get that kind of a group? So if G's presentation is like this, then we would generate H with the same generating elements, A1 to AN, and two other extra elements, and then define, as I was mentioning, then define relators involving these, so that the relators would satisfy a condition like this. That would give H to be a small cancellation group. And then you define a homomorphism from H to G. You just send AI to AI and BJs to 1. And the kernel would be exactly B1 generated by B1 and B2. And that's this finitely generated kernel. So this is a very nice example where it tells that given any finitely presented group, we can, and a real number, positive real number, we can construct a small cancellation group of that coefficient, of that order, so that G is a quotient of that small cancellation group, and that too with a finitely generated kernel. So that's a very nice construction. So it's a very small paper. It's a good read. So now now we would look at the decision problems, the so-called decision problems, which through which Max then started off the study of this type of groups. So what are the decision problems? I mean, there are other, but here the two problems I would mention is word problem, which is to decide whether or not a given word is trivial, and a conjugacy problem, which is about deciding whether or not two given words are conjugate in the given group G. So these two problems then prove that for fundamental groups of genus G surfaces, these problems have a solution. I mean, these problems are solvable. I mean, solvable in the sense that we can design an algorithm. He devised an algorithm that is essentially based on his observation, his following observation, which would give these problems, a decision, an answer in finite time. So how is that? The observation he made is that a freely reduced non-trivial word W, if a freely reduced non-trivial word W in this group, this fundamental group is trivial, then W contains more than half of a defining relator R. It contains more than half of a defining relator R. So the defining relator here is the one which is the product of these G commutators. And he's saying that if a reduced word, any freely reduced non-trivial word has to be trivial, then it should contain more than half of a defining relator. That's the single relator here. Or any cyclic permutation of R inverse here. So this observation led to the famous dense algorithm, and later on Grindlinger extended this observation. He proved similar results in the C prime 1/6 groups, and later he proved for C prime 1/8 groups the conjugacy problem and so on. So this paved the way for the decision problems, the solvability of the decision problems in small cancellation groups. So then what the Grindlinger lemma says is that it's supposedly the most remarkable result in this small cancellation theory. Not only in the classical small cancellation theory, in the various other forms of generalizations that small cancellation theory has. In every small cancellation type theory, there would appear something like a Grindlinger lemma in a different avatar maybe, but that's a crucial result. So what the Grindlinger lemma says is that if W be a cyclically reduced word in a small cancellation group, G satisfying a small cancellation hypothesis C prime 1/6, represents a trivial element, then this has a subword U, which is also a subword of a defining relator. So this was not a defining relator, this was just a trivial element in G. That means it's an element here in the normal subgroup generated by this set. Now, this says that if it's trivial, then it has a subword U, which is also a subword of a defining relator, such that it's a subword, this is a prefix, and the rest of it is V, and it is a subword in this way, that length of U is more than length of V. That means length of U is greater than half of R. So U is at least half of the defining relator. So that's what Den observed in surface groups. And which later on proved by Reidmeister that it doesn't necessarily depend on the hyperbolic metric structure and so on. That's the motivation for Grindlinger proving this result in this context. So in the due course we will mostly look at this type of metric small cancellations. We will also see some CP type small cancellation conditions in the coming slides. So now based on this Grindlinger's lemma, what is the dense algorithm? This is the algorithm for the word problem, and the algorithm for the conjugacy problem would be a little different, but it will reduce to this one. And there you have to conjugacy problem is to determine whether or not two given words are conjugates. So it can be shown that those two words will represent a Van Kampen diagram which is like an annulus, and whose two boundaries are the given two words W1 and W2. And it can be shown that one can find a path along that annulus and cut it open, cut the annulus open along that, and that would give rise to a simply connected Van Kampen diagram, and that would reduce the problem to the word problem and so on. So how to solve the word problem, the dense algorithm in this context of C prime 1/6 groups? What this algorithm says is that first you search for such subwords from defining relators R, which is of this form. You find this kind of subwords. If you find them, replace that subword by the inverse of this, because this is smaller. If you replace this by the inverse of this, see why the inverse of this? Because u and v, uv is 1, and then u would be v inverse. So you are replacing u by v inverse. Now V inverse has the same length as V. So essentially what you are doing is you are reducing the length of W by replacing it with V inverse. And after replacing, it says that you freely reduce. If you have again something like S inverse, you replace it with empty words and so on. You continue. So call it W1. In G, the words W0 and W1, these are equivalent, as it can be seen easily, and the length of W1 is lesser than W0, the starting word. So we have got an equivalent word in this presentation, which gives me the same element in the group, and with a smaller word length. Now you keep constructing inductively, you keep constructing such words by repeated application of these two. Search them. If you find them, then replace with them, and then freely reduce and get the word W1. This way you keep constructing W1, W2, and so on. And each of these will be equivalent by the same argument in G. And each of them would be the, I mean, if you can pass to a further word, further Wi plus 1, its length would be smaller than Wi. So at most W number of steps would lead us to either an empty word. So that would tell us that W is a trivial word in G. And if it doesn't, it would lead us to a word W hat, which cannot be shortened by this method any further. And then it means that it is not one in the group G, because this is the way you reduce in a group. So it cannot be further reduced in this presentation. So it's a non-trivial word. So this is the dense algorithm in short. So a lot of combinatorics is involved behind these statements. The Greenlinger lemma implies that in a C prime 1/6 group, you have something like this, right? That you have a subword which is like this. So then that means you can run the dense algorithm, right? So in C prime 1/6 groups, you have a solvable word problem via this dense algorithm. So this was a very nice result in the classical small cancellation theory, and this was later improved, generalized, extended to many different contexts. Next is the linear isoperimetric inequality. So we have a freely reduced W0, which is here in the set of relators, and we can define a combinatorial area. I mean, we can count the number of two cells in the Van Kampen diagram. We have seen that it is a two complex, and we can just count the number of two cells in that Van Kampen diagram. That's the area. So the length of the perimeter, this is the Van Kampen diagram, then this is the perimeter, and the length of the perimeter, since the Van Kampen's lemma says that the perimeter delta M0 is W0, so the length of the perimeter is just the W0 norm of W, the word length. So the presentation satisfies a linear isoperimetric inequality, means that you have a constant C such that a freely reduced relator W0 can be a boundary level of a diagram M0 with at most these many two cells. at most these many 2 cells it can fit in that Van Kampen diagram. So that's that tells us that and in another consequence of this Grindlinger lemma is that the C prime 1/6 groups, they satisfy this linear isoperimetric inequality. And now we see that in the previous talk, Dr. Shodhar talked about hyperbolic groups, and hyperbolic groups were defined by Gromov, and there were many different characterizations for hyperbolic groups, and one of them is a linear isoperimetric inequality. So and C prime 1/6 groups, they do satisfy this linear isoperimetric inequality. So here is a definition of hyperbolic groups. In the previous lecture also we have seen this. So in this from this result, which is a consequence of Grindlinger's lemma, we see that it has a linear isoperimetric inequality, and that implies that C prime 1/6 groups are hyperbolic groups in the sense of Gromov. So, and historically also these small cancellation groups played an important role in the motivation behind these groups. So now the main question becomes the guiding question becomes that if we are given a group G and subgroups R1, R2, Rn, what should be the conditions that we should put on this collection of subgroups so that we understand the normal subgroup generated by these subgroups of G and the quotient of G by this normal subgroup generated by R1 by Ri's. So I mean, let's just rephrase it. Then we will see that S was our generating set. So we have seen that G was a quotient of Fs by the normal subgroup generated by R. And what is this R? So R was the collection of words, right? Words in certain types of words, reduced, etc., in Fs, but they were words. So the normal subgroup generated by R can be thought of as the normal subgroup generated by the cyclic subgroups of these words. If we have to think of the small cancellation condition in this context of the statement, that how do we put conditions on general collection of subgroups, a small cancellation like conditions, so that we understand the normal subgroups and the quotients better in general. So the classical small cancellation theory would fit into this setup as this, that G is here the free group and Ri's are these cyclics, infinite cyclics. So in this context, I mentioned here that Mikhail Gromov, he mentions in one of his very important papers, Random Walks in Random Groups, that the freedom of G, freedom in the sense of this freedom, here the group G is free, right, in the classical small cancellation. He mentions that the freedom of G is not indispensable, in the sense that I mean, you can relax the freeness of Fs and look for similar small cancellation conditions. So what would be the next step to look at? If we dispense with the freeness, if we relax the freeness, that would be the generalization in some sense of a free group, which are the word hyperbolic groups. So then comes the generalization of small cancellation theory over the hyperbolic groups. So so this generalization was by Olshansky, and Olshansky was working on small cancellation theory for a long time, and he also constructed the Tarski monster group And then he extended the small cancellation theory on hyperbolic groups, in this sense that in any way, if we have to define the small cancellation, then we have to somehow say that a piece, first we have to fix the notion of a piece, and then we have to say that a piece, whenever it appears in a relator, it is small compared to the relator, the length of the relator. And that means the small cancellation. When we form a product, it cancels less subword compared to the total length of the product, and so on. So we have to somehow come to a definition of a. We have to somehow get hold of something like a piece. If we do not have a piece a priori, then we have to define something like some generalization of a piece to make sense of this discussion to start with. And here Olshansky's prescription is that you start with a hyperbolic group, which is G naught, which has this generating set S and relators R naught. Now, in the sense of the previous slide, so here you find something like a R1, that a symmetric set of geodesic words excuse me, in G naught, where each of the words are at least of some length, some very large positive number, greater than a large positive number. So we are not going into the details of these choices, this construction, but intuitively we will see why it is a generalization of the earlier small cancellation theory. See, earlier when we defined a piece, this is a typical situation from a classical small cancellation theory. A piece is a subword of a relator where two different relators meet. So this is a relator. In this description, U fits somewhere. This is another relator. In its expression, U fits somewhere else. So there is a piece where two relators overlap on their boundary, on the relator along subwords. So now Olshansky is suggesting that we will be taking a quotient. We will be taking a quotient of G naught by the normal subgroup generated by R1, and that is like G1 is generated by the same thing S, and relators are more. It's R1, R0 union R1. Now, an epsilon piece with respect to R1, an epsilon piece is something like this. Here, some subword of R1 words like R and R prime, we will call an epsilon piece. U is an epsilon piece if it appears in R1 word like this. There should be another R1 word which is R prime, where we have another something like this U prime, which gives us something like a quadrilateral here, where the two vertical sides of the quadrilateral is very small, is epsilon. It's very small compared to the size of the relators and also the hyperbolicity constants of the base group and so on. So we are not going into the choices of these coefficients. So here we will call such a subword to be an epsilon piece, and we will say that R1 satisfies a small cancellation condition C prime epsilon rho lambda. Earlier we were not mentioning epsilon and rho. This epsilon and rho are the coefficients coming for the fact that we are no longer on a free group situation, free group quotient situation. So here, just see that compared to the lengths of these relators, the previous stage relators, which are coming from R0, can be very small. So there would be large overlaps. I mean, long overlaps with the R1 relators of R0 relators, possibly. So we want to avoid that. So we are looking only at R1 words. and R1 satisfies this small cancellation condition if an epsilon piece is less than lambda times this. Okay, so now moving forward, the small cancellation theorem in this context by Olshansky, it says that for suitable choice of these coefficients epsilon, rho and lambda, the quotient is delta 1 hyperbolic for some delta 1. Here it was delta not hyperbolic, and the hyperbolicity constant changes, and we have a delta 1. Okay, so now I just mentioned here quickly that this can be repeated. Just from the construction, from the definition, it is very obvious that this process can be repeated. We can take a quotient, further quotient of G1 and so on. Okay, now another approach to small cancellation over hyperbolic groups is given by Delzin, and Delzin's approach was by using Gromov-Wiener product to define a small cancellation condition. And in his definition, he took a G which is hyperbolic, and he took a set of relators which are suitably symmetrized. I'm not going into the detail. Some suitably reduced elements in G, which we will be considering as relators, and we choose lambda to be less than 1/8. Then we say that R satisfies the small cancellation C prime lambda if the minimum of all elements here, the minimum length of all elements here are greater than this. And you see that this is something like that row condition in the previous. And here he doesn't talk essentially about a piece, but what he talks about is possibly far more penetrating, in the sense that he talks about something called a fellow traveling condition, in the sense that R1 and R2 are elements here, and for A, where A's length is bounded above by 1000 delta, some constant, then A R1, and this is the Gromov-Wiener product. This is just the definition is that A, B, and C, if this is the thing, then this measures essentially how much a geodesic starting from C going to A and B fellow travel. In a free group, this is very easy to see. In general, we have an estimate for we have a definition of the Gromov hyperbolic groups in terms of this inner products. And here he enforces that whenever that fellow traveling distance is greater than something, for these two elements here in capital R, then this relator, if we can say it, if we can call it a relator, then this relator R2, since its fellow traveling with A R1 is quite high, greater than some number, then R2 has to be a conjugate of R1 by A. So that's his definition of small cancellation. He says that the group G would, the set R would satisfy the small cancellation condition C prime lambda over the hyperbolic group G, delta hyperbolic group G, if it satisfies these. And then he uses this condition to show that whenever we have a non-elementary delta hyperbolic group G, and then if R is a family of suitably chosen words, elements in G, satisfying such a small cancellation condition, then the normal subgroup generated by R is free. That's remarkable. And then also he shows that the normal subgroup, the quotient of the group by the normal subgroup is delta prime hyperbolic for some delta prime. And here is a special case of that, in the sense that if we take something called hyperbolic elements in hyperbolic groups, a set of them, F1 to Fn, with large something called stable length or stable norm something. We will see a similar definition a few slides later. Then the normal subgroup generated by them raised to an index n. Then there exists such an integer n, so that if we raise all of them to n and then take a normal subgroup generated by them, then that is free. And also similarly the quotient is hyperbolic. So these are remarkable results. Yes.
Yeah. Could you wrap up another 5 or 6 minutes?
Okay, sure. I will speed up. So
Sure.
another result in this paper, very important result, is SQ universality, which says that given any countable group, there is a quotient of the given group where you can embed that given group. So he proved the SQ universality for groups satisfying this type of conditions. In fact, he proves for non-elementary hyperbolic groups SQ universality, which was also proven by Olshansky in a different result by different methods. And then comes the graded small cancellation. As I mentioned earlier, that this process of Olshansky's small cancellation and also Delza's can be repeated. So it's nothing but a repetition. We start with a G naught, and then you keep considering small cancellation subsets with different coefficients, and then keep taking quotients that will give you a sequence of epimorphisms, and the limit of this is called a graded small cancellation group, which is like a stratified small cancellation. Not one coefficient holds for the entire group. You stratify the relative, and they satisfy different small cancellation conditions. And another is a very important notion of graphical small cancellation by Gromov, where he considers graphs and graph maps, labeled graphs and graph maps, and defines small cancellations. What he says here is that if you take a bouquet of k circles, which I call rows k, and then the fundamental group of that is the free group, and if the circles are labeled by S letters, if you have something called a label, something called a map like this from any graph with certain condition to this bouquet of circles, then you can consider this quotient group of the free group by the induced map and the normal subgroup generated by that, and you can define a small cancellation condition on that, and he proves that quotients of such groups will be hyperbolic again. Like this, the group GM is hyperbolic, and theta m, the initial graph index in the Cayley graph of GM. These were actually elaborated by Delza and Arjantseva in a later paper. So from graphical to geometric small cancellation, I'm out of time. So this is just one step further from the previous thing, and here you see there is a new way of defining small cancellation over groups acting on hyperbolic spaces in a certain way. So I will not go into details here. And there are other generalizations of small cancellation theory. One by Damani, Girardel, and Osin, the important one, rotating families and so on. That's also motivated by Gromov's work, and also Coulomb. So these results have very important consequences, and this is then filling was proved by Osin for relatively hyperbolic groups. SQ universality was proven. Another thing is cubical small cancellations, and there are plenty of different applications like Gain algorithm, then filling, and normal subgroups in FM hyperbolic, relatively hyperbolic, mapping class groups out FNs. These are coming from the generalized geometric small cancellation context, SQ universality, and other construction of monsters like this. Gromov's monster, I just want to mention, is a very important example. This is a counter example, the first one, and now possibly there is one more example where you have a group which does not coarsely embed in a Hilbert space, which gives a counter example to some version of a Baum-Kohn conjecture. Okay, so I will stop here. Thank you.
Thank you very much, Subrata, for this nice presentation. And so I will request the participants, if they have any question, please unmute yourself and ask the question directly to the speaker. Okay, I can't see any questions. So anyway, let us thank the speaker again. And Subrata, thank you very much.
Thank you.
Thanks very much.
To the organizers for allowing me to speak. Thank you.
Okay, so yeah, Subrata, you can stop sharing your screen. Yeah.
Thank you.
So next speaker is Gianluca Faraco. Luca, are you here?
Yes, I'm here.
Yeah, sure. So can you start sharing your screen?
Okay, so just a second.
Yeah.
Do you see the slides?
Yes, sure. So tell me whenever you are ready, I will start because, yeah.
Okay, good. So tell me when I can start.
Okay. So we shall start now because we are a bit late already. So welcome everyone for the last talk of today's Geometry, Topology and Dynamics Symposium. And so Gianluca Faraco is a postdoc at Indian Institute of Science, Bangalore, and he will be talking about periods of meromorphic abelian differentials. So Luca, up to you.
Okay, thanks Arpan for the introduction, and let me thank the organizer for giving me the opportunity to deliver this talk here in this amazing math festival. And I'm going to discuss a part of an ongoing joint work with Shubhajoy Gupta. And this work is somehow related with some topic already covered by Shubhajoy yesterday, but this is a result which is also interesting on its own right, and so I will discuss here. Okay, so I start introducing the main object. So SGN will denote a surface with G handles and N punctures, and the surface is also assumed to be connected, oriented, and of hyperbolic type. That means all the characteristic is negative. So as the name suggests, the Riemann surface is the datum of a topological surface along with a one-dimensional complex structure. So we have charts taking values on C, and transition functions are restrictions of bilomorphism on their domain of definitions. By the abelian differential on a Riemann surface, instead we mean an holomorphic one form. That means these are an assignment of holomorphic function to each local coordinates in such a way fzdz is invariantly defined. And for any fixed Riemann surface X, we define omega X, this vector space of abelian differential over the Riemann surface, whereas omega and Gn will denote a much bigger space, is the set of all possible couples, where X is a Riemann surface, as omega again is an abelian differential. So, fix a Riemann surface and pick an abelian differential, omega, and omega is an holomorphic one form, and then as such, it can be integrated along any closed curve. And then we may define a mapping, an association that takes each curve gamma to the complex number defined by the integration of omega along gamma. And such an association turns out a well-defined representation from the first homology group with integer coefficients to the additive group of complex numbers. And this representation is called period character of omega. This can be thought like an object naturally attached to the abelian differential. Well, we can define now another mapping called period mapping, and here is denoted by PR in bold, from the global space omega and Gn to the whole space of representations from the first homology group with integer coefficients to the additive group of complex numbers, mapping each couple x omega to the representation chi defined by the integration of omega along each along closed curves gamma. So we have this mapping. Now it sounds natural to ask who the image of such a mapping is. So in other words, suppose we are given with a representation from the first homology group to C, does it arise as the period character of some abelian differential with respect to some complex structure X? This is the question we would like to answer, and let me state before what happens for closed surfaces. And for this case, we go back to 1 centenary ago, because out in 1920 provides necessary sufficient conditions for a character chi to appear as the period of some abelian differential omega with respect to some complex structure X on the closed surface. And I'll prove this theorem using some geometric and elementary argument, let's say, but the same theorem has been recently rediscovered by Misha Kapovits around 2000, but his proof relies on Ratner's theory, so it's another connection between geometry and ergodic theory. By the way, the condition provides, so what I'll notice is that a character chi appears, so there are basically two abstractions for a character chi to be the period of an abelian differential. The first is that such a quantity, which is a real number, has to be strictly positive with respect to some standard symplectic basis. And this quantity is called volume of chi. Terminology is not casual. There is the study is very well motivated, but I give you the motivation later because using this from this point of view, it might sound unclear why we call this a number volume. And so let me consider then the second condition, which actually applies to a special family of representations, namely those representations whose image is a lattice in C. In this case, we need a further requirement that the volume of chi is at least 2 times the area of C mod gamma, mod lambda, sorry. And as I said, these are necessary and sufficient conditions. So for closed surface, the image of the period mapping defined here when n is 0 is completely determined and characterized. So what happens for punctured surfaces? What we have shown with Shubojai is that every representation chi appears as the period character for some abelian differential omega with respect to some complex structure X. And so the picture is changed completely because now there are no conditions. So it's classical that any Riemann surface on a punctured surface, so let's say a punctured Riemann surface, extends to a Riemann surface on a closed surface as G. And this is basically an application of the Riemann extension theorem, because if you pick any puncture and a small open neighborhood of such a puncture, this is biomorphic to the puncture disk. And this chart, now Riemann extension theorems applies, and this chart can be extended over 0, and then you have an holomorphic function over the unite disk, and you use this function for viewing this disk on your surface, and what you are doing, you are filling the puncture. You do the same argument for all the puncture, you get a closed surface with a Riemann with a complex structure X bar who extends X. This can always be done, but if you pick an abelian differential in omega X, this extends to a meromorphic abelian differential omega bar on X bar, because some of the punctures may appear as pole of this abelian differential. And so if you adopt from this new light, what our theorem says is that any representation chi appear as the period of a meromorphic abelian differential omega bar for some complex structure S bar on SG. And notice that here the surface is closed, but the representation is taken from the first homology group of a puncture surface. Because when you have a meromorphic differential, there is at least one pole. And so if you compute this integral, suppose here the omega is meromorphic and gamma is a closed curve enclosing one pole, the value of the integral may be very well different from 0, because this is the residue. And so you have a contractible curve, and the period of this contractible curve is different to 0. So this association is no longer an homomorphism. We bypass this problem by removing all the poles. In this case, you have a puncture surface, and now this association is a well-defined representation. So this is the reason why, even if the surface is closed, we consider character from a puncture surface. How do we prove this result? So we adopt a geometrical point of view, and then I need to introduce quite shortly translation structures. If you are familiar with the language of geometry structures, so this kind of definition is not difficult for you. So a translation structure is an atlas of charts of the form Z goes to Z power K, where K could be greater than 1. So this means that some charts are not local homomorphism, but they are simple branch coverings around a discrete set of points. HR take values on E2, and transition functions are translations in E2. So each translation can be identified with an element of C. In the case you are not familiar with with geometric structures, you can think of translation structures like the surface that you get from a polygon on E2, and where you identify the sides using translation. So consider this picture here. This is an L shape in E2. This is an octagon where some sides are aligned, and you can identify one with 1, 2, and 2, 3, 3, and 4, 4 using translation like the arrows indicate. And when all the identifications are done, you get a closed surface of genus 2, and all the black points identifies to a unique point, which is, let me say, somehow bigger. Bigger because I'm not going through the detail of what bigger means, but the point is that around this point, each local chart space to be a local homomorphism and has this form where K is at least 2. In this particular example, K turns out to be 3, because if you sum the inner angles, you get a point of angle 6 pi, and then this means that K is 3. But anyway, you can think translation structures like also polygon, surface that you get by gluing sides of polygon via translations. There is sorry. From the complex analytical point of view, a translation structure is a couple, X omega, where X is a Riemann surface and omega, again, is a abelian differential. And that is that a translation structure is a geometric structure, and as such, it defines a representation called holonomy. Such a representation somehow encode data of the geometry. And for the very specific case of translation structures, what we have again is a representation from the first homology group into C. So, representation in the representation space, in this representation space, may have a twofold role. They play two roles. They could appear as the period of some, as the period character of some abelian differential omega, or they could be the holonomy of some translation structure on the surface. It happens that a representation chi appear as the period character of some abelian differential omega on X, even though, with respect to some complex structure X, even though if it arises the holonomy of some translation structure. And so in the case of closed surfaces, a representation chi is the holonomy of a translation structures if and only if these conditions are satisfied. And now I can tell you what volume means. So suppose that a representation chi is the period on a some abelian differential, then is also the holonomy of a translation structure on the surface. And as such, this geometric structure as a volume, as an area. And the area is represented by exactly this quantity. And for closed surfaces, it happens that you have a translation structure. Positive area is something needed. You can get rid of this condition. So the requirement volume to be positive can be easily explained using translation structures. And also the second condition has a very geometrical interpretation, but I don't think I have enough time for going through this condition, but it can be explained very clearly by using translation structures. So this characterization is the point of view of the proof of the theorem that of Shubujoy and me. In the sense that starting from a representation chi, what we have done is we have found translation structures having chi as the holonomy. And once the translation structure is found, then you have an abelian differential who extends to a meromorphic abelian differential on the closed surface. So chi in general as a holonomy of a geometric structure is not sufficient for determine a unique geometric structure. So in general, if you want to recover a geometric structure starting from a representation, there are some choices. There are some choices are needed, and the structure that you get depends on these choices. But so this property somehow gives us the right freedom, enough freedom for finding translation structure for any given representation. So also if we take the trivial representation, we are able to find a translation structure on an open surface, not closed, of course. And So there is an abelian difference associated to that structure. So due to the lack of time, I can explain properly the techniques we have used, starting from a representation for determine a translation structure. And so for this reason I'm going to stop here. Thanks.
Thank you, Luca. Thank you very much. So in the audience, if you have any question, please ask the speaker directly. Unmute yourself and ask the speaker. Okay, I don't see any questions. In that case, let's thank the speaker again for this nice presentation. And thank you, Luca. Thank you very much.
Thanks to you.
Okay, so this was the final talk of this evening. I think, Soma, are you here?
Yeah. Nice
So
talk,
to you.
Luca.
Thanks.
Yeah, so let's conclude this session and also the, kind of academic part of the whole conference here, because tomorrow we have a math quiz coming up in the morning, and in the evening we have a panel discussion on maths and society. So yeah, thanks a lot, Orpunda, for chairing this session, and we conclude this symposium here. Okay, thanks a lot, everyone.
Bye, everybody.
Thank you.
Bye.
Bye. Thank you, everyone.